What if everything you were taught about the limits of ancient human capability was wrong? Not slightly wrong, but fundamentally, deeply wrong. Imagine standing alone before a structure so precise, so massive, so mathematically perfect, that even with today's technology, replicating it would push us to the edge of what's possible. Now imagine being told that this was built by people who supposedly lacked advanced tools, machines, or even complex mathematics. That unsettling gap between what we see and what we're told is where this story begins. Across the world, scattered like silent witnesses to a forgotten age, are structures that should not exist, at least not according to our understanding of history. Enormous stone blocks cut with laser-like precision. Buildings aligned to astronomical events with accuracy that rivals modern observatories. Complex engineering systems designed to withstand earthquakes, floods, and the passage of thousands of years. These are not myths or legends. They are real, measurable, touchable. And they refuse to fit neatly into the timeline we've accepted. For generations, we've been taught a comforting narrative: human progress is linear. We start primitive, slowly develop tools, master agriculture, invent writing, and eventually arrive at modern technology. It's a story of constant upward movement, where the present is always smarter than the past. But what happens when physical evidence challenges that story? What happens when ancient engineering looks less like a crude beginning, and more like the remnants of something already advanced? Stand before the Great Pyramid of Giza, and the feeling is immediate. There's a strange silence, not just of sound, but of explanation. Over 2 million stone blocks, some weighing as much as a fully loaded commercial airplane, placed with a precision that leaves gaps thinner than a credit card. The structure is aligned to true north with an accuracy modern surveyors still struggle to explain. This wasn't guesswork. This wasn't trial and error. This was deliberate, calculated, and exact. And Egypt is just the beginning. High in the Andes, stone walls zigzag across mountain ridges, composed of multi-ton blocks fitted together so tightly that not even a razor blade can slip between them. No mortar. No binding agent. Just stone shaped to stone, each piece uniquely cut, interlocked like a three-dimensional puzzle designed to flex during earthquakes instead of collapsing. Modern engineers study these walls not as historical curiosities, but as lessons. In Turkey, a site buried for over 10,000 years has rewritten the history books. Massive stone pillars, carved with intricate reliefs, arranged in deliberate geometric patterns long before civilization was supposed to exist. No cities. No metal tools. No agriculture, according to the official story. And yet, here it is. Planning. Symbolism. Engineering. Organization on a scale that should have been impossible at that time. These places share a disturbing common trait: we can describe what they are, but we cannot fully explain how they were built. That's the quiet problem archaeologists don't like to talk about. Because explanation implies understanding, and understanding implies that someone, somewhere in the past, knew more than we're comfortable admitting. Our textbooks say ancient builders were clever, resourceful, and skilled within their limitations. But the stones tell a different story. The stones suggest mastery. They suggest knowledge passed down, refined, and applied with confidence. Consider the cuts themselves. Not rough. Not uneven. But smooth, flat, and consistent. In some cases, curved with perfect symmetry. Granite, one of the hardest natural stones on Earth, shaped as if it were clay. Modern attempts to replicate these cuts using only known ancient tools often fail, or require extreme effort for results that still fall short. Experimental archaeology shows us what should be possible. The ancient results show us what actually was done. The gap between the two is where the mystery lives. And then there's the scale. Moving a single stone weighing 50 tons today requires specialized cranes, reinforced transport vehicles, and detailed engineering plans. Ancient sites contain stones weighing 2, 3, even 10 times that amount, placed at heights, angles, and locations that defy simple explanations. We're told manpower did it. Ramps did it. Ropes did it. But when engineers calculate the forces involved, the friction, the terrain, the logistics, it becomes clear those explanations are more like placeholders than answers. What's more unsettling is how often these feats appear independently, across continents, separated by oceans and thousands of years. Similar building styles. Similar stone-cutting techniques. Similar astronomical alignments. Similar mathematical ratios embedded in architecture. Coincidence is one explanation, but it's not a satisfying one. Because coincidence doesn't account for consistency. Ancient builders understood geometry not just as a concept, but as a tool. Circles, triangles, ratios, and alignments were woven into stone itself. Structures were positioned to mark solstices, equinoxes, and celestial cycles with astonishing precision. This wasn't superstition. It was observation. Measurement. Long-term data collection. It implies generations of knowledge, patiently accumulated and preserved. Which raises an uncomfortable question: where did that knowledge go? If ancient civilizations possessed engineering capabilities that rival or even exceed some modern methods, why did later societies seem to forget them? Why do we see regression instead of continuous improvement? Why do myths speak of lost golden ages, great floods, and sudden destruction, stories repeated across cultures that supposedly had no contact with one another? The idea that advanced knowledge can be lost feels foreign to us. We live in an age of digital backups and global communication. But history tells a different story. Libraries burn. Cities collapse. Entire populations vanish. Skills that aren't constantly practiced disappear. Knowledge that isn't written down becomes legend, and legend becomes myth. And myths are easy to dismiss. That dismissal may be our greatest blind spot. Because when we strip ancient stories of their symbolic language, what often remains are echoes of real events, catastrophes that reshaped landscapes, societies that rose and fell, technologies that vanished not because they failed, but because the people who understood them were gone. This is not about claiming ancient people had smartphones or spaceships. That's a distraction. The real mystery is more subtle, and more disturbing. It's the possibility that human intelligence, ingenuity, and engineering sophistication reached peaks in the distant past that we are only now beginning to recognize again. The stones don't lie. They don't exaggerate. They don't conform to narratives. They simply exist, unchanged, immovable, and patiently waiting. Waiting for us to ask better questions. Because once you truly look at these ancient structures, not through the lens of assumption, but through the lens of engineering, the comfortable story of human progress starts to feel fragile. And in its place emerges something far more intriguing, the idea that history is not a straight line, but a cycle. That civilizations rise, master their world, and sometimes disappear, leaving behind only stone, silence, and unanswered questions. This is not just a story about the past. It's a story about memory. About what survives. About what we choose to ignore because it doesn't fit. And as we begin this journey into lost ancient engineering feats that challenge modern knowledge, one truth becomes impossible to avoid: the greatest mystery is not how these structures were built, but why we stopped asking how long ago. The story we are taught about human history is clean, orderly, and reassuring. It tells us that progress moves in one direction, from ignorance to knowledge, from simplicity to complexity, from stone tools to silicon chips. According to this version of the past, every generation stands taller than the one before it, building neatly on what came earlier. It's a story that makes us feel safe, superior, and certain that we are living at the peak of human achievement. But that story only works if the evidence cooperates. And increasingly, it doesn't. At first glance, the official timeline of human development seems reasonable. Early humans learned to make basic tools. They hunt, gather, and slowly settle down. Agriculture appears. Villages become cities. Writing is invented. Technology advances step by step, century by century. It's simple, predictable, comfortable. Yet buried beneath this narrative are anomalies, small at first, easy to ignore, that quietly refuse to stay in their assigned place. For a long time, these anomalies were treated as mistakes. Measurement errors. Misinterpretations. Outliers not worth serious attention. But as technology improved and data accumulated, those mistakes began to repeat themselves. Different researchers, different continents, different cultures, yet the same uncomfortable pattern kept emerging. The past was not as technologically simple as we assumed. One of the biggest cracks appears when timelines collide with reality. Archaeological layers are supposed to represent progression, older layers below, newer layers above. Simple enough. But what happens when advanced techniques appear where only primitive ones should exist? What happens when complex architecture, precise engineering, and sophisticated planning show up thousands of years earlier than expected? The standard response has often been adjustment, not rethinking. Dates are debated. Interpretations are softened. Terms like ritual, symbolic, or ceremonial are applied generously, sometimes as placeholders rather than explanations. Because once something is labeled symbolic, it no longer has to make practical sense. But stone doesn't care about symbolism. A stone block weighing dozens of tons still has to be quarried, shaped, transported, and placed. No amount of ritual meaning makes that easier. No belief system changes the physics involved. At some point, someone had to solve the engineering problem. This is where the official story begins to strain. Take the idea that ancient people were limited by their tools. We're told that without iron, steel, or advanced machinery, they could only achieve rough, imprecise results. And yet, we find stone surfaces polished to near perfection. We find angles so accurate they rival modern machining. We find holes drilled into hard rock with consistent diameters and depths that suggest controlled, repeatable processes. To explain this, historians often emphasize time. They argue that with enough labor and patience, anything is possible. Given centuries, primitive methods could slowly achieve remarkable results. It sounds reasonable, until you actually test it. Experimental archaeology has tried. Researchers attempt to recreate ancient techniques using replica tools. What they find is not just difficulty, but impracticality. The effort required is staggering, and the results rarely match the originals. This creates an uncomfortable tension. Either ancient people possessed far more advanced techniques than we credit them for, or our assumptions about their limitations are wrong. Another crack appears when we look at scale. Early societies, we're told, struggled just to survive. Food production was inconsistent. Life expectancy was low. Resources were scarce. Under those conditions, building massive stone complexes should have been nearly impossible. And yet, these societies somehow organized labor forces of thousands, planned projects that took decades or centuries, and executed them with astonishing precision. Planning alone implies advanced knowledge. You need surveying. You need logistics. You need an understanding of load distribution, material properties, and long-term stability. These are not accidental achievements. They require systems of education, transmission of knowledge, and leadership capable of coordinating immense efforts. But where are the records? This absence is often cited as proof that such systems didn't exist. No manuals, no blueprints, no detailed construction texts, therefore no advanced engineering. But that logic assumes that knowledge must be preserved the way we preserve it today. Writing is fragile. Paper burns. Clay tablets break. Oral traditions, while powerful, leave little physical trace. The lack of records may not indicate a lack of knowledge, but a loss of it. History is full of such losses. The collapse of the Western Roman Empire led to centuries where engineering techniques, road-building methods, and architectural knowledge faded or vanished entirely. Concrete recipes were forgotten. Infrastructure decayed. Progress reversed. And that happened in a society with writing, bureaucracy, and extensive documentation. Now imagine a similar collapse in a much earlier age. Suddenly, the gaps in the timeline don't seem so strange. Another issue lies in how we define advanced. Modern technology is electrical, digital, and mechanical. We measure advancement by speed, efficiency, and automation. But ancient engineering may have followed different priorities. Durability instead of convenience. Harmony with natural forces instead of domination over them. Precision without mass production. If that's the case, we may be overlooking sophistication simply because it doesn't look like ours. Consider alignment. Many ancient structures are positioned with extraordinary astronomical accuracy. They track solar movements, lunar cycles, and stellar positions over vast spans of time. Achieving this requires long-term observation, careful record-keeping, and mathematical modeling. Yet these accomplishments are often dismissed as religious or ceremonial, as if belief somehow replaces calculation. But belief doesn't explain consistency. Belief doesn't explain why the same alignments appear across different cultures, in different hemispheres, using different materials, but achieving similar results. There is also the problem of inherited assumptions. Archaeology, like any discipline, builds on previous conclusions. Once an idea becomes established, it's taught, repeated, and reinforced. Challenging it requires overwhelming evidence, and even then, resistance is strong. Careers, reputations, and entire frameworks depend on maintaining continuity. So anomalies are often treated cautiously, quietly filed away, or reframed to fit existing models. Yet the sheer number of these anomalies is becoming harder to ignore. Advanced stonework appears earlier than expected. Sophisticated metallurgy shows up where it shouldn't. Mechanical devices emerge centuries ahead of their supposed time. Each case alone might be explained away. Together, they form a pattern. And patterns demand attention. This doesn't mean the official story is entirely wrong. It means it may be incomplete. Oversimplified. Built around averages rather than extremes. Human history may not be a smooth upward curve, but a jagged landscape of rises and falls, breakthroughs and losses. If that's true, then the past becomes far more interesting, and far more unsettling. Because it suggests that intelligence is not new. Ingenuity is not exclusive to modernity. And collapse is not hypothetical. It suggests that entire chapters of human capability may have existed, flourished, and vanished, leaving behind only fragments that confuse us today. Fragments like massive stone platforms whose purpose we debate. Like perfectly fitted walls we admire but can't fully explain. Like tools and techniques that appear suddenly, without clear predecessors. The official story struggles not because it lacks answers, but because it assumes the questions have already been settled. And once that assumption is shaken, everything changes. Because if the past was more advanced than we believe, then our position at the top of history becomes uncertain. We are no longer the final chapter, just another page. Another civilization standing among the ruins of forgotten ones, confident in its progress, unaware of its vulnerability. The cracks in the story aren't flaws to be ignored. They are invitations. Invitations to look deeper. To question timelines. To reconsider what primitive really means. And as those cracks widen, they begin to reveal something beneath the surface, something older, more complex, and far less comfortable than the story we were taught. The question that haunts engineers, archaeologists, and historians alike is deceptively simple: how did ancient civilizations achieve such extraordinary precision without the tools we consider essential? Look closely at the stone blocks of Sacsayhuaman in Peru, where walls composed of massive stones fit together with almost no gaps. The angles are precise, the surfaces polished, and the interlocking stones so seamless that even a thin blade cannot be inserted between them. Yet, according to conventional history, these builders had no metal saws capable of cutting granite with such perfection. No powered machinery. No laser-guided instruments. Only manpower, chisels, and patience. That alone would be remarkable, but what comes next challenges the very limits of what we think is possible. Modern engineers who attempt to replicate these constructions using the supposed ancient techniques encounter immediate and insurmountable difficulties. Simple chiseling and abrasion fail to produce the same smoothness. Even using a team of dozens, moving stones and aligning them with such exacting tolerances requires hours, days, and sometimes weeks, often still falling short of the original. The problem is not merely labor, it is knowledge, skill, and understanding of material behavior. Ancient builders seem to intuit, or perhaps deliberately calculate, the expansion, contraction, and natural imperfections of the stones they worked with. They did not just stack rocks, they engineered them, treating each block as a custom component within an enormous machine, where a misalignment could disrupt the integrity of the entire structure. Consider also the geometric sophistication embedded in these constructions. The Great Pyramid of Giza, for instance, is aligned almost perfectly to the cardinal points, deviating by mere minutes of a degree. Achieving this without modern instruments is mind-boggling. Hypotheses involving stars, shadows, or simple sightlines provide partial explanations, yet they fail to account for the level of accuracy achieved. Observing and replicating celestial patterns over time requires sustained attention, meticulous record-keeping, and abstract mathematical reasoning. These are not trivial endeavors, they suggest a society that systematically studied astronomy, mathematics, and geometry with a rigor that modern students often find challenging even in a classroom setting. The challenge of precision extends beyond stonework and alignment. In India, the iron pillar of Delhi stands as a testament to metallurgical mastery that confounds modern scientists. Forged without modern steelmaking techniques, it has resisted corrosion for over 1,600 years. The quality of the iron, its resistance to environmental degradation, and the purity of the metal suggest a level of material science knowledge that should not have existed in that era. Ancient engineers not only shaped materials but also understood their long-term behavior, an understanding that continues to elude contemporary replicators attempting to recreate the pillar using historically documented methods. Beyond material precision, the ancient builders also demonstrated remarkable foresight in planning and logistics. Constructing massive structures with blocks weighing tens or even hundreds of tons requires more than physical labor, it requires an understanding of leverage, weight distribution, and team coordination on a massive scale. It requires meticulous planning to transport stones across uneven terrain, lift them into position, and secure them permanently without modern cranes or pulleys. Ancient texts rarely provide instructions, blueprints, or formulas, yet the results show a level of expertise comparable to modern engineering projects. It is as if they possessed a body of practical knowledge that was transmitted orally, through apprenticeship, or perhaps through methods now lost to history. One of the most astonishing aspects is the consistency with which these techniques appear across different continents and cultures, often separated by thousands of miles and vast oceans. From the perfectly cut stones of Inca walls in Peru to the monumental megaliths of ancient Egypt, from the precise alignments of temples in India to the star-oriented complexes of Central America, there is a recurring theme of exactitude and sophistication. This raises profound questions about knowledge transmission, independent discovery, or perhaps a shared source of understanding long before the histories we accept today. The similarities are too numerous to dismiss as coincidence, yet conventional explanations struggle to reconcile these parallels with the isolated development models we are taught. Even more intriguing is the evidence of advanced surveying techniques embedded in the layout of these sites. Lines of sight, leveling, and orientation demonstrate an awareness of physics and mathematics that modern scholars often underestimate. Some structures exhibit ratios and dimensions based on mathematical constants, suggesting not only precision but deliberate design guided by principles of proportion, balance, and structural integrity. These builders were not merely placing stones, they were calculating, measuring, and engineering solutions with an intuitive grasp of concepts we sometimes think of as modern discoveries. Experimental archaeology has shed light on the difficulty of reproducing these feats using only what is considered historically plausible. Teams attempting to move massive stones with wooden sledges, ropes, and ramps quickly discover the limitations of these methods. Friction, weight, and terrain impose constraints that ancient builders somehow overcame with apparent ease. Some researchers propose alternative techniques, from stone softening compounds to vibration-assisted movement, but evidence is often sparse, leaving room for speculation. What remains clear is that the conventional narrative, relying solely on manpower and simple tools, cannot fully explain the precision and scale of these constructions. This gap between what is documented and what is physically evident forces a reconsideration of ancient capabilities. The notion that humans of the distant past were primitive, limited, or technologically backward begins to collapse under the weight of evidence. Precision, planning, and material mastery suggest not only intelligence but systematic application of knowledge. It is as if these civilizations possessed engineering frameworks comparable to our own, yet developed them in forms suited to the tools and resources available to them. The result is a paradox: structures that are at once archaic and sophisticated, simple in appearance yet staggeringly complex in execution. The implications extend beyond mere curiosity. Understanding how ancient builders achieved such precision could revolutionize modern engineering, construction, and materials science. Techniques once dismissed as impossible may hold insights into efficiency, durability, and sustainability. It also challenges our assumptions about the linear progression of human knowledge. If ancient societies could achieve such feats, why did much of this knowledge vanish? Why do gaps exist where once there may have been continuity? The answer may lie in a combination of societal collapse, loss of documentation, or the simple passage of time erasing practical expertise that was never fully codified. Yet perhaps the most profound realization is the psychological impact of these achievements. Standing before walls carved with exacting precision, or observing monuments aligned with the stars, it is impossible not to feel awe. The builders were not only competent but visionary. They operated with foresight, planning, and skill that demands respect, and yet their methods remain elusive. Their work forces a confrontation with the limitations of our own understanding. For all our technology and knowledge, we are still struggling to match their achievements. The deeper question emerges: how did they conceive of such possibilities without the frameworks we rely upon today? Was it intuition, trial and error, inherited knowledge, or something more profound? Did these ancient engineers think in ways radically different from us, or did they simply have access to knowledge that later generations lost? The physical evidence compels us to question not just their capabilities but our assumptions about history, progress, and human potential. Ultimately, the precision of ancient engineering challenges more than just our technical understanding, it challenges our perspective on human history itself. It exposes the fragility of the narratives we accept, the assumptions we rely on, and the ease with which extraordinary feats are dismissed or explained away. The question remains open, tantalizing, and unnerving: if they could achieve such perfection without modern tools, what else did they know? And how much of that knowledge has been irretrievably lost to time, leaving only these silent, immovable witnesses behind to puzzle and astonish us? The mystery persists, compelling us to look closer, think deeper, and question everything we believe about the origins of human ingenuity. It is in the tension between what we know and what the stones tell us that the true wonder of these ancient feats is revealed. The more we examine them, the more it becomes apparent that the ingenuity of our ancestors may have been far greater than we have ever dared to imagine. Massive stones, some weighing hundreds of tons, lie scattered across ancient sites around the globe, monuments to an engineering capability that seems almost unimaginable. At first glance, the sheer scale of these constructions is enough to provoke awe. But as one examines them more closely, it becomes evident that the mystery goes far beyond size alone. The precision with which these stones were cut, shaped, and positioned challenges every assumption about the technological limits of ancient societies. The real question is not simply how they moved them, but how they shaped them with such perfection, and why they achieved a level of craftsmanship that even modern methods struggle to replicate. Take, for instance, the colossal granite blocks found in the pyramids of Egypt. Some of these blocks weigh as much as 25 tons, yet they were quarried, transported, and perfectly aligned with a precision that suggests a deep understanding of material properties and structural dynamics. Modern engineers attempting to duplicate these feats find that even with cranes, trucks, and hydraulic systems, achieving the same results is difficult. Ancient methods, which relied on manpower, wooden sledges, and rudimentary tools, appear insufficient when measured against the evidence of the final product. The stones themselves tell a story of skill, knowledge, and control over the materials that far exceeds the supposed technological means available at the time. This pattern repeats in other parts of the world. In South America, the Inca walls of Sacsayhuaman display polygonal masonry so precise that gaps between stones are imperceptible. These blocks, some weighing upwards of 200 tons, are fitted together without mortar, yet they remain perfectly stable centuries later, even in the face of frequent seismic activity. The walls flex under pressure rather than collapse, an effect that modern engineers strive to replicate in earthquake-resistant design. How a society without metal tools, cranes, or mechanized transport could achieve such feats remains a source of intense debate and fascination. Even more perplexing are the megalithic structures of Europe and the Middle East, where the combination of size, weight, and precision continues to defy conventional explanation. At sites such as Baalbek in Lebanon, massive stones weigh over 1,000 tons, positioned in ways that defy current lifting technologies. The quarry marks, cut lines, and transport routes suggest careful planning, yet no written records describe how these operations were conducted. The absence of documentation amplifies the mystery, forcing researchers to rely solely on the evidence of the stones themselves. And this evidence raises uncomfortable questions. If ancient people could manipulate such enormous materials, what other capabilities might they have possessed that have been lost to time? What makes these achievements even more remarkable is the apparent uniformity of precision. In Egypt, Peru, India, and beyond, stones were shaped to exacting standards, perfectly level, and aligned in complex patterns that required advanced understanding of geometry and structural forces. The surfaces of many blocks are smoothed to a degree that modern polishing techniques still struggle to match, and the angles between them often form perfect right angles or complex polygons. Achieving this with only copper tools, hammers, and abrasion techniques seems implausible. Experimental archaeology has repeatedly demonstrated the difficulty of producing even modest approximations of these results using historically plausible methods, highlighting the gulf between what should have been possible and what was actually accomplished. The logistics involved in moving and placing these stones add another layer of complexity. Transporting multi-ton blocks over uneven terrain, lifting them into position with limited mechanical assistance, and positioning them with millimeter accuracy requires not only extraordinary physical effort but also a sophisticated understanding of leverage, balance, and coordination. It suggests an organized workforce guided by knowledge and experience rather than brute force alone. Every placement had to be intentional, with careful consideration of the forces acting on the structure over time. Mistakes were not easily corrected, which implies that the builders possessed methods for planning and execution that remain largely unknown. Furthermore, the distribution of these megalithic achievements across continents raises intriguing questions about the spread of knowledge. Without evidence of direct contact between many of these ancient cultures, the similarities in construction techniques, precision, and material manipulation are striking. It suggests that either these capabilities emerged independently in multiple locations or that there existed some form of shared knowledge that has since disappeared. Either scenario challenges conventional historical narratives, which tend to emphasize isolated, linear development rather than recurring patterns of sophisticated achievement across time and space. Another element to consider is the long-term durability of these constructions. Many of the megalithic sites that continue to impress us today were designed to last for millennia, enduring earthquakes, floods, and the relentless effects of weathering. The durability of the materials, combined with the precision of their assembly, speaks to a level of engineering foresight that goes far beyond mere functional construction. These were not hastily erected monuments, they were built to endure, suggesting that the ancient engineers understood the interaction between materials, environmental forces, and time itself in ways that we are only beginning to appreciate. The level of skill and knowledge required to achieve these feats implies a society that prioritized engineering mastery, technical education, and the transmission of practical expertise. These civilizations may have possessed a body of knowledge that was highly specialized and carefully guarded, passed from generation to generation. The precision and scale of the work suggest that these techniques were not accidental but deliberate, honed through observation, experimentation, and refinement over long periods. In other words, ancient engineering was systematic, sophisticated, and highly developed. Yet despite the evidence, mainstream explanations often fall back on oversimplified theories, ramps, levers, and human labor. These explanations fail to account for the elegance, efficiency, and uniformity observed in the surviving structures. They reduce what are extraordinary feats of engineering to mere mechanical exercises, ignoring the intelligence, planning, and ingenuity required. By focusing solely on the physical possibility of moving stones, conventional narratives overlook the full scope of knowledge demonstrated in shaping, transporting, and assembling them with such precision. What is particularly striking is the contrast between expectation and reality. The tools and technologies available to these ancient builders, as far as the historical record tells us, should have limited them to crude, rough constructions. Instead, they produced work that rivals, and in some cases surpasses, modern capabilities in accuracy and durability. This contradiction forces a re-evaluation of assumptions about the capabilities of early civilizations and the nature of technological progress. Perhaps we have underestimated the intelligence, resourcefulness, and ingenuity of our ancestors. Ultimately, the mystery of these massive, perfectly placed stones is more than a question of brute strength or technical skill. It is a window into the minds of people who understood principles of physics, geometry, and material science in ways that remain elusive today. They designed and executed projects that required coordination, planning, and foresight on a scale that few modern societies could replicate without sophisticated machinery and advanced knowledge. The evidence demands recognition. Ancient engineering was not primitive. It was extraordinary. It was deliberate. And it challenges the core assumptions about what humanity was capable of long before the modern era. The stones, standing immovable through centuries, continue to provoke awe, wonder, and speculation. They are physical testaments to a knowledge that has been lost or deliberately obscured, silent witnesses to feats of precision and scale that seem almost impossible in context. Their existence forces a confrontation with uncomfortable questions about the timeline of human achievement, the continuity of technological knowledge, and the capacity for ancient societies to solve problems that we continue to struggle with today. Each massive block, each impossibly precise fit, is a reminder that the past may have been far more sophisticated, and far more enigmatic, than we have ever dared to imagine. The Great Pyramid of Giza has stood for more than 4.5 millennia, a silent sentinel over the sands of Egypt, yet it continues to defy our understanding. To the casual observer, it is a tomb, a monument built to honor a pharaoh long dead. But a closer examination reveals a structure that is far more than a mere burial site. Every aspect of the pyramid, from the orientation of its sides to the precision of its internal chambers, suggests a level of knowledge and intent that goes beyond conventional funerary purposes. Scholars, engineers, and historians alike have struggled to reconcile the pyramid's complexity with the tools, resources, and techniques supposedly available to the builders of the Fourth Dynasty. The scale of the Great Pyramid alone is staggering. It originally rose to a height of over 480 feet, composed of more than 2 million limestone and granite blocks, some weighing as much as 80 tons. The placement of these stones was executed with millimeter precision, forming perfectly straight lines and angles that align almost exactly with the cardinal points. Modern surveyors have noted that the deviation from true north is astonishingly minimal, and no error accumulates across the massive structure. Achieving this level of accuracy today requires sophisticated instruments, GPS technology, and precise calculations. How could a civilization without steel tools, cranes, or advanced mathematics accomplish such precision thousands of years ago. The interior design of the pyramid adds another layer of mystery. Far from being a simple chamber for a king, the internal passages, shafts, and chambers suggest knowledge of geometry, physics, and possibly even acoustics. The Grand Gallery, a long ascending corridor with corbelled walls, demonstrates a sophisticated understanding of structural forces. Its design distributes immense weight from above, preventing collapse while allowing passage to higher chambers. Even more puzzling are the narrow shafts that extend from the king's and queen's chambers. Some align with specific stars or constellations, suggesting a deliberate astronomical function rather than a purely architectural one. The precision and intent behind these features indicate a level of planning that seems almost impossible for a society presumed to be operating with only primitive tools and rudimentary mathematical knowledge. Beyond the technical marvel, the Great Pyramid also embodies a form of symbolic engineering that merges science with culture. The alignment of the pyramid with cardinal points, the dimensions corresponding to ratios related to pi and the golden ratio, and the astronomical orientation suggest that the builders were integrating knowledge of the cosmos into their architecture. Whether these were deliberate calculations or intuitive applications is still debated, but the result is a structure that reflects both engineering mastery and cultural sophistication. It raises the possibility that the pyramid served multiple purposes simultaneously, as a tomb, as an observatory, and perhaps even as a machine designed to interact with the natural world in ways we are only beginning to speculate. The logistics of construction add further layers of intrigue. Moving millions of massive stones from quarries, transporting them across considerable distances, and then placing them with such precision presents a challenge that modern engineers find difficult even with contemporary machinery. Traditional explanations, using ramps, levers, and large labor forces, often fall short of explaining the scale, speed, and accuracy evident in the finished pyramid. Some researchers have suggested the use of counterweights, sophisticated pulley systems, or even water-based transport methods, but definitive evidence remains elusive. What is clear is that the builders possessed not only physical strength and coordination but also detailed planning, a deep understanding of materials, and perhaps even innovative technologies that have since been lost. The question of time is also critical. Conventional estimates suggest the Great Pyramid was constructed over approximately 20 years, which, given the scale of the project, would have required the placement of several thousand stones per year. This level of efficiency seems improbable if relying solely on simple tools and manual labor. The precision of each block, the smoothness of the surfaces, and the exactness of the fit suggest that the builders did not merely assemble stones, they engineered them, pre-planned each placement, and executed the plan with remarkable consistency. The process was not haphazard but highly methodical, almost industrial in its precision, challenging assumptions about the capabilities of the society that undertook it. The construction techniques themselves hint at knowledge that extends beyond simple engineering. The Tura limestone casing, polished to a mirror-like finish, would have reflected sunlight across the desert, creating a radiant beacon visible for miles. Such a feature required not only aesthetic vision but also an understanding of materials, light, and surface properties. The accuracy of the internal chambers, the smoothness of the walls, and the alignment of passages indicate careful measurement and a command of geometric principles that rival, and in some cases exceed, modern standards. This suggests a deliberate fusion of practical engineering, aesthetic design, and possibly even spiritual or symbolic intent. Equally remarkable is the durability of the pyramid. Despite millennia of erosion, earthquakes, and human interference, it remains largely intact, a testament to both the ingenuity of its design and the quality of its construction. Modern buildings, engineered with steel and concrete, rarely achieve such longevity without intensive maintenance. The Great Pyramid, however, has endured with minimal intervention, highlighting not only the precision but also the foresight and understanding of natural forces possessed by its builders. They designed a structure capable of surviving centuries, factoring in weight distribution, material behavior, and environmental conditions in ways that continue to impress and perplex engineers today. The Great Pyramid also raises questions about the transfer of knowledge. How did the builders develop such expertise without apparent predecessors or contemporaneous texts detailing their methods? The absence of detailed construction records leaves researchers with only the physical evidence itself to interpret. Yet that evidence alone is compelling. The precision, alignment, and scale suggest a systematic approach, implying education, apprenticeship, and perhaps even institutional knowledge dedicated to mastering construction techniques. The pyramid may have been the culmination of centuries, or even generations, of accumulated expertise, an embodiment of knowledge that was both practical and symbolic. Finally, the possibility that the Great Pyramid served multiple functions beyond a tomb cannot be ignored. Some theorists propose that it could have acted as a resonant chamber, an astronomical observatory, or even a device to harness natural energies in ways lost to history. While such ideas remain speculative, the complexity and precision of the structure leave open the possibility that the pyramid's purpose was far more sophisticated than a simple burial monument. Its design suggests an understanding of science, mathematics, and engineering that challenges our assumptions about ancient civilizations. Standing before the Great Pyramid today, it is impossible not to feel a mixture of awe, wonder, and profound curiosity. Every block, angle, and alignment speaks to a level of intelligence and capability that seems almost alien by the standards of its era. The structure challenges conventional timelines, disrupts assumptions about technological progress, and invites us to consider the possibility that ancient humanity may have reached heights of engineering sophistication that we are only now beginning to comprehend. The Great Pyramid is not merely a relic of the past, it is a testament to what is possible when human ingenuity, observation, and skill converge, and it remains one of the most compelling mysteries of the ancient world. It is within this tension between the known and the seemingly impossible that the true fascination of the Great Pyramid emerges. Every visitor, every researcher, every engineer who studies it is confronted with the realization that we may not fully understand the methods, intentions, or capabilities of the people who built it. The pyramid challenges us not just to marvel at its scale and precision, but to reconsider what humanity, long ago, may have truly been capable of achieving. It serves as a reminder that the past is not always what it seems, and that the extraordinary achievements of ancient engineers may still hold secrets waiting to be discovered. The stonework of ancient civilizations continues to astonish experts because of its level of precision, particularly in the way massive blocks were cut, shaped, and fitted together. Across the world, from Egypt to South America, from India to the Mediterranean, examples of stone craftsmanship demonstrate a mastery that seems impossible given the tools and technologies available at the time. In Egypt, granite boxes, obelisks, and temple foundations exhibit perfectly smooth surfaces and precise right angles, often created from stones so hard that even today they challenge modern cutting tools. The surfaces are not merely flat, they are flawlessly planar, often polished to a finish that would require modern abrasives to replicate. Such precision raises immediate questions: how did ancient craftsmen achieve it, and why have the techniques they used been lost to history? Experiments attempting to replicate these cuts with historically plausible tools reveal just how extraordinary the original workmanship truly was. Using copper chisels, stone hammers, and abrasive sand, researchers can produce rough approximations of the shapes, but achieving the smoothness, the uniformity of angles, and the perfection of fit found in ancient structures remains elusive. Even when labor-intensive methods are employed, the results fall short. It is not merely a question of effort, it is a question of knowledge. Ancient artisans appear to have understood how to manipulate the properties of stone, controlling fractures, stress points, and natural weaknesses with a level of precision that borders on the mechanical. Each block was not just shaped, it was engineered. In Peru, the polygonal masonry of Inca walls presents an even more confounding puzzle. Massive blocks, some weighing over 200 tons, are carved into complex, interlocking shapes that resist earthquakes. The precision with which the stones fit together is so fine that a knife blade cannot pass between them. Unlike Egyptian rectangular blocks, the stones here are irregular, yet their placement demonstrates an understanding of structural mechanics that allows them to flex slightly during seismic events without collapsing. Modern engineers marvel at this, noting that contemporary techniques for earthquake-resistant construction still strive to achieve similar flexibility without sacrificing stability. The Inca may have intuitively understood principles of stress distribution and material behavior that remain highly advanced even today. The ability to achieve such precision without metal saws, power tools, or formalized engineering manuals suggests an alternative approach to technology, one based on intimate observation, experimentation, and hands-on mastery. It implies that ancient builders spent years, perhaps generations, perfecting methods for shaping and fitting stone, passing knowledge orally or through apprenticeship systems. In some cases, they may have used techniques that are now forgotten, involving materials, chemical processes, or mechanical methods that we have yet to rediscover. The result is a type of craftsmanship that defies simple explanation, blending art, science, and engineering in ways modern humans can only approximate with great difficulty. Another remarkable feature is the alignment and uniformity of these cuts. In Egyptian temples and tombs, angles are precise, walls are perfectly vertical, and stone blocks are level across surfaces that span tens of meters. Maintaining such accuracy over large distances requires a sophisticated understanding of geometry and measurement, particularly when tools such as plumb bobs, sightlines, or leveling instruments are rudimentary at best. The fact that ancient builders consistently achieved such results suggests that they had methods for verifying, adjusting, and controlling their work with incredible care. Mistakes were not common, they were minimized or prevented entirely through disciplined processes that remain largely mysterious. Beyond the technical achievements, the aesthetic qualities of the stonework are equally impressive. Surfaces are polished and finished in ways that indicate an awareness of appearance as well as function. In temples, shrines, and ceremonial sites, the stones are often arranged to catch light, create shadow, or reflect the surrounding environment in subtle ways. This suggests that ancient builders were not solely focused on durability or stability, they also sought to communicate status, spirituality, or cosmic significance through their engineering. Every line, every angle, every polished surface may have held meaning beyond the purely structural, merging technical skill with symbolic intention. The question of tools and methods remains central. How did ancient builders manipulate granite, basalt, or other hard stones without steel tools capable of cutting them cleanly? Some theories propose the use of abrasives, pounding stones, or softer metals, but the results of modern experiments indicate that these methods are insufficient to explain the level of precision achieved. Others speculate about lost techniques, perhaps chemical softening of stone, vibration-assisted shaping, or unknown mechanical devices. Whatever the method, it is clear that ancient stoneworkers had capabilities that surpass what conventional histories allow, demonstrating a form of engineering knowledge that appears sophisticated, deliberate, and repeatable. The precision of stonework also points to advanced planning. Each block had to be carefully measured, cut, and positioned to ensure that it fit seamlessly with its neighbors. In cases like the Great Pyramid or Inca walls, the tolerances are so tight that minor miscalculations would have caused structural instability. This implies not only skill in stone shaping but also the ability to visualize complex three-dimensional assemblies, understand the interaction of forces, and anticipate how the structure would behave over centuries. Such foresight challenges assumptions about the cognitive and technical abilities of ancient societies. Furthermore, the recurrence of these techniques across continents is striking. From the finely cut stones of Egypt to the interlocking polygons of Peru, to precisely fitted megaliths in Europe and Asia, similar levels of precision appear in cultures separated by vast distances and time periods. While some suggest coincidence, the repeated appearance of such sophisticated stonework implies a form of shared knowledge, common methodology, or independent discovery that consistently pushes the boundaries of what was considered possible. The parallel mastery observed across different civilizations remains one of the most compelling mysteries of ancient engineering. The durability of these structures is another testament to the skill of ancient stoneworkers. Many of the stones used in temples, tombs, and fortifications remain intact after thousands of years, resisting erosion, earthquakes, and human interference. In some cases, the methods of placement and interlocking have allowed walls to survive natural disasters that would have destroyed less carefully constructed buildings. The combination of precision, material understanding, and long-term planning indicates that these civilizations possessed an engineering sensibility that considered both the immediate construction and the survival of the structure over millennia. Ultimately, the stonework of the ancient world challenges modern assumptions on multiple levels. It is precise, durable, aesthetically sophisticated, and technically advanced in ways that are difficult to reconcile with the tools, materials, and documented knowledge of the time. Replicating even a fraction of this work today is a formidable challenge, highlighting the extraordinary capabilities of ancient craftsmen. The craftsmanship is not merely functional, it embodies a comprehensive understanding of geometry, materials, and structural behavior, suggesting a deliberate and systematic approach to engineering that modern humans often struggle to match. As we study these stones, we are forced to reconsider the nature of ancient knowledge. Were these techniques the result of centuries of careful observation, apprenticeship, and refinement? Did ancient builders have access to lost methods or technologies that allowed them to achieve such perfection? Or did they rely on a combination of intuition, trial and error, and experiential understanding that we underestimate? Whatever the explanation, one thing is clear: the precision of ancient stonework is not a fluke or accident. It is evidence of skill, intelligence, and knowledge that challenges our assumptions about the capabilities of human societies in the distant past. Every perfectly cut block, every flawlessly fitted wall, and every smooth, angled surface stands as a testament to human ingenuity. Yet it is also a reminder of the limits of our understanding, a call to investigate further, and a challenge to reconcile the marvels of the ancient world with the stories we have been told about the progression of technology. The mystery of ancient stonework is not simply about the physical stones themselves, it is about the minds that shaped them, the knowledge they wielded, and the ingenuity that allowed them to achieve what, even today, seems almost impossible. Ancient structures are often celebrated for their size, precision, and durability, but there is another layer of sophistication that is frequently overlooked: their use of sound. Across the globe, archaeological sites reveal evidence that ancient builders may have understood the power of acoustics and deliberately incorporated it into the design of temples, chambers, and sacred spaces. This is not merely a matter of accidental echoes or incidental resonance. In many cases, the manipulation of sound appears intentional, carefully engineered to produce specific effects on those who enter, hear, or perform rituals within these spaces. The implications are profound, suggesting that ancient civilizations explored not just the physical world but the sensory, psychological, and even spiritual dimensions of human experience. Consider the hypogeum of Halsaflini in Malta, an underground complex carved entirely from limestone. Its chambers are structured in such a way that a human voice, even at a whisper, can resonate throughout the underground halls. Frequencies between 110 and 130 Hz produce a response that seems to vibrate within the human body, creating an experience that is both physical and emotional. Visitors today report sensations of unease, altered perception, or even a sense of transcendence when these resonances occur. The builders, working thousands of years ago, had no access to microphones, sound meters, or acoustic modeling software. Yet they manipulated space to create effects that modern architects and sound engineers would find difficult to replicate. Similarly, in Egypt, the so-called resonance chambers within temples and pyramids exhibit properties that amplify certain frequencies while dampening others. Some of these chambers are remarkably precise in their dimensions and orientation, which affects how sound waves propagate within them. The result is a space where chanting, music, or spoken words are transformed, their resonance seemingly magnified, sustained, or focused. Scholars debate whether these effects were intentional, but the consistency across different sites and periods suggests deliberate planning. It is as if the ancient builders understood the interaction between space, material, and vibration in ways that go far beyond what we would expect from societies considered primitive by conventional standards. The integration of sound into architecture is not limited to underground structures. Above ground, temples and ceremonial complexes often show patterns that influence acoustics. Long corridors, precisely spaced columns, and dome-like ceilings can produce harmonic resonance, echo effects, and directional amplification. In some cases, these features coincide with areas of ritual or ceremonial importance, suggesting that the manipulation of sound was intertwined with cultural, religious, or psychological objectives. Ancient engineers were not merely creating functional spaces, they were crafting experiences, using architecture to guide perception, emotion, and even states of consciousness. In Peru, the Inca Temple of the Sun at Machu Picchu exhibits an extraordinary sensitivity to sound. Its stone walls, terraces, and plazas are arranged in a way that certain vocalizations or instruments can be heard clearly across long distances, even in areas where visual contact is obstructed. Some researchers propose that this facilitated communication during rituals or coordinated activities, while others suggest it may have been intended to enhance spiritual experiences. Whatever the purpose, the acoustic design demonstrates an understanding of wave behavior, reflection, and amplification that suggests empirical knowledge gained through observation and experimentation over generations. The question arises, how did ancient builders acquire this knowledge? Unlike stone cutting or construction, the manipulation of sound is less tangible and harder to codify. There is little in the historical record to describe intentional acoustic design, and yet the physical evidence speaks for itself. It suggests that these civilizations engaged in systematic experimentation, discovering through trial and observation how certain shapes, materials, and configurations influence auditory experiences. This knowledge may have been considered sacred or secret, passed orally or embedded within ritual practices, which could explain why it has largely disappeared from historical texts. The effects of these acoustic spaces extend beyond the technical. Sound has a profound impact on human physiology and psychology, influencing heart rate, breathing, and perception. In carefully designed chambers, frequencies can induce relaxation, tension, or heightened awareness, altering the subjective experience of participants. For ancient societies, this would have been a powerful tool in ritual, meditation, and communal gatherings. The architecture itself becomes an instrument, capable of shaping consciousness without the need for external devices or modern technology. This represents a sophisticated integration of sensory experience with social, cultural, and spiritual life, an approach that modern architecture rarely achieves. Moreover, the deliberate use of acoustics challenges the notion that ancient engineering was solely functional. It demonstrates a holistic understanding of environment, material, and human perception. Builders were not merely solving structural problems, they were considering how spaces would be experienced, how sound would travel, and how it could be harnessed to achieve desired effects. In this sense, ancient architecture was multidimensional, blending engineering, physics, psychology, and artistry in ways that modern disciplines often separate. Evidence for acoustic engineering also appears in ancient theaters, amphitheaters, and ceremonial platforms. The Greeks and Romans are famous for their theaters, designed to carry sound to thousands of spectators. Yet similar principles can be observed much earlier in non-Western contexts. Certain stone circles, ceremonial mounds, and temple platforms are positioned and shaped to optimize sound propagation across open spaces. These designs suggest that ancient builders were attentive not only to the material and structural integrity of their constructions but also to the invisible, ephemeral medium of sound itself. This integration of sound into architecture raises profound questions about the sophistication of ancient knowledge. It suggests that civilizations long before the modern era had a practical understanding of principles that we now describe in terms of physics and acoustics. They may have discovered, through careful observation and empirical experimentation, the relationships between shape, material, and vibration. Such knowledge would have required not only intelligence but a culture that valued and transmitted these discoveries across generations. The psychological impact of these acoustic spaces cannot be overstated. Modern visitors to these sites often describe experiences of awe, unease, or transcendence, sensations that hint at deliberate manipulation by the builders. Whether these effects were intended to inspire devotion, convey power, or facilitate altered states of consciousness, they reveal a level of sophistication that extends beyond construction into the realm of human experience itself. Ancient engineers were not only shaping stone, they were shaping perception. Finally, the presence of acoustic engineering in disparate regions suggests that this knowledge may have been more widespread than previously acknowledged. From Malta to Egypt, Peru to India, we find evidence of deliberate attention to sound, integrated with architecture in ways that enhance ritual, ceremony, and human experience. The consistency of these practices across cultures and continents challenges assumptions about technological and intellectual isolation. It raises the possibility that knowledge of acoustics, like other forms of advanced engineering, may have been shared, transmitted, or independently discovered in ways that historians are only beginning to appreciate. In examining the acoustic design of ancient structures, we encounter a convergence of science, art, and spirituality. These civilizations understood that architecture could do more than shelter or endure, they realized it could influence perception, emotion, and consciousness itself. The manipulation of sound, intentionally embedded in stone and space, reflects a mastery of principles that we now describe through physics and engineering. It is a subtle, powerful testament to the ingenuity of the past, one that compels us to reconsider not only the capabilities of ancient builders but also the depth and scope of human knowledge long before the modern era. Through these examples, it becomes clear that ancient engineering was multidimensional. It was not merely about moving massive stones or achieving visual symmetry, it was about creating experiences that engaged the senses, the mind, and the spirit. Sound was as much a tool of design as geometry or material choice, demonstrating that these civilizations were capable of manipulating invisible forces with intention and sophistication. In this, we see a level of understanding that challenges our assumptions, inviting us to explore the past not as a primitive precursor to modernity, but as a repository of knowledge, insight, and innovation that continues to astonish and inspire. The more we study these sites, the more it becomes evident that acoustics was not an afterthought but an integral component of ancient design. From subterranean chambers to open-air plazas, the deliberate shaping of sound reveals an advanced grasp of physics, perception, and human psychology. It reminds us that ancient civilizations were not merely builders, they were architects of experience, engineers of sensation, and masters of dimensions that modern scholars are only beginning to measure. The resonance of their knowledge, like the vibrations in their chambers, continues to echo through time, inviting us to listen, observe, and reconsider the extraordinary capabilities of the past. Across the vast plains of Anatolia, hidden beneath layers of earth that have preserved them for millennia, lie the remnants of one of humanity's oldest known temples, Göbekli Tepe. Carved stone pillars, some standing over 20 feet tall and weighing multiple tons, rise from the ground in circular arrangements that predate Stonehenge by some 6,000 years. These structures, painstakingly carved with reliefs of animals, symbols, and abstract shapes, challenge the conventional narrative of human history. At a time when humanity was supposedly still engaged in simple hunter-gatherer lifestyles, these people were undertaking monumental construction projects with a level of planning, coordination, and craftsmanship that seems astonishingly advanced. The mere existence of Göbekli Tepe forces us to reconsider what humans were capable of before the dawn of settled civilization. The complexity of the site is staggering. Each pillar appears carefully positioned within the circular enclosures, often paired with another, forming symmetrical arrangements that suggest deliberate geometric planning. The carvings on the pillars are not superficial, they are deep, precise, and in some cases intricately detailed, representing animals that would have been familiar to the builders. The scale of the work implies an understanding of both stone properties and leverage, as some pillars weigh several tons. Transporting and erecting these monolithic stones without metal tools, wheels, or draft animals requires ingenuity that seems almost inconceivable. Yet the structures stand today as silent testimony to the skill, organization, and vision of these ancient builders. One of the most remarkable aspects of Göbekli Tepe is the apparent coordination of effort required to construct it. Carving, transporting, and erecting massive stone pillars is no trivial task. It would have required a sizable workforce, organized into specialized groups with defined roles and responsibilities. Someone had to plan the layout, others to carve and shape the stones, and still others to move and raise them into position. This level of coordination suggests social structures far more complex than we usually associate with hunter-gatherer societies. It implies leadership, communication, and perhaps even an institutionalized knowledge system to ensure that the project was carried out efficiently and accurately. The carvings themselves offer insight into the knowledge and observation skills of the builders. Animals such as lions, snakes, boars, and birds are depicted with a realism that suggests careful study and familiarity with anatomy and behavior. Some of the reliefs appear symbolic, potentially representing cosmological or spiritual concepts. Whether the carvings are purely decorative, ceremonial, or imbued with deeper meaning remains a subject of scholarly debate, but their sophistication underscores the intellectual and artistic capabilities of the society that produced them. This was not random or primitive artwork, it was deliberate, expressive, and technically accomplished. Göbekli Tepe also presents a puzzle in terms of its age. Radiocarbon dating suggests the site was constructed around 9600 BCE, a time when agriculture had not yet become widespread and humans were still largely nomadic. Conventional historical narratives posit that monumental architecture emerges only after settled societies develop, with surplus food, labor specialization, and stable governance enabling large-scale projects. Göbekli Tepe contradicts this assumption. It suggests that the desire to build complex, meaningful structures may have preceded the development of agriculture, possibly even motivating humans to settle and cultivate the land. This flips the traditional timeline of civilization on its head, implying that social and spiritual motivations could drive technological and organizational advances rather than follow them. Another layer of mystery lies in the sheer precision of construction. The pillars are not merely erected haphazardly, they are placed in patterns that suggest careful measurement, alignment, and perhaps an understanding of geometric principles. Some researchers have noted alignments with celestial phenomena, implying a rudimentary knowledge of astronomy. Even if the alignments were approximate, the repeated patterns and consistent design across enclosures indicate planning and forethought. The builders were not working by chance, they were executing a vision, a blueprint that guided their hands and coordinated the work of many. The site also raises questions about lost knowledge. How did these people learn to cut, transport, and erect such massive stones without the technologies we consider essential? What methods allowed them to manipulate rocks weighing several tons with such apparent ease? No written records survive, leaving us to piece together their techniques from the stones themselves. The answers may never be fully known, yet the physical evidence points to a level of skill and understanding that surpasses what conventional assumptions would predict for this era. Each standing pillar is a testament to a body of knowledge that seems to have vanished, leaving behind only the stones as clues to a society whose capabilities were far greater than history has long acknowledged. The implications of Göbekli Tepe extend beyond engineering into the realms of social organization and human cognition. Constructing such a site requires not only physical labor but planning, communication, and shared vision. It suggests that the people who built it had developed complex social structures capable of organizing large groups, distributing tasks, and maintaining cohesion over years or decades. This level of social sophistication challenges the assumption that early humans were simple, survival-focused groups. Instead, it paints a picture of a community capable of long-term planning, collective effort, and abstract thought. Equally intriguing is the question of purpose. Unlike later pyramids or temples associated with known rulers or deities, Göbekli Tepe offers no definitive explanation for why it was built. There are no tombs, no obvious residential structures, no evidence of large-scale agriculture at the site itself. Its function remains enigmatic, a ceremonial center, a place of pilgrimage, or perhaps an observatory for astronomical or spiritual observation. The mystery deepens when considering that the site appears to have been deliberately buried around 8000 BCE, covering the stones with soil in a way that preserved them almost perfectly for future generations. Why would a civilization go to such lengths to construct something monumental only to intentionally conceal it? The act of burial itself hints at ritual, reverence, or a complex cultural practice that we are only beginning to understand. Göbekli Tepe forces historians and archaeologists to confront the limits of conventional thinking. It demonstrates that humans of the distant past were capable of feats that rival, and in some cases surpass, what we might expect from later civilizations. The site challenges assumptions about the relationship between technology, social complexity, and monumental construction. It suggests that human ingenuity, organization, and artistic vision emerged far earlier than previously believed. The apparent sophistication of the builders, combined with the scale and precision of their work, compels a re-evaluation of what is possible in a hunter-gatherer context. In addition, the site highlights the potential for knowledge to be lost or intentionally hidden. Techniques for quarrying, carving, and erecting massive stones, as well as the social and organizational frameworks required, may have disappeared as societies evolved or relocated. Göbekli Tepe serves as a reminder that history is not always a straightforward progression of knowledge and skill. Knowledge can emerge, flourish, and vanish, leaving only traces in stone, memory, or myth. It challenges the assumption that technological and social advancement follows a linear path, suggesting instead a far more complex and irregular trajectory of human development. The broader significance of Göbekli Tepe lies in its ability to expand our understanding of early human capability. It is a testament to the power of vision, collaboration, and technical skill, demonstrating that even in periods we consider primitive, humans were capable of organizing, executing, and completing monumental projects with sophistication that rivals later civilizations. Each pillar, each carving, each carefully arranged circle speaks to an intelligence and intentionality that is both inspiring and humbling. Ultimately, Göbekli Tepe is more than an archaeological site, it is a challenge to our assumptions about human history. It forces us to consider that monumental architecture, complex social organization, and sophisticated technical skill may have existed long before the rise of cities and kingdoms. It invites us to question the stories we tell about the origins of civilization, to look beyond conventional timelines, and to recognize that the capacity for extraordinary achievement has been part of the human experience for far longer than we have imagined. The silent pillars of Göbekli Tepe continue to stand as a testament to ingenuity, vision, and mystery, urging us to reconsider the boundaries of what humanity was capable of in the distant past. In the highlands of Peru, far above the valleys and rivers, the remnants of ancient civilizations reveal an engineering sophistication that continues to astonish modern scholars. Machu Picchu, often called the "Lost City of the Incas," is not merely a collection of stone ruins, it is a masterclass in planning, architecture, and environmental adaptation. Unlike many ancient sites that are studied primarily for their cultural or religious significance, Machu Picchu stands as a testament to human ingenuity, precision engineering, and harmonious integration with the natural world. The city is perched on a ridge between two peaks, surrounded by precipitous cliffs and traversed by narrow terraces that prevent landslides and erosion, demonstrating a deep understanding of topography and hydrology. The construction of Machu Picchu involved moving massive stones across rugged terrain, shaping them with incredible precision, and assembling them into structures that have withstood centuries of earthquakes, rainfall, and landslides. The stones are cut to fit together without mortar, yet the walls remain stable, flexible, and resilient. This technique, known as ashlar masonry, allowed the Inca to create structures that could withstand seismic activity, an inevitability in the Andean region. Modern engineers have studied these walls and found that the slight irregularities in the stone shapes and the careful interlocking of blocks distribute stress efficiently, absorbing and dispersing the energy of tremors. The Inca achieved this without knowledge of modern engineering formulas, demonstrating an intuitive understanding of forces, materials, and structural behavior. Water management at Machu Picchu adds another layer of complexity to the site. The city was designed with a sophisticated system of canals, fountains, and drainage that channeled rainwater through terraces and into natural channels without causing damage to the structures. This was essential in a region prone to heavy rainfall and potential flooding. The planners accounted not only for the volume of water but also for its flow, pressure, and erosion potential, creating a system that still functions today. Such hydraulic engineering indicates careful observation, planning, and practical experimentation, skills that would have required generations of accumulated knowledge and hands-on expertise. The terraces themselves demonstrate an intricate understanding of agriculture, soil mechanics, and climate adaptation. By carving the mountainside into stepped fields, the Inca created microclimates that supported diverse crops, prevented soil erosion, and stabilized the mountainside. Each terrace required precise leveling, careful drainage, and careful placement of retaining walls. The precision of these terraces is astonishing. They are uniform in height, slope, and depth, optimized for water retention and soil conservation. This reflects not only an agricultural strategy but also an engineering mindset, where form and function are seamlessly integrated to create a sustainable environment. Machu Picchu also exhibits remarkable urban planning. The city is divided into sectors that accommodate residential, ceremonial, agricultural, and administrative purposes. Streets and pathways are laid out with remarkable foresight, following natural contours to minimize disruption while maximizing accessibility. Buildings are aligned with astronomical events, such as solstices and equinoxes, suggesting that the Incas combined practical construction with cosmological knowledge. The precision of this alignment, combined with the spatial organization of the city, indicates advanced surveying techniques and an understanding of geometry and measurement that rivals contemporary methods. Stonework at Machu Picchu is particularly striking in its quality and precision. Massive blocks are shaped to fit together with such exactness that not a single blade can penetrate the seams. Unlike the polygonal masonry of Sacsayhuaman, some blocks at Machu Picchu are rectangular yet polished and angled with extreme accuracy. The builders achieved this with stone hammers and abrasion tools, but the result is indistinguishable in many cases from machine-cut stone. The sheer skill required to produce such uniformity and to erect these stones on uneven terrain, on slopes exceeding 45 degrees in some places, is staggering. The precision extends to corners, angles, and interlocking patterns, revealing a level of craftsmanship that suggests both meticulous planning and advanced tactile knowledge. Transportation and placement of these stones remain an unresolved mystery. Many of the blocks used in Machu Picchu weigh several tons, and yet there is no evidence of wheels, draft animals, or modern machinery. The builders may have employed a combination of levers, ramps, ropes, and human coordination, but the precise methods are unknown. What is undeniable is that the operation required not only strength but also sophisticated logistical planning. Stones had to be quarried, shaped, transported, and positioned with incredible precision, all while working on steep mountainsides and under conditions that would challenge even modern construction crews. The success of this endeavor speaks to the ingenuity, organization, and collective effort of the Inca civilization. Beyond its technical feats, Machu Picchu reveals an extraordinary harmony with the natural environment. Buildings, terraces, and water channels are integrated seamlessly with the surrounding landscape. The placement of temples, residential areas, and agricultural fields considers sun exposure, wind patterns, and the natural contours of the mountains. This environmental sensitivity not only demonstrates aesthetic and practical considerations but also suggests a philosophy that valued balance between human activity and nature. Unlike many modern constructions, which often impose themselves upon the land, Machu Picchu adapts to it, creating a resilient and enduring settlement that reflects a sophisticated understanding of environmental engineering. The ceremonial aspects of the city further highlight the Incas' integration of technical skill with cultural and spiritual life. Structures such as the Temple of the Sun and the Intihuatana stone are aligned with celestial events, indicating precise astronomical knowledge. These alignments were not merely symbolic, they reflect careful observation, measurement, and application of natural cycles in architectural design. The combination of spiritual, practical, and engineering considerations in these constructions underscores the multifaceted expertise of Inca architects, who were able to synthesize disparate forms of knowledge into a cohesive and functional city. The enduring legacy of Machu Picchu challenges assumptions about ancient civilizations' capabilities. The city was abandoned in the 16th century, yet its structures have survived centuries of earthquakes, rain, and erosion. Modern engineers study its walls, terraces, and water systems not just for historical insight but for practical lessons in sustainability, resilience, and urban planning. The durability and elegance of Machu Picchu are a testament to the knowledge and foresight of its builders, highlighting a level of engineering and architectural sophistication that defies expectations for pre-Columbian societies. In addition to its technical marvels, Machu Picchu offers profound insight into the intellectual and cultural achievements of the Inca. The city demonstrates that these ancient people were not only capable of monumental construction but also possessed knowledge of mathematics, astronomy, agriculture, and environmental management. Their work reflects a comprehensive understanding of the interplay between human settlement, natural forces, and celestial patterns. This integration of disciplines reveals a civilization that was advanced, intentional, and highly sophisticated, challenging the notion that pre-modern societies were simple or technologically limited. Ultimately, Machu Picchu stands as a monument to human ingenuity, foresight, and adaptability. Its construction required precise engineering, meticulous planning, and coordination of labor on a massive scale. The city harmonizes functionality, aesthetics, environmental integration, and spiritual significance, creating a settlement that has endured through centuries without losing its structural integrity or cultural resonance. Machu Picchu is not merely an archaeological site, it is a profound demonstration of what ancient humans were capable of achieving when vision, skill, and knowledge converged. Every terrace, every precisely cut stone, every water channel reflects the depth of Inca understanding, revealing a civilization that was far more technologically and intellectually sophisticated than often credited. Machu Picchu challenges us to rethink conventional timelines, to question assumptions about ancient capabilities, and to marvel at the ingenuity of people who, without modern machinery or formalized engineering education, created a city that continues to inspire awe, study, and admiration thousands of years later. The city's presence atop the Andes is a constant reminder that human creativity and intelligence have long been capable of feats that transcend both time and expectation. The enigmatic ruins of Ollantaytambo, perched high in the sacred valley of Peru, offer a striking example of Inca engineering that combines monumental stonework with strategic military foresight and urban planning. Often overshadowed by Machu Picchu, Ollantaytambo stands as one of the most sophisticated settlements of the Inca Empire, featuring terraces, temples, and fortifications built with stones so precisely cut that the joints remain impervious to modern replication. The site is unique in that it appears to have been designed for multiple purposes simultaneously, as a religious center, a defensive stronghold, and a functioning town for its inhabitants. This multifunctional approach reflects a comprehensive understanding of both the physical and social landscapes, blending engineering, strategy, and culture into a coherent whole. One of the most remarkable aspects of Ollantaytambo is the precision of its megalithic stonework. Massive stones, some weighing dozens of tons, are shaped with polygonal cuts and interlocked so tightly that it is nearly impossible to insert even a thin blade between them. Unlike many modern construction projects where precision is achieved using mechanical instruments, the Incas accomplished this with stone hammers and abrasion techniques. The surfaces are smooth, the angles exact, and the interlocking patterns so sophisticated that the walls remain stable centuries later, even in the face of frequent earthquakes. The craftsmanship indicates not just physical skill but a profound understanding of materials, geometry, and structural stability. The terraces at Ollantaytambo are another testament to Inca ingenuity. Carved into the mountainside, these terraces served multiple purposes, including agriculture, erosion control, and structural reinforcement of the steep slopes. Each terrace was engineered to channel water efficiently, prevent landslides, and optimize microclimates for crop cultivation. The placement and dimensions of the terraces reveal careful consideration of sunlight exposure, soil fertility, and the natural topography. By integrating agriculture with structural engineering, the Incas transformed the harsh Andean environment into a sustainable living and working space, demonstrating foresight, resourcefulness, and a holistic approach to construction. Water management at Ollantaytambo was equally sophisticated. Channels, fountains, and drainage systems are integrated seamlessly into the architecture, directing water from mountain springs to agricultural terraces and residential areas. The Incas accounted not only for flow and pressure but also for sediment, seasonal variations, and potential erosion. The result is a hydraulic system that continues to function even today, centuries after its construction. This demonstrates an advanced empirical understanding of hydrology and engineering principles, achieved without modern tools or written formulas. The water systems at Ollantaytambo highlight the Incas' ability to combine functionality, durability, and aesthetic design in a way that few modern engineers could replicate with such elegance. Strategically, Ollantaytambo also served as a fortress. Its elevated location, steep terraces, and fortified walls made it a formidable stronghold against invaders. The layout reflects a keen understanding of defensive architecture. Narrow access points, high vantage positions, and layered terraces allowed defenders to control the flow of attackers effectively. Stones were placed with such precision that the walls could withstand both natural forces and potential siege tactics. The Incas' ability to integrate military strategy with urban and agricultural design demonstrates a comprehensive vision that encompassed not only the physical construction but also the social and strategic needs of the community. The monumental temple complex at Ollantaytambo further emphasizes the technical and cultural sophistication of the Incas. Known as the Temple of the Sun, it features massive stone blocks arranged in a pattern that aligns with solar events. Some blocks weigh upwards of 50 tons and are cut with a level of precision that has left modern scholars puzzled. The alignment of the temple with solstices and other celestial events indicates that the Incas possessed a sophisticated understanding of astronomy, which they integrated seamlessly into their architecture. This combination of spiritual, practical, and astronomical knowledge reflects a civilization that viewed engineering not merely as functional but as a means to connect with cosmology, religion, and social cohesion. Transporting and positioning the massive stones at Ollantaytambo posed challenges that continue to baffle archaeologists and engineers. There is no evidence of wheeled vehicles, large draft animals, or mechanical cranes capable of lifting blocks weighing tens of tons. Yet the Incas managed to quarry, shape, transport, and assemble these stones with astonishing precision on steep mountain slopes. Hypotheses include the use of inclined planes, rollers, ropes, and coordinated labor, but the exact methods remain speculative. The logistical achievement suggests not only physical capability but also meticulous planning, experimentation, and possibly lost techniques that allowed the builders to manipulate these enormous stones effectively. The urban planning at Ollantaytambo demonstrates a remarkable synthesis of form and function. Residential areas, ceremonial spaces, and agricultural terraces are integrated into a single cohesive design that respects both the natural terrain and the social needs of the inhabitants. Streets and stairways follow the contours of the mountainside, while plazas and temples occupy positions that maximize visibility and accessibility. This thoughtful integration suggests that the Incas approached urban planning with an understanding of human behavior, traffic flow, and communal interaction, combining engineering precision with social insight. It is a form of planning that modern urban designers study for lessons in resilience, adaptability, and efficiency. The alignment of structures at Ollantaytambo with astronomical events is particularly compelling. Observations indicate that the Temple of the Sun and other key structures were positioned to mark solstices and equinoxes, demonstrating an awareness of solar patterns and celestial cycles. This knowledge was likely used to regulate agricultural activities, ceremonial calendars, and spiritual observances. The ability to integrate astronomical observation into large-scale construction projects speaks to the Incas' interdisciplinary expertise, merging astronomy, architecture, and engineering in a way that few ancient civilizations achieved with such consistency. In addition to its technical and astronomical accomplishments, Ollantaytambo reveals the Incas' ability to adapt to and manipulate their environment. The terraces, walls, and water systems are designed not only to resist earthquakes and erosion but to work with the natural landscape, maximizing stability and utility while minimizing environmental disruption. This approach reflects a sophisticated understanding of geotechnical principles, hydrodynamics, and sustainable design. The Incas did not impose their structures on the landscape arbitrarily, they observed, measured, and engineered solutions that enhanced the natural environment rather than fighting against it. The durability of Ollantaytambo's construction is remarkable. Centuries after its abandonment, the walls, terraces, and temples remain largely intact, surviving earthquakes, landslides, and centuries of weathering. Modern engineers continue to study the site for insights into seismic-resistant construction, precise stone shaping, and effective water management. The longevity of these structures attests to the meticulous craftsmanship, advanced engineering, and deep empirical knowledge of the builders, whose achievements continue to inspire and challenge contemporary understanding. Ultimately, Ollantaytambo serves as a powerful testament to the ingenuity and sophistication of the Inca civilization. The site demonstrates mastery of stonework, hydraulic engineering, urban planning, astronomical observation, and environmental adaptation, all executed without the benefit of modern tools or formalized mathematical instruction. It highlights a society capable of organizing massive labor forces, coordinating complex construction projects, and integrating functionality, aesthetics, and cultural meaning into their built environment. Ollantaytambo challenges assumptions about the technological and intellectual capabilities of pre-Columbian societies, revealing a civilization that was far more advanced than previously acknowledged. Every terrace, wall, and temple at Ollantaytambo is evidence of a culture that understood materials, forces, and human needs at an extraordinary level. The combination of monumental engineering, strategic planning, and environmental harmony speaks to a civilization that was innovative, adaptive, and profoundly intelligent. The site is not merely an archaeological curiosity, it is a lesson in human potential, demonstrating that with vision, knowledge, and coordinated effort, societies can achieve feats that continue to defy modern replication. Ollantaytambo remains a living testament to the advanced engineering, ingenuity, and enduring legacy of the Inca, challenging our understanding of what was possible in the ancient world. In the high deserts of northern Chile, among the arid plains and jagged mountains, lie the mysterious Nazca lines, vast geoglyphs etched into the earth that have baffled scholars, archaeologists, and engineers for nearly a century. Stretching over 50 miles, these enormous designs depict animals, human figures, geometric patterns, and complex spirals, some measuring hundreds of feet across. Viewed from the ground, the lines are difficult to discern, yet from the air, their full scale and intricate detail emerge in breathtaking clarity. The sheer ambition and precision of these creations pose a question that has perplexed researchers since their discovery. How did a civilization, operating thousands of years ago without modern aerial technology, conceptualize, design, and execute such enormous and exact figures? The Nazca lines are not mere scratches on the desert floor, they are carefully constructed features. The top layer of reddish-brown pebbles was removed to expose the lighter-colored sand beneath, creating high-contrast images that have endured for centuries despite wind, rain, and shifting sands. The creators of these lines understood the properties of the desert soil, exploiting natural contrasts to make their work visible over long distances. Even the simplest geometric figures display astonishing accuracy, with straight lines that extend for miles without the aid of sighting tools, compasses, or surveying instruments as we know them today. The precision is remarkable, suggesting not only practical knowledge but also sophisticated methods for measurement and alignment. Many of the geoglyphs depict animals, spiders, monkeys, hummingbirds, and llamas, rendered in stylized yet recognizable forms. The sheer scale of these images is staggering, some hummingbirds span nearly 300 feet from wingtip to wingtip. Producing figures of this size required an understanding of proportion, scaling, and perspective that exceeds what is typically attributed to pre-Columbian societies. Researchers have speculated that the Nazca people may have employed rudimentary grid systems or used stakes and ropes to maintain accurate proportions. However, no definitive evidence survives to explain the methodology, leaving the execution of these monumental works shrouded in mystery. Equally compelling are the geometric designs, straight lines, trapezoids, spirals, and parallel bars, that crisscross the desert. Some lines extend uninterrupted for over 10 miles, cutting through valleys, hills, and rugged terrain with a precision that seems impossible without advanced surveying techniques. These straight lines and their intersections are not random, many appear to align with astronomical events, such as solstices or the rising and setting of specific stars. This suggests that the creators of the lines had knowledge of celestial cycles and incorporated it into their work, integrating astronomy with art and ritual in a way that implies careful observation, long-term planning, and sophisticated cultural understanding. The purpose of the Nazca lines remains a subject of intense debate. Some scholars propose that they served as religious or ceremonial pathways, designed to be walked in ritual observance or as offerings to deities. Others suggest that they functioned as astronomical calendars, marking the positions of the sun, moon, and stars for agricultural or ceremonial purposes. There are even hypotheses that the lines were created as messages or markers visible from above, perhaps intended for gods or celestial beings. Regardless of the purpose, the scale, precision, and complexity of the lines indicate that their creation required careful coordination, planning, and execution over generations, reflecting a society with advanced organizational and engineering capabilities. The logistics of constructing the Nazca lines are themselves remarkable. To produce straight lines extending for miles, the creators would have had to maintain consistent angles and directions across uneven terrain without modern surveying tools. To scale figures accurately, they likely employed a system for transferring small-scale drawings onto the desert floor using grids or reference points, although the exact method remains unknown. Some researchers have demonstrated that it is theoretically possible to create such figures with rudimentary tools, but the execution observed in the Nazca Desert suggests a level of precision and consistency that is difficult to achieve without systematic planning and practice. One of the most intriguing aspects of the Nazca lines is their durability. The arid climate of the region has helped preserve the geoglyphs for over 1,000 years, but their longevity is also a testament to the careful construction techniques employed. The creators removed the top layer of darker stones without disturbing the underlying soil, ensuring that the lines remained sharply defined. The line's resistance to erosion suggests that the builders had not only an aesthetic or ritual purpose in mind but also a long-term vision, creating works meant to endure across generations. The geoglyphs also raise questions about knowledge transfer and cognitive ability. Conceptualizing a design hundreds of feet across, scaling it accurately, and then executing it on the ground requires advanced spatial reasoning, planning, and coordination. It is evidence that the Nazca people possessed not only technical skill but also abstract thought and collective intelligence. Large teams would have had to work together, following precise measurements and instructions to ensure that the final figures emerged exactly as intended. This level of coordination suggests social organization, knowledge sharing, and perhaps specialized roles or apprenticeships dedicated to the creation of the lines. Astronomical alignment provides yet another layer of mystery. Researchers have identified correlations between certain lines and the positions of celestial bodies, suggesting that the Nazca people observed the skies with remarkable accuracy. These alignments may have served practical purposes, such as determining planting seasons or ceremonial events, but they also imply an integration of natural observation with cultural expression. The geoglyphs, in this sense, functioned as both scientific and spiritual tools, reflecting a society capable of combining empirical knowledge with ritualistic practice in a way that few civilizations have achieved. The Nazca lines challenge conventional assumptions about the capabilities of pre-Columbian civilizations. The complexity, precision, and scale of these geoglyphs indicate advanced planning, technical knowledge, and organizational skill. They reveal a people who were not merely surviving but actively shaping their environment, integrating art, science, and spirituality into monumental works that continue to inspire awe today. The geoglyphs demonstrate a level of engineering sophistication, cultural intentionality, and visionary thinking that modern scholars often underestimate when considering ancient societies. The mystery deepens when considering that the lines are best viewed from above. Without flight, the Nazca could not have fully appreciated their scale, raising questions about perspective and intention. Some scholars argue that the lines were intended for the gods, assuming that divine observers would view the desert from above, while others suggest that small elevated vantage points or temporary scaffolding may have been used. Regardless, the decision to create works whose grandeur is only visible from a higher perspective reflects a conceptual and artistic vision that is highly advanced, blending technical skill with imaginative foresight. The enduring fascination with the Nazca Lines stems not only from their visual impact but from the questions they pose about human ingenuity, knowledge, and ambition. They exemplify a civilization capable of precise, large-scale planning, effective labor coordination, and the integration of astronomical and ritual knowledge into monumental construction. Their existence challenges linear narratives of technological progression, demonstrating that human societies thousands of years ago possessed capacities for abstract thinking, engineering, and artistry that remain extraordinary even by modern standards. Ultimately, the Nazca Lines are more than artistic creations, they are monumental statements of cultural identity, technological skill, and intellectual achievement. Every straight line, geometric pattern, and intricate figure reflects the combined efforts of a society that mastered its environment, understood celestial patterns, and coordinated labor with remarkable precision. The geoglyphs endure as a testament to human ingenuity, inviting us to marvel at the accomplishments of a civilization that achieved extraordinary feats without the tools, instruments, or technology that we often consider necessary for such endeavors. The desert of Nazca continues to guard its secrets, challenging our assumptions and inspiring generations to contemplate the sophistication of the people who etched their visions across the earth so many centuries ago. Across the rugged landscape of southern Turkey, nestled between mountains and rivers, lie the ruins of Mount Nemrut, an extraordinary archaeological site that continues to astonish historians, engineers, and archaeologists alike. Constructed during the 1st century BCE under the reign of King Antiochus I of Commagene, Nemrut is famed for its colossal statues, massive stone terraces, and intricate burial mound, a monument that blends engineering brilliance with spiritual and political symbolism. Standing over 2,100 meters above sea level, the site presents both natural and logistical challenges, yet the ancient builders managed to transport, carve, and arrange enormous stones with a precision that modern engineers would find daunting. The mountain itself becomes both a canvas and a foundation, revealing a civilization that harmonized architecture, symbolism, and the environment in ways that remain strikingly sophisticated. The most immediately striking feature of Mount Nemrut is its colossal statues, which rise to heights of over 8 meters and weigh tens of tons each. Carved from local limestone, these figures depict a mixture of deities, mythological creatures, and King Antiochus himself, blending Hellenistic, Persian, and Armenian influences into a single monumental complex. The sheer size of these statues presents immediate engineering challenges, quarrying the stone, transporting massive blocks up steep mountain paths, and precisely positioning them in alignment with terraces and other architectural elements. Even with modern machinery, moving and erecting stones of this magnitude on such challenging terrain would be an immense undertaking. Yet the ancient builders accomplished this feat using methods that remain largely speculative, showcasing a combination of ingenuity, coordination, and skill that is still difficult to fully comprehend. The terraces of Mount Nemrut further illustrate the sophistication of the site's construction. Large stone blocks were arranged to form broad platforms that support the statues, create ceremonial spaces, and stabilize the mountain slopes. The terraces required careful engineering to prevent landslides and ensure long-term durability, considering the region's seismic activity and exposure to harsh weather conditions. Evidence suggests that the builders meticulously planned the layout, calculating angles, slopes, and placement to distribute weight and maintain stability. The precision and foresight embedded in these terraces demonstrate that the construction of Nemrut was not a series of ad hoc efforts but a highly organized, deliberate project guided by engineering knowledge and aesthetic vision. Transportation of materials presents one of the greatest enigmas of Mount Nemrut. The limestone used for the statues was quarried from nearby sources, but the path from quarry to construction site involves steep inclines, rocky terrain, and narrow mountain trails. The ancients lacked wheeled vehicles capable of handling such weight, and there is no evidence of large draft animals being used in sufficient numbers to manage this task. Hypotheses range from the use of inclined planes, rolling logs, coordinated teams of workers, to levers and ramps constructed specifically for each block. Regardless of the methods employed, the successful positioning of these massive statues and blocks on a mountain summit reflects advanced logistical planning, teamwork, and an understanding of mechanical principles that is remarkable for a civilization operating over 2,000 years ago. Astronomical alignment is another layer of complexity at Nemrut. The terraces and statues are arranged to face the rising and setting sun during solstices and equinoxes, suggesting that the site functioned not only as a burial monument but also as a ceremonial and cosmological observatory. The placement of the statues, combined with the precise orientation of terraces, indicates a knowledge of celestial patterns and the ability to incorporate these observations into large-scale construction. Such integration of astronomy with architecture points to an interdisciplinary understanding that combines empirical observation, symbolic intent, and technical execution, a synthesis rarely seen even in later monumental constructions. The artistic and symbolic aspects of Nemrut are inseparable from its engineering achievements. The colossal statues, meticulously carved reliefs, and carefully designed terraces convey not only religious and political messages but also demonstrate mastery of scale, proportion, and spatial arrangement. The faces of the statues were originally painted, and the alignment of the site with natural light and the surrounding landscape suggests an intentional interplay between architecture, art, and environment. The builders were not merely concerned with stability or size, they sought to create an immersive, awe-inspiring experience that conveyed power, divinity, and cosmic harmony. This integration of aesthetics and engineering reflects a civilization that valued knowledge, symbolism, and technical skill equally, merging practical construction with cultural and spiritual significance. The burial mound atop Nemrut adds yet another dimension to the site's complexity. Composed of millions of tons of loose stones, it conceals the king's tomb and serves as a monumental marker visible for miles. Constructing a mound of this size on a mountain summit required careful planning to ensure stability, weight distribution, and resistance to erosion over centuries. The logistics of moving and positioning such a vast quantity of stones, while simultaneously maintaining precise terraces and pathways, highlight the extraordinary organizational capabilities of the Commagene builders. The mound itself is both functional and symbolic, providing a final resting place for the king while asserting his presence across the landscape long after death. Seismic considerations at Mount Nemrut further illustrate the builders' engineering prowess. The region is prone to earthquakes, yet many of the terraces, statues, and retaining walls have endured for over 2 millennia. The slightly inclined placement of stones, interlocking construction techniques, and distribution of mass all suggest that the builders intuitively understood how to design for seismic resilience. Such foresight indicates empirical observation and experimentation, revealing knowledge of natural forces and material behavior that modern engineers study for lessons in long-term structural stability. Nemrut's survival through centuries of earthquakes underscores the sophistication of its design and the meticulous skill of its creators. Logistics and labor organization at Nemrut were likely monumental in scope. Constructing terraces, carving and erecting statues, transporting stones, and creating the burial mound would have required a large, coordinated workforce operating over many years. This implies not only technical knowledge but also social organization, leadership, and project management. Tasks would have been divided among specialized teams, each responsible for quarrying, carving, transport, or placement, all operating under a unified plan to achieve a cohesive monumental complex. The efficiency and coordination required for such an endeavor reflect an advanced level of societal complexity, challenging assumptions about ancient civilizations' capacity for large-scale projects. The enduring grandeur of Nemrut invites reflection on the intersection of engineering, artistry, and cultural ambition. Every statue, terrace, and stone block embodies a synthesis of technical skill, aesthetic judgment, and spiritual intent. The builders were capable not only of manipulating massive stones with precision but of integrating their work with the landscape, celestial cycles, and symbolic meanings. The result is a site that communicates power, reverence, and cosmic alignment across millennia, preserving the vision of a civilization that understood how to merge practical engineering with enduring artistic and cultural expression. Ultimately, Mount Nemrut serves as a profound testament to the sophistication of ancient civilizations. The combination of colossal stonework, precise alignment, astronomical integration, and structural durability reveals a culture that possessed advanced engineering knowledge, organizational capacity, and visionary ambition. The site challenges contemporary assumptions about technological limits in the ancient world, demonstrating that human ingenuity, coordination, and skill have been capable of extraordinary feats for millennia. Mount Nemrut is not merely an archaeological wonder, it is a monument to the enduring capabilities of human intellect, creativity, and engineering mastery, compelling us to reconsider the scope and depth of knowledge achieved by civilizations long before the modern era. The site continues to inspire scholars and visitors alike, encouraging both admiration and inquiry. Each terrace, statue, and stone block is evidence of a civilization capable of harmonizing scale, precision, and aesthetic intent. Nemrut demonstrates that monumental construction is not solely a measure of physical strength but of vision, planning, and the application of complex knowledge across multiple disciplines. It is a site that transcends time, offering insight into human potential, ingenuity, and the enduring quest to leave a mark on the world that resonates with both the earthly and the celestial. The achievements at Mount Nemrut continue to resonate, challenging us to understand and appreciate the extraordinary capabilities of our ancestors. In the remote highlands of Peru, overlooking the Urubamba River, lies Sacsayhuaman, an ancient fortress and ceremonial complex whose scale, precision, and engineering continue to defy modern understanding. Built by the Inca civilization, Sacsayhuaman is renowned for its massive stone walls, composed of irregularly shaped boulders, some weighing over 200 tons, fitted together with extraordinary precision. Unlike typical masonry, the stones interlock so seamlessly that not even a knife blade can pass between them. This site challenges conventional assumptions about pre-Columbian engineering, offering evidence that the Inca possessed advanced techniques for quarrying, shaping, transporting, and assembling megalithic stones in a way that remains mysterious to this day. The layout of Sacsayhuaman is both strategic and symbolic. Positioned on a hill overlooking Cusco, the Inca capital, the fortress provided a defensive advantage, commanding panoramic views of the surrounding valleys and mountains. Its zigzagging walls, some 3 meters thick and over 6 meters high, form a series of terraces that could withstand both human assault and natural events such as earthquakes. The precision of the stone placement ensures stability, with irregular polygons interlocking to distribute stress evenly across the structure. Engineers today marvel at how the Inca achieved such stability without mortar, relying solely on the shapes of the stones and the skillful alignment of each block. Transportation and placement of these massive stones remain one of the greatest enigmas of Sacsayhuaman. Many of the stones were quarried miles away from the site, in some cases weighing more than 100 tons. There is no evidence of wheels, large animals capable of carrying such weight, or modern lifting devices. Theories suggest that the Inca used a combination of ramps, levers, rolling logs, and coordinated labor to maneuver the stones into place. Some stones appear to have been adjusted on-site with incredible accuracy, rotated and tilted to achieve perfect interlocking with neighboring blocks. The level of coordination, planning, and manpower required for this undertaking is staggering, demonstrating a society with remarkable organizational and engineering capabilities. The precision of Sacsayhuaman's stonework is particularly striking. Each block is unique, shaped to fit its neighbors in an irregular, almost puzzle-like configuration. The stones are angled and contoured to resist shifting under seismic forces, a technique that has allowed the walls to endure centuries of earthquakes that have devastated other structures in the region. Modern simulations show that these irregular interlocking patterns dissipate seismic energy effectively, an intuitive understanding of material behavior that predates formal structural engineering by millennia. The ingenuity lies not only in the size of the stones but in their exact placement, revealing a sophisticated grasp of mechanics and natural forces. Beyond engineering, Sacsayhuaman also held ceremonial significance. Archaeological evidence indicates that the site was used for religious rituals, military parades, and gatherings that reinforced the political and spiritual authority of the Inca rulers. Its construction likely required significant labor contributions from surrounding communities, suggesting a system of organized workforce mobilization and a social hierarchy capable of executing complex, long-term projects. This intertwining of engineering, social organization, and ceremonial function reflects a civilization that integrated technical skill with cultural, religious, and political objectives seamlessly. Water management and environmental adaptation were additional considerations in the design of Sacsayhuaman. The terraces and walls were constructed to withstand erosion and heavy rainfall common in the Andean highlands. Channels and drainage paths were incorporated to prevent water accumulation and soil instability. By integrating these environmental adaptations into the architecture, the Inca ensured the long-term stability of the complex, demonstrating a keen understanding of hydrology, soil mechanics, and landscape engineering. The combination of structural durability and environmental foresight reflects a level of planning and empirical knowledge that is remarkable even by modern standards. The scale of Sacsayhuaman is breathtaking. The outer walls span over 500 meters and enclose an area of more than 3 hectares. The sheer size required careful planning of stone quarrying, transport, and assembly, as well as precise coordination of labor over many years. Each layer of stones appears to have been placed with deliberate attention to weight distribution, stability, and aesthetics. The fortress was not only functional as a defensive stronghold but also designed to impress and inspire, communicating the power and sophistication of the Inca civilization. Its monumental scale suggests that the builders were capable of conceptualizing complex three-dimensional forms and executing them with extraordinary precision. The puzzle of Sacsayhuaman extends to the techniques used for cutting and shaping the stones. The surfaces are often smooth, with precise angles and flat planes that fit together without mortar. The stones show evidence of abrasion and pecking, but the level of polish and accuracy suggests methods that we do not fully understand. Some researchers propose that the Inca may have employed specialized tools, techniques for softening or fracturing stone, or even methods lost to time. Regardless of the method, the results demonstrate skill and knowledge that surpasses what we might expect for a pre-industrial society, highlighting an advanced understanding of material properties and manipulation techniques. Sacsayhuaman's irregular polygonal masonry is not only functional but also aesthetically striking. The interlocking stones create patterns that are both visually compelling and structurally effective. This combination of beauty and utility reflects an integrated approach to construction, where form and function are inseparable. The visual complexity of the walls may also have held symbolic or ceremonial significance, further emphasizing the holistic nature of Inca design. By merging engineering, art, and symbolism, Sacsayhuaman demonstrates that the Inca were not merely builders but visionaries capable of creating structures that engage both the intellect and the senses. The enduring stability of Sacsayhuaman offers lessons for modern engineering. Contemporary studies of the site show that its earthquake-resistant design, environmental adaptation, and labor organization remain instructive for modern architects and engineers. The fortress exemplifies how empirical observation, practical experimentation, and careful planning can produce results that withstand time and natural forces. It challenges assumptions about technological linearity, demonstrating that ancient civilizations often achieved levels of sophistication in structural engineering that rival or even surpass what was thought possible for their era. Social and organizational aspects of Sacsayhuaman's construction are equally impressive. Mobilizing labor for quarrying, transporting, and shaping massive stones required hierarchical coordination, logistics, and planning. The Inca likely had systems to organize, feed, and direct thousands of workers, balancing efficiency with precision. This reflects not only technical capability but also sophisticated social structures capable of supporting large-scale projects over extended periods. The construction of Sacsayhuaman therefore reveals a civilization that excelled in both intellectual and organizational domains, blending practical engineering with social and cultural management. Ultimately, Sacsayhuaman is a monument to the ingenuity, skill, and vision of the Inca civilization. Its massive stones, precise interlocking patterns, earthquake-resistant design, and integration with the environment exemplify advanced engineering, while its ceremonial and strategic functions reflect a complex, organized society. The fortress challenges modern assumptions about the technological capabilities of pre-Columbian civilizations and demonstrates that human ingenuity has long been capable of extraordinary feats. Every wall, terrace, and stone block tells a story of planning, craftsmanship, and collective effort, offering a glimpse into the intelligence, foresight, and artistry of a society that continues to inspire awe and admiration centuries later. Sacsayhuaman is not merely an archaeological site, it is a lesson in human potential. It showcases how advanced knowledge of materials, environmental adaptation, structural mechanics, and social organization can converge to produce structures of enduring strength and beauty. The fortress invites us to reconsider the capacities of ancient civilizations, reminding us that innovation, skill, and vision are not confined to modern times but have been central to human achievement for millennia. Its enduring presence atop the Andean hills is both a marvel and a challenge, compelling us to study, learn from, and marvel at the extraordinary accomplishments of our ancestors. Deep in the rugged mountains of southern Peru lies Ollantaytambo, a site that exemplifies the Inca civilization's extraordinary mastery of engineering, urban planning, and stonework, yet continues to defy modern understanding of ancient construction techniques. Often overshadowed by Machu Picchu, Ollantaytambo stands as a living testament to the ingenuity, precision, and organizational skills of the Inca. The fortress-like terraces, colossal stone walls, and ceremonial complexes demonstrate a level of sophistication that challenges conventional timelines of technological development, revealing a civilization capable of feats that modern engineers still struggle to fully replicate or explain. The construction of Ollantaytambo's terraces and walls illustrates the Incas' profound understanding of materials and structural dynamics. Massive stones, some weighing over 50 tons, were quarried, transported, and meticulously fitted into place without the use of mortar, wheels, or large draft animals. Each stone was shaped with remarkable precision to interlock with adjacent stones, creating walls that are both aesthetically impressive and structurally resilient. The polygonal masonry allows the walls to withstand seismic activity, with the interlocking stones absorbing and dispersing energy during earthquakes. This technique demonstrates that the Inca possessed empirical knowledge of stress distribution and material properties long before such concepts were formally understood, relying on observation, experimentation, and hands-on craftsmanship to achieve lasting durability. Water management played a critical role in the design of Ollantaytambo. The terraces, carefully engineered channels, and drainage systems ensured that rainwater could be directed efficiently across agricultural and urban areas without causing erosion or structural damage. This sophisticated hydraulic engineering allowed the Inca to cultivate crops at high altitudes while maintaining the integrity of their construction. Water channels were positioned to prevent sediment accumulation and flooding, suggesting a nuanced understanding of hydrodynamics and environmental adaptation. The ability to harmonize architecture with natural forces underscores a civilization that valued sustainable, long-term solutions over short-term expedients. The transportation and placement of megalithic stones at Ollantaytambo remain among the greatest enigmas of ancient engineering. The stones had to be moved across steep, uneven terrain without modern machinery or lifting equipment. Hypotheses suggest the use of ramps, rollers, ropes, and coordinated labor, but the precision achieved in placing the stones indicates a level of planning and control that goes beyond mere physical effort. The builders had to ensure that each massive block was correctly aligned with the rest of the structure, both horizontally and vertically, while also considering the natural slope of the terrain. This required not only mechanical ingenuity but also sophisticated spatial reasoning and project coordination. Astronomical alignment is another remarkable feature of Ollantaytambo. Key structures, temples, and terraces were oriented to align with solar events, such as solstices and equinoxes, suggesting that the Inca integrated observational astronomy into their construction practices. These alignments were likely used to regulate agricultural cycles, religious ceremonies, and social gatherings, demonstrating an advanced understanding of celestial patterns. The combination of astronomical observation with monumental construction reflects a civilization capable of synthesizing multiple forms of knowledge, engineering, mathematics, and astronomy, into cohesive and functional designs. The fortress-like aspects of Ollantaytambo demonstrate strategic foresight in both defense and urban planning. Its elevated location provides commanding views of surrounding valleys and river approaches, allowing inhabitants to monitor and control movement in the region. The zigzagging terraces, narrow access points, and massive walls would have made direct assault difficult, while simultaneously facilitating rapid movement and defense within the complex. This dual-purpose design, combining military strategy with urban and agricultural functionality, indicates that the Inca approached construction not merely as a technical endeavor but as a multidimensional exercise in planning, control, and adaptation to both natural and human challenges. Artistic and ceremonial considerations were also integral to Ollantaytambo's design. Temples and plazas were constructed to accommodate religious rituals, social gatherings, and astronomical observations. Stone surfaces were often finely finished, terraces were aesthetically proportioned, and spaces were aligned to create a sense of order and grandeur. This blending of form, function, and symbolism underscores the Incas' holistic approach to architecture, where technical skill was inseparable from cultural, spiritual, and social purpose. The builders were not merely constructing functional spaces, they were creating a built environment that communicated power, identity, and cosmological understanding. The durability of Ollantaytambo over centuries highlights the effectiveness of Inca engineering techniques. Despite being exposed to earthquakes, heavy rainfall, and landslides, the terraces, walls, and temples have remained remarkably intact. Modern engineers study these structures to understand their earthquake-resistant qualities, particularly the interlocking polygonal masonry and the precise placement of stones that absorb seismic energy. This resilience demonstrates that the Inca combined empirical observation, trial and error, and practical experience to develop construction methods capable of withstanding natural disasters, reflecting both ingenuity and foresight in their approach to building in challenging environments. Social organization was critical to the successful construction of Ollantaytambo. Mobilizing labor for quarrying, transporting, shaping, and placing massive stones required a hierarchical system capable of coordinating thousands of workers over extended periods. Specialized teams would have been responsible for different tasks, from stone cutting to terrace construction to water management. This level of organization implies a sophisticated understanding of project management, logistics, and human resources, illustrating that the Inca combined technical skill with social engineering to execute monumental projects effectively. The integration of environment, architecture, and agriculture at Ollantaytambo is striking. Terraces not only supported massive structures but also stabilized steep slopes and allowed for efficient cultivation in an otherwise inhospitable landscape. The placement of terraces, channels, and walls indicates that the Inca observed the land carefully and engineered solutions that worked in harmony with natural conditions. By understanding and manipulating the environment in this manner, they were able to create sustainable settlements capable of supporting large populations, reflecting a remarkable combination of ecological awareness, technical proficiency, and social planning. Ollantaytambo also challenges assumptions about the linear progression of technology. The precision of stone cutting, the scale of construction, and the integration of astronomy and hydraulics demonstrate capabilities that rival modern engineering in concept if not in execution. The site forces historians and engineers to reconsider the technological potential of pre-Columbian societies, suggesting that the Inca achieved a level of sophistication often underestimated in traditional narratives of human development. It serves as a reminder that knowledge, skill, and innovation do not always follow a predictable chronological path. Ultimately, Ollantaytambo stands as a testament to the vision, intelligence, and creativity of the Inca civilization. Its massive stones, precise interlocking walls, strategic terraces, and integrated water systems reflect an understanding of materials, forces, and environmental dynamics that continues to impress contemporary observers. The site demonstrates the Incas' ability to blend engineering, aesthetics, astronomy, and social organization into cohesive and enduring structures. Every terrace, wall, and pathway is evidence of meticulous planning, technical skill, and cultural intentionality, illustrating that the achievements of ancient civilizations were often far more advanced than we give them credit for. The site remains a source of inspiration and study, offering lessons in resilience, precision, and holistic design. Ollantaytambo exemplifies how technical knowledge, environmental adaptation, and social coordination can converge to create structures that endure across centuries, combining utility, beauty, and symbolic meaning. It challenges us to rethink the capabilities of ancient civilizations and to recognize the ingenuity and foresight of the Inca, whose monumental achievements continue to astonish and captivate the modern world. Ollantaytambo is more than an archaeological wonder, it is a lasting symbol of human potential, creativity, and a timeless capacity for engineering brilliance that transcends technology, geography, and era. High in the Andes, above the sacred valley of Peru, the ruins of Pisac stand as a testament to the extraordinary architectural, agricultural, and engineering skills of the Inca civilization. While often overshadowed by sites such as Machu Picchu and Ollantaytambo, Pisac offers an equally compelling example of human ingenuity, blending monumental construction with environmental mastery, social organization, and spiritual symbolism. Perched on steep hillsides and overlooking fertile valleys, the site includes terraces, temples, residential complexes, and ceremonial plazas, all integrated with the natural contours of the mountain. The sheer precision and scale of Pisac's construction challenge assumptions about the technological capabilities of pre-Columbian societies, revealing a civilization capable of feats that continue to inspire wonder and intrigue. The agricultural terraces of Pisac are among the most striking features of the site. Carved directly into the mountainside, these terraces serve multiple purposes, preventing soil erosion, stabilizing slopes, and creating microclimates suitable for diverse crops. Each terrace was engineered with precise inclinations to channel water, regulate drainage, and optimize sunlight exposure, reflecting a sophisticated understanding of environmental and agricultural dynamics. The careful alignment of terraces, combined with retaining walls built from finely cut stones, ensured both structural stability and agricultural productivity. The Inca's ability to manipulate the environment so effectively demonstrates a harmonious integration of engineering, ecology, and food production that few modern societies can match in such challenging terrain. Stonework at Pisac reveals an advanced mastery of materials and construction techniques. Massive boulders and carefully cut stones were shaped to fit together without the use of mortar, creating walls that have endured centuries of earthquakes, rainfall, and landslides. The precision of the polygonal masonry allowed for interlocking stones that distributed weight evenly and absorbed seismic energy, ensuring the long-term durability of the structures. Some stones weigh multiple tons, yet they were transported from distant quarries and positioned with remarkable accuracy, reflecting both mechanical ingenuity and organizational skill. The craftsmanship at Pisac exemplifies the Inca's intuitive understanding of structural mechanics and their ability to translate knowledge into monumental architecture. Water management at Pisac is another example of the Inca's engineering sophistication. Channels, aqueducts, and drainage systems were carefully designed to distribute water across terraces, temples, and residential areas, mitigating erosion while supporting agriculture and daily life. The builders accounted for seasonal rainfall variations, water pressure, and sedimentation, creating a hydraulic network that functioned reliably over centuries. This integration of water management into urban planning and agricultural design demonstrates a nuanced comprehension of environmental dynamics, combining practical engineering with foresight and long-term planning. Pisac's hydraulic systems exemplify the Inca's capacity to manipulate natural resources with precision and efficiency. The urban layout of Pisac reflects a sophisticated approach to spatial organization, social hierarchy, and functional zoning. Residential areas, ceremonial complexes, and agricultural terraces are seamlessly integrated, creating a cohesive environment where daily life, governance, and ritual intersect. Streets, stairways, and plazas were strategically placed to facilitate movement, maximize visibility, and maintain the natural flow of the landscape. Temples and ceremonial platforms occupy elevated positions, emphasizing spiritual and political significance, while residential areas are positioned for optimal accessibility and protection. This thoughtful urban planning indicates that the Inca approached construction as an interdisciplinary endeavor, combining engineering, architecture, social organization, and cultural symbolism into a unified design. Transporting the massive stones used at Pisac required extraordinary logistical planning. Some of the stones were quarried several kilometers away and then moved along steep, uneven mountain paths. Without wheels or modern machinery, the Inca relied on ingenuity, coordinated labor, and possibly ramps, levers, and ropes to maneuver the stones into precise positions. The ability to manage such complex operations indicates not only technical knowledge but also sophisticated project management, social coordination, and communication skills. This combination of engineering expertise and organizational capacity exemplifies the Incas' ability to execute monumental projects with both precision and efficiency. PISAC also demonstrates the Incas' integration of astronomical knowledge into construction and ceremonial practice. Several terraces, temples, and platforms are aligned with solstices, equinoxes, and significant celestial events, suggesting that the builders observed and tracked astronomical phenomena to guide agricultural cycles and ritual activities. This integration of astronomy with engineering and urban planning reflects a comprehensive understanding of natural patterns and their application to human life. It reveals a civilization capable of synthesizing observational knowledge, technical skill, and cultural intent into structures that function both practically and symbolically. The ceremonial complexes at PISAC highlight the spiritual and political dimensions of Inca architecture. Temples, plazas, and ritual spaces were strategically positioned to convey authority, reinforce social hierarchy, and facilitate communal gatherings. The design of these spaces reflects an acute awareness of sightlines, orientation, and environmental context, ensuring that rituals were performed in harmony with the surrounding landscape and celestial cycles. These ceremonial elements underscore the Incas' holistic approach to construction, in which technical precision, aesthetic considerations, and symbolic meaning were inseparable. Sustainability and environmental adaptation were central to PISAC's design. The terraces not only provided agricultural productivity but also stabilized the mountainsides, preventing landslides and preserving soil fertility. Water systems were engineered to minimize waste, prevent erosion, and maximize crop yield. By carefully observing and working with natural forces, the Inca created a settlement that was resilient, productive, and harmonious with its environment. This approach reflects a deep understanding of ecological principles, demonstrating that ancient societies were capable of implementing sustainable engineering solutions long before the concept existed in modern discourse. The endurance of PISAC over centuries attests to the efficacy of Inca engineering. Despite exposure to earthquakes, intense rainfall, and natural wear, the terraces, walls, and ceremonial structures remain largely intact. Modern engineers study these features to understand their stability, seismic resistance, and hydrological design. The longevity of the site illustrates the successful application of empirical knowledge, careful planning, and technical skill, offering valuable lessons in resilience and durability that remain relevant today. Social organization was equally critical to the construction and maintenance of PISAC. Coordinating labor for quarrying, shaping, transporting, and placing massive stones required hierarchical management, planning, and communication. Specialized teams likely handled different tasks, while supervisors ensured precision, efficiency, and adherence to design. This level of organization reflects an advanced understanding of project management and the ability to mobilize human resources effectively, demonstrating that the Inca combined technical knowledge with social engineering to accomplish monumental achievements. The combination of monumental construction, hydraulic engineering, astronomical alignment, and urban planning at PISAC underscores the Incas' multidisciplinary expertise. They seamlessly integrated knowledge of materials, mechanics, environment, and celestial observation to create a settlement that functioned efficiently, endured over centuries, and held profound cultural and spiritual significance. Each terrace, wall, and platform reflects the meticulous attention to detail, foresight, and technical mastery that characterized Inca civilization. Ultimately, PISAC is a testament to human ingenuity, resilience, and creativity. Its terraces, walls, and ceremonial complexes demonstrate advanced engineering, precise construction, and thoughtful adaptation to challenging terrain. The site challenges modern assumptions about ancient capabilities, revealing a civilization capable of remarkable technical achievement, environmental harmony, and social coordination. PISAC's enduring presence reminds us that the Inca were not only builders but visionaries, capable of creating structures that continue to inspire awe, study, and admiration centuries later. Every aspect of PISAC, from its massive stone terraces to its intricate water channels, reflects a civilization that understood and harnessed the forces of nature, applied advanced engineering techniques, and organized large-scale labor effectively. The site demonstrates a mastery of materials, spatial planning, and environmental adaptation that continues to fascinate historians, engineers, and archaeologists. Pisac stands as both a functional settlement and a monumental achievement, offering insight into the technical sophistication, cultural depth, and visionary capabilities of the Inca civilization. Its enduring presence atop the Andean hills is a powerful reminder of the heights of human potential, ingenuity, and the timeless pursuit of knowledge and mastery over both landscape and stone. In the remote highlands of Bolivia, near the shores of Lake Titicaca, lies Tiwanaku, one of the most enigmatic and technically advanced civilizations of the ancient Andes. Unlike the Inca, who built during the late pre-Columbian period, Tiwanaku predates them by over a millennium, flourishing between 500 and 1000 CE. The site is renowned for its monumental architecture, precise stone masonry, and sophisticated hydraulic and agricultural systems, all of which reflect a civilization capable of extraordinary engineering feats, organization, and understanding of their environment. Tiwanaku challenges conventional historical timelines and raises profound questions about the technological capabilities of pre-Columbian societies, illustrating a civilization that integrated functionality, spirituality, and aesthetics into enduring constructions. One of the most remarkable aspects of Tiwanaku is the precision of its stonework. The civilization quarried massive blocks of andesite and sandstone, some weighing over 130 tons, and transported them across considerable distances without wheels or draft animals. The stones were shaped with remarkable accuracy, cut to interlock with neighboring blocks so precisely that modern engineers struggle to replicate the technique. The surfaces are often polished, the angles exact, and the joints so tight that not even a thin blade can pass between them. This level of craftsmanship indicates a deep empirical understanding of materials, cutting techniques, and structural stability, achieved through meticulous observation, experimentation, and skill passed down through generations. The Acapana Pyramid, one of Tiwanaku's central structures, exemplifies the ingenuity and technical sophistication of its builders. Constructed as a terraced platform mound, the pyramid measures approximately 200 by 200 meters at its base and rises over 18 meters high. The terraces were engineered not only to support the massive structure but also to channel rainwater efficiently, preventing erosion and structural failure. The precise placement of stones, careful leveling of terraces, and integration of drainage systems reflect a comprehensive understanding of both structural mechanics and environmental forces. Acapana is not merely a ceremonial platform but a masterclass in applied engineering and landscape adaptation. The subterranean channels and hydraulic systems at Tiwanaku reveal a civilization deeply attuned to water management. The site contains intricate networks of canals, drains, and reservoirs that controlled water flow, distributed resources to agricultural terraces, and mitigated flooding during seasonal rains. These systems demonstrate advanced knowledge of hydrodynamics, fluid pressure, and erosion control. Tiwanaku's engineers were able to manipulate the landscape on a large scale, integrating water management seamlessly into urban planning, ceremonial architecture, and agricultural production. The sophistication of these systems indicates careful observation, long-term planning, and an understanding of natural forces that rivals many later civilizations. Transportation and placement of Tiwanaku's massive stones remain among archaeology's greatest mysteries. Stones were quarried from locations sometimes over 60 kilometers away and then transported to the site using methods that remain speculative. Hypotheses include rolling stones on logs, dragging them on sledges over lubricated paths, and coordinated labor using ropes and inclined planes. Despite the lack of wheels or mechanical cranes, the builders achieved precise placement and alignment, often on steep or uneven terrain. This logistical achievement demonstrates exceptional organizational skill, labor management, and mechanical understanding, suggesting a society capable of planning and executing complex construction projects on an impressive scale. The Sun Gate, one of Tiwanaku's most iconic monuments, exemplifies both the artistic sophistication and technical mastery of the civilization. Carved from a single block of andesite, the gate measures over 3 meters in height and features intricate reliefs of deities, celestial figures, and symbolic motifs. The precision of the carvings, the symmetry of the designs, and the sheer scale of the monument indicate mastery of both stone carving and geometric design. Moreover, the Sun Gate is aligned with astronomical events, demonstrating that Tiwanaku's architects incorporated celestial knowledge into their construction practices. This alignment suggests that the civilization combined practical engineering with cosmological observation, creating structures that functioned as both sacred symbols and technical achievements. Agriculture at Tiwanaku was revolutionized by advanced terrace and raised field systems, known as waro-waro. These fields elevated crops above the surrounding water table, improving drainage and reducing frost damage, while channels between them managed water flow to maintain optimal soil moisture. The waro-waro system increased crop yields, stabilized soils, and supported a large population in a high-altitude environment prone to extreme weather. These agricultural innovations required engineering knowledge, careful planning, and a deep understanding of local climatic conditions. Tiwanaku's ability to manipulate both water and soil demonstrates an integrated approach to environmental management that is both practical and sustainable. The spatial organization of Tiwanaku reflects deliberate urban planning that integrated residential, ceremonial, and agricultural areas. Temples, plazas, and pyramids were strategically placed to create sightlines, facilitate movement, and reinforce social hierarchy. Residential zones were constructed to support the daily lives of workers, priests, and rulers, while ceremonial areas provided space for religious rites and communal gatherings. The alignment of key structures with celestial events suggests that astronomical observation was central to city planning, influencing both architecture and ceremonial practice. Tiwanaku's planners exhibited an understanding of how to harmonize functionality, aesthetics, and symbolism within a single urban landscape. The precision of Tiwanaku's construction is particularly evident in the interlocking stonework, which provided both stability and resilience against natural forces. The polygonal stones were cut to fit tightly, distributing weight evenly and reducing the risk of collapse during earthquakes or settling. This technique demonstrates an intuitive understanding of structural dynamics, particularly impressive given the absence of formal engineering knowledge or written technical manuals. The builders relied on empirical observation, iterative practice, and meticulous craftsmanship to achieve remarkable durability, ensuring that many structures remained standing for over a millennium. The integration of spiritual and practical considerations is central to Tiwanaku's architectural philosophy. Temples, pyramids, and ceremonial platforms were designed not only for ritual use but also for environmental and structural efficiency. The alignment of structures with solar and lunar cycles served both symbolic and functional purposes, guiding agricultural activities and ceremonial events. By combining aesthetic, religious, and engineering concerns, Tiwanaku's builders created a built environment that was both functional and meaningful, reflecting a civilization capable of sophisticated interdisciplinary thinking. Social organization played a critical role in the realization of Tiwanaku's monumental projects. Coordinating labor for quarrying, transporting, shaping, and assembling massive stones required hierarchical management, planning, and communication. Specialized teams likely handled different aspects of construction, from carving intricate reliefs to constructing hydraulic channels to raising massive stone blocks into precise positions. This level of coordination reflects not only technical knowledge but also advanced project management, social hierarchy, and the ability to mobilize a workforce effectively, demonstrating that Tiwanaku's achievements were as much social as they were technical. The endurance of Tiwanaku's structures underscores the effectiveness of its construction methods. Despite centuries of exposure to harsh high-altitude weather, seismic activity, and environmental erosion, the site's monumental architecture remains largely intact. Modern engineers and archaeologists study Tiwanaku to understand the durability, stability, and innovative engineering techniques embedded in the site. Its resilience provides lessons in structural design, environmental adaptation, and resource management that continue to inspire contemporary scholars. Ultimately, Tiwanaku stands as a profound testament to the ingenuity, foresight, and technical mastery of its civilization. Its monumental architecture, precise stonework, innovative agricultural systems, and sophisticated water management reveal a society capable of integrating multiple disciplines into a coherent and enduring built environment. Tiwanaku challenges conventional narratives about the technological capabilities of pre-Columbian civilizations, demonstrating that ancient societies were capable of extraordinary engineering, environmental adaptation, and organizational complexity. Every terrace, stone, and platform at Tiwanaku reflects careful planning, empirical knowledge, and cultural intentionality. The city's combination of monumental construction, functional innovation, and symbolic meaning demonstrates a civilization that understood the principles of materials, mechanics, and environmental systems at a remarkable level. Tiwanaku remains an enduring symbol of human ingenuity, reminding us that advanced engineering, architectural precision, and sophisticated urban planning were not inventions of the modern era but achievements that human societies have been capable of for millennia. Its enduring presence on the high plains of Bolivia continues to inspire awe, curiosity, and admiration, compelling us to reconsider the true scope of ancient technological accomplishment. In the stark, windswept expanses of southern Egypt, the ancient city of Abydos rises from the sands as one of the most enigmatic and archaeologically significant sites in human history. Revered as a sacred necropolis, Abydos served as a religious center for over 3 millennia, linking the earliest dynasties to the later pharaonic periods. Beyond its spiritual significance, Abydos contains evidence of extraordinary engineering feats, precise stonework, and architectural sophistication that continue to astonish historians, engineers, and archaeologists. From massive temples to intricate tombs, the site challenges conventional assumptions about ancient Egyptian capabilities, revealing a civilization capable of combining monumental construction, complex logistics, and spiritual symbolism with astonishing precision. The architectural marvels of Abydos reflect a meticulous understanding of design, materials, and structural mechanics. Temples such as the Temple of Seti I feature massive limestone blocks, some weighing tens of tons, meticulously cut, transported, and positioned with extraordinary accuracy. The stones were carved to interlock seamlessly, often with near-perfect joints, creating structures that have withstood millennia of seismic activity, Nile floods, and desert erosion. The precision of the masonry is staggering, surfaces are polished, angles exact, and alignment with celestial phenomena intentional. This level of craftsmanship illustrates a civilization with not only technical skill but also a profound understanding of geometry, load distribution, and material properties, achieved without modern machinery or engineering manuals. The construction logistics at Abydos further highlight the ingenuity of the ancient Egyptians. Quarrying massive limestone and sandstone blocks required advanced knowledge of stone selection, fracture mechanics, and shaping techniques. The transport of these colossal stones over long distances, sometimes hundreds of kilometers from quarries to the construction site, remains a topic of fascination and debate. Scholars hypothesize the use of sledges, lubricated ramps, coordinated labor, and intricate planning to move and position the stones. The precise alignment of massive blocks on uneven terrain demonstrates a mastery of mechanical principles and organizational strategy that rivals, and in some cases exceeds, modern expectations for ancient construction. Abydos also exemplifies the Egyptians' mastery of environmental adaptation and landscape engineering. The temples and tombs were strategically positioned to align with the natural contours of the desert, nearby Nile tributaries, and cardinal directions. Such placement was not purely symbolic, it minimized erosion risks, enhanced structural stability, and facilitated access for ritual and ceremonial purposes. Drainage systems were carefully integrated to manage seasonal rainfall and occasional flooding, reflecting an understanding of hydrology and environmental forces. The ability to harmonize monumental architecture with natural topography demonstrates an interdisciplinary knowledge that combined engineering, environmental science, and spiritual considerations. The spiritual and ceremonial significance of Abydos is inseparable from its architectural achievements. The Temple of Seti I and the Osirian, an enigmatic subterranean structure, illustrate the Egyptians' capacity to merge technical precision with symbolic intent. The Osirian, constructed with enormous granite and sandstone blocks, is aligned with cardinal directions and features chambers, corridors, and subterranean water channels that suggest ritualistic, symbolic, and possibly astronomical functions. The complexity of its construction, combined with the precise orientation and integration with other temple complexes, indicates a civilization capable of combining practical engineering, ceremonial design, and symbolic communication into a unified architectural vision. Astronomical alignment at Abydos reflects an advanced understanding of celestial patterns and their integration into construction. Many temples, tombs, and ceremonial structures were oriented toward specific stars, solstices, or equinoxes, suggesting that the ancient Egyptians used the heavens as a guide for ritual timing, agricultural planning, and spiritual significance. The precision required to achieve these alignments with massive stone structures demonstrates knowledge of mathematics, geometry, and observational astronomy. Aligning structures over large distances, while maintaining consistency in angles and orientation, highlights both the Egyptians' technical capabilities and their ability to plan projects on a monumental scale with foresight and accuracy. The tombs and burial complexes at Abydos reveal another layer of architectural sophistication. Royal and elite tombs were often constructed using massive blocks, precise corridors, and interlocking chambers designed to protect the deceased and convey spiritual meaning. The placement of these tombs required not only structural ingenuity but also symbolic understanding, aligning the deceased with celestial bodies, the Nile, and sacred topographical features. Many tombs incorporate complex corbelling, load distribution, and internal drainage systems, illustrating an intimate knowledge of both engineering and ritual practice. This integration of structural mechanics with spiritual symbolism underscores the Egyptians' holistic approach to construction, where functionality, durability, and meaning were inseparable. Labor organization and social coordination were essential to the realization of Abydos monumental projects. Constructing temples and tombs of this scale required thousands of skilled workers, artisans, and planners operating in a hierarchical system. Coordinating quarrying, transport, stone shaping, and assembly demanded meticulous planning, clear communication, and an understanding of human resource management. Specialized teams likely handled distinct tasks, from carving inscriptions to shaping massive blocks to supervising construction techniques. The scale and precision of Abydos architecture reflect not only technical knowledge but also advanced social and logistical capabilities, demonstrating that the success of monumental construction relied as much on organization and planning as on physical skill. The engineering techniques evident at Abydos remain a source of study and amazement for modern experts. The interlocking stone blocks, massive lintels, and load-bearing walls illustrate principles of stress distribution, seismic resistance, and long-term durability. The Egyptians demonstrated an intuitive understanding of how to manage weight, friction, and tension, creating structures capable of withstanding centuries of natural forces. Even with contemporary tools, replicating the precision, alignment, and scale achieved at Abydos would be a formidable challenge, highlighting the advanced empirical knowledge and craftsmanship of its builders. Material selection and shaping at Abydos also reveal a sophisticated mastery of geology and engineering. The choice of limestone and sandstone for different structural elements was deliberate, balancing ease of carving, durability, and load-bearing capacity. Surfaces were smoothed, angles cut precisely, and massive blocks interlocked to ensure structural integrity without the use of mortar. Techniques such as abrasion, pecking, and polishing were employed with meticulous attention to detail, producing surfaces and joints that remain remarkably precise even after millennia. The combination of careful quarrying, expert shaping, and precise assembly demonstrates a civilization with deep empirical knowledge and remarkable technical skill. Water and environmental management at Abydos further highlight the Egyptians' ingenuity. Channels and drainage systems prevented water accumulation and erosion, while strategic positioning leveraged natural slopes to facilitate runoff and preserve structural integrity. This integration of natural forces into architectural design reflects a civilization capable of observing, understanding, and manipulating the environment for both practical and ceremonial purposes. The engineers at Abydos understood that monumental structures required long-term stability, and they implemented solutions that ensured the endurance of their sacred architecture. Ultimately, Abydos stands as a profound testament to human ingenuity, precision, and foresight. Its temples, tombs, and ceremonial complexes reveal a civilization capable of extraordinary technical and architectural achievement, integrating engineering, astronomy, environmental adaptation, and spiritual symbolism into monumental constructions. Every stone block, precisely cut joint, and carefully aligned temple is evidence of meticulous planning, skill, and cultural intentionality. Abydos challenges modern assumptions about the capabilities of ancient societies, illustrating that the Egyptians possessed advanced knowledge, organization, and craftsmanship that continue to astonish and inspire today. The site's endurance over millennia underscores the effectiveness of the ancient Egyptians' engineering and construction techniques. Despite exposure to earthquakes, Nile floods, and centuries of desert conditions, the temples and tombs of Abydos remain largely intact, demonstrating the success of both their structural and environmental strategies. Abydos not only provides insight into ancient technology but also serves as a lasting monument to human creativity, vision, and determination. It reminds us that civilizations long before the modern era were capable of engineering feats that blend technical mastery with cultural and spiritual sophistication, leaving a legacy that continues to challenge and inspire the world. Every aspect of Abydos, from the massive interlocking stones to the intricate drainage systems and astronomical alignments, reflects the Egyptians' holistic approach to construction. Their achievements reveal a civilization that understood the interplay between materials, forces, environment, and symbolism, creating structures that are functional, durable, and spiritually meaningful. Abydos remains a monumental symbol of human potential, ingenuity, and the timeless ability to transform knowledge, skill, and vision into enduring architectural marvels that continue to captivate, challenge, and inspire centuries later. High atop the limestone cliffs of Malta, the megalithic temples of Hagar Kim and Najdra rise as some of the oldest freestanding stone structures in the world, predating both Stonehenge and the Great Pyramids by several centuries. Constructed around 3600 to 2500 BCE, these temples stand as a testament to the extraordinary architectural, engineering, and astronomical capabilities of prehistoric societies in the Mediterranean. Despite the absence of written records from the builders, the temples reveal a profound understanding of stone construction, celestial observation, and spatial organization, challenging conventional assumptions about the technological abilities of Neolithic civilizations. The precision, scale, and sophistication of these structures continue to astonish modern researchers, inviting questions about how such monumental achievements were possible thousands of years before the advent of advanced tools and engineering knowledge. The architectural design of Hagar Kim and Najdra is immediately striking. Both complexes are composed of massive limestone blocks, some weighing several tons, carefully shaped and assembled into walls, passageways, and chambers. The builders achieved remarkable accuracy in stone placement, with joints fitting tightly without the use of mortar, creating structures capable of withstanding centuries of seismic activity, wind, and rain. The layout of the temples reflects intentionality and purpose, with semicircular apses, central courts, and axial alignments that suggest both ceremonial function and spatial sophistication. Each stone was carefully selected, transported, and positioned to create an enduring architectural framework that communicates not only technical skill but also a deep understanding of geometry, weight distribution, and structural stability. The transportation and placement of megalithic stones at Hagar Kim and Najdra remain a topic of considerable fascination. Quarrying the massive limestone blocks from nearby sources and moving them across uneven terrain without wheels, draft animals, or advanced machinery required ingenuity, coordination, and physical endurance. Archaeologists hypothesize the use of sledges, rollers, ropes, and inclined planes, yet the precision with which the stones were ultimately positioned suggests methods that incorporated both careful planning and sophisticated practical knowledge. The process likely involved a large workforce organized into teams responsible for excavation, transport, shaping, and assembly, indicating a society capable of large-scale project management and logistical coordination at a level often underestimated in prehistoric contexts. The temple's integration with celestial phenomena demonstrates an advanced understanding of astronomy. Najdra, in particular, is aligned with the solstices, such that on the summer solstice, the rising sun illuminates specific chambers and features in precise alignment with the temple's architecture. This indicates that the builders carefully observed solar cycles and incorporated this knowledge into the construction, integrating ceremonial function with astronomical precision. Such alignments suggest that the temples were used not only as places of worship but also as early observatories, capable of tracking seasonal changes that were crucial for agriculture and ritual practice. The combination of astronomical awareness with architectural ingenuity reflects a sophisticated interplay of science, art, and spiritual practice in these prehistoric communities. Water management and environmental adaptation were also integral to the design of the temples. The builders accounted for the exposure of these structures to the harsh Mediterranean climate, incorporating drainage systems, elevated platforms, and stone placement that minimized water damage and erosion. The ability to anticipate environmental forces and engineer solutions that preserved the integrity of the temples over millennia demonstrates a nuanced understanding of materials, weather patterns, and site-specific challenges. The combination of structural resilience and environmental adaptation reflects a prehistoric engineering sophistication that continues to impress modern researchers. The artistic and symbolic elements of the temples are deeply intertwined with their engineering. Hagar Kim and Najdra feature carved stone altars, decorative motifs, and petroglyphs that convey ritual and spiritual significance. The precision of the carvings, often integrated seamlessly into load-bearing stones, highlights the builder's ability to merge functional architecture with aesthetic and symbolic expression. This integration of art, ritual, and engineering underscores a holistic approach to construction, demonstrating that the temples were designed to engage the senses, convey meaning, and facilitate communal and ceremonial activities while maintaining structural integrity. The spatial organization of the complexes reveals a sophisticated understanding of movement, sightlines, and social function. Chambers and apses were arranged to guide visitors through specific paths, likely enhancing the spiritual or ceremonial experience. The axial alignment and proportional relationships between spaces suggest that the builders possessed a sense of scale and proportion that allowed them to construct harmonious, functional, and aesthetically compelling environments. These considerations indicate an awareness of human perception, spatial dynamics, and experiential design, illustrating that the temples were conceived as immersive environments rather than mere static structures. Labor organization at Hagar Kim and Najdra would have required a high degree of social coordination. Quarrying, transporting, shaping, and assembling massive stones demanded the efforts of a large, organized workforce. Evidence suggests that communities mobilized collectively to contribute labor and expertise, indicating complex social structures capable of supporting extended construction projects. Coordination likely involved assigning specialized roles, managing resources, and synchronizing tasks to ensure both precision and efficiency. This demonstrates that the prehistoric builders combined technical knowledge with organizational acumen, resulting in structures that were not only durable but also monumental in scale and cultural significance. The endurance of these temples through millennia is a testament to the effectiveness of their construction techniques. Despite exposure to earthquakes, storms, and centuries of erosion, Hagar Kim and Najdra remain remarkably intact. Modern engineers study these structures to understand their stability, weight distribution, and resistance to environmental stressors. The tight-fitting stones, careful orientation, and adaptive design highlight methods that prefigured many principles of modern engineering, revealing that prehistoric builders possessed empirical knowledge that allowed them to construct long-lasting monuments in challenging environments. The integration of astronomy, environment, and construction at Hagar Kim and Najdra illustrates the prehistoric builders' interdisciplinary expertise. These societies were capable of synthesizing observations of celestial patterns, environmental forces, and human use into architectural solutions that were functional, symbolic, and enduring. The temples were designed to serve multiple purposes simultaneously, as ceremonial centers, astronomical observatories, and resilient architectural marvels. This multidimensional approach demonstrates a depth of understanding and foresight that challenges assumptions about prehistoric technological capabilities. Ultimately, Hagar Kim and Najdra stand as enduring testaments to human ingenuity, vision, and technical mastery in the prehistoric world. The massive stones, precise construction, celestial alignments, and environmental adaptations reflect a civilization that understood the interplay of materials, forces, and human needs at an advanced level. These temples challenge modern assumptions about Neolithic societies, illustrating that even in the absence of written language or advanced tools, humans were capable of monumental achievements that integrated engineering, art, science, and spirituality. Every stone, alignment, and carved detail at Hagar Kim and Najdra reflects careful planning, sophisticated skill, and cultural intentionality. The builders demonstrated knowledge of mechanics, astronomy, and environmental adaptation, achieving a synthesis of technical mastery and aesthetic expression rarely seen even in later periods. These temples continue to inspire awe, study, and debate, standing as powerful reminders of the extraordinary capabilities of prehistoric humans. They reveal that the origins of monumental engineering, astronomical observation, and integrated architectural design extend far deeper into human history than commonly appreciated, challenging us to reconsider the timeline of technological and cultural sophistication in the ancient world. The enduring legacy of Hagar Kim and Najdra illustrates that technical skill, artistic vision, and spiritual purpose were inseparable in prehistoric construction. Their survival across thousands of years underscores the effectiveness of empirical knowledge, careful planning, and environmental adaptation. These temples are not merely archaeological relics, they are monumental embodiments of human creativity, intelligence, and capacity for innovation. They continue to captivate the imagination, demonstrating that the roots of engineering, astronomy, and architectural excellence stretch back to the earliest chapters of human civilization, leaving an indelible mark on the story of human achievement. Deep in the remote deserts of Egypt, on the west bank of the Nile, lies the ancient necropolis of Saqqara, a site that has long fascinated archaeologists, historians, and engineers alike. Saqqara is home to some of the most important developments in early Egyptian architecture, serving as a burial ground for pharaohs and nobles for more than 3 millennia. Yet, what makes Saqqara particularly compelling is not just its spiritual significance but the remarkable engineering feats that it embodies. From the step pyramid of Djoser to hidden chambers and intricate subterranean networks, the site reveals a civilization that had mastered both the manipulation of massive stone and the sophisticated organization of labor, logistics, and knowledge, centuries before the advent of machinery or modern engineering techniques. These structures continue to challenge conventional assumptions about what ancient societies were capable of achieving. The step pyramid of Djoser stands as the crown jewel of Saqqara, representing a paradigm shift in architectural design. Constructed around 2667 to 2648 BCE under the supervision of the Vizier Imhotep, this pyramid was the world's first large-scale stone structure. It was revolutionary in its departure from traditional mastaba tombs, elevating stacked layers to create a stepped appearance that would inspire later pyramids across Egypt. The sheer scale of the construction is awe-inspiring, with millions of limestone blocks meticulously cut, transported, and assembled. Each block, some weighing several tons, was positioned with extreme precision, forming a structure that has endured thousands of years of environmental stress, including earthquakes, floods, and extreme temperature fluctuations. The precision of alignment, both horizontally and vertically, demonstrates an empirical understanding of structural stability, load distribution, and materials science that remains astonishing even by modern standards. Transporting the limestone for the step pyramid was an extraordinary feat in itself. The quarries from which the stones were sourced were often located several kilometers away from the construction site. Without the benefit of wheeled vehicles, cranes, or other modern machinery, the ancient Egyptians relied on a combination of human labor, sledges, lubricated tracks, and possibly inclined planes to move massive blocks over uneven terrain. This required meticulous planning, coordination of thousands of workers, and an understanding of mechanical principles such as leverage and friction. The logistical complexity of moving and precisely positioning tens of thousands of stone blocks highlights not only physical ingenuity but also a level of project management sophistication that would rival modern construction endeavors. The engineering of the step pyramid extends beyond its vertical construction. Beneath the pyramid lies a labyrinthine network of underground chambers, tunnels, and galleries, designed both to house the remains of the pharaoh and to serve ceremonial purposes. These subterranean structures were carved with extraordinary precision, with corridors and chambers aligned to cardinal directions and carefully designed for structural integrity. The stone ceilings are supported by corbelling techniques, distributing weight evenly to prevent collapse over centuries. In addition to their practical function, these underground passages were laden with symbolic significance, reflecting the Egyptian worldview of the afterlife and the journey of the soul. The dual nature of these chambers, functional and spiritual, demonstrates the ancient Egyptians' ability to integrate engineering, architecture, and cosmology seamlessly. One of the most striking aspects of Saqqara is the precision with which the pyramid and surrounding complexes were aligned with celestial phenomena. Scholars have long noted that the step pyramid complex aligns closely with specific stars and cardinal points, indicating an understanding of astronomy and its integration into architectural design. Such alignment would have required careful observation over decades, tracking the movements of celestial bodies, and translating these observations into large-scale construction plans. This interplay of astronomy and architecture reflects an advanced capacity for interdisciplinary thinking, combining empirical observation with geometric knowledge and practical construction techniques. Water management and environmental adaptation were also integral to the construction of Saqqara's monuments. The desert environment posed significant challenges, including erosion, sand accumulation, and seasonal flooding. Drainage channels, strategic siting, and careful stone placement were employed to mitigate these risks. The step pyramid itself is built on a bedrock foundation that stabilizes the structure, while surrounding terraces and retaining walls help manage water flow and prevent erosion. These considerations demonstrate that the Egyptians were not merely constructing monuments, they were engineering long-lasting structures that accounted for environmental forces, revealing an empirical understanding of soil mechanics, hydrology, and landscape adaptation. The labor organization required for Saqqara's monumental constructions was extraordinary. Archaeological evidence suggests that thousands of skilled artisans, laborers, and planners were mobilized to execute the complex designs. Specialized teams were likely responsible for quarrying, shaping, transporting, and assembling stones, while overseers coordinated the timing, sequencing, and quality of work. Housing, food, and logistics would have been managed on an unprecedented scale, indicating a society with sophisticated administrative capacity. The ability to coordinate such an immense workforce over decades demonstrates that the success of Saqqara's constructions relied as much on social and organizational ingenuity as on engineering expertise. Beyond the step pyramid, Saqqara contains numerous other pyramids, tombs, and temples, each demonstrating technical innovation and architectural sophistication. The Pyramid of Unas, for example, contains the earliest known pyramid texts, inscribed on the interior walls, and is oriented with meticulous precision. The construction of these pyramids involved innovations such as internal chambers supported by corbelled ceilings, cleverly designed passageways, and techniques to reduce the risk of structural collapse. The consistency of these techniques across multiple structures over centuries indicates a sustained and sophisticated architectural tradition, one that combined empirical experimentation with standardized methods passed through generations of builders. Stonework at Saqqara also exhibits extraordinary refinement. Blocks were cut with precise dimensions, surfaces smoothed, and joints fitted with remarkable accuracy. The polygonal and rectangular masonry, combined with subtle adjustments to weight distribution and alignment, enabled the structures to withstand seismic activity, settling, and environmental degradation over millennia. The ability to achieve such precision without modern measurement tools suggests the use of practical geometry, physical templates, and iterative techniques developed through experience and observation. This level of craftsmanship reveals a deep understanding of materials science, structural engineering, and project planning that challenges assumptions about the capabilities of early civilizations. The integration of symbolism and function is evident throughout Saqqara's complexes. Temples, ceremonial courts, and mortuary chapels were designed not only to facilitate religious rites but also to communicate power, hierarchy, and cosmological principles. The orientation, proportional relationships, and spatial sequencing of structures reflect an intentional effort to embed meaning into architecture, merging engineering, aesthetics, and spiritual function. Every aspect of the complexes, from the positioning of obelisks to the layout of courtyards, is carefully calculated to reinforce cultural, religious, and social narratives, illustrating the Egyptians' ability to synthesize multiple domains of knowledge into cohesive monumental environments. Astronomical knowledge at Saqqara extended beyond simple alignment. Scholars have proposed that certain passageways and chambers were designed to track solar and stellar movements, marking seasonal changes critical for agriculture and ritual calendars. These precise alignments required systematic observation, recording, and translation of celestial patterns into physical construction. The successful integration of astronomy with large-scale stone construction demonstrates the Egyptians' capacity for abstract thinking, planning, and problem-solving at a scale that continues to astonish modern engineers and researchers. Environmental adaptation and structural resilience were also key components of Saqqara's enduring success. Builders accounted for erosion, flooding, and material expansion and contraction, implementing techniques that minimized long-term damage. The combination of robust foundations, strategic stone placement, and careful management of environmental forces ensured the survival of structures over thousands of years. This foresight reflects a sophisticated empirical understanding of materials, mechanics, and natural processes, highlighting the Egyptians' ability to design solutions that were both innovative and durable. The social, organizational, and technical achievements evident at Saqqara suggest a civilization capable of large-scale interdisciplinary problem-solving. Coordinating labor, resources, and knowledge over decades, while integrating engineering, astronomy, and religious symbolism, required an unprecedented level of planning and intellectual capacity. The pyramids and associated structures demonstrate that the Egyptians were not only skilled builders but also sophisticated planners, astronomers, administrators, and engineers. Their accomplishments challenge modern assumptions about the technological limitations of early civilizations, revealing a society capable of extraordinary innovation, foresight, and precision. Ultimately, Saqqara stands as a monumental testament to human ingenuity, foresight, and technical mastery. The step pyramid, underground galleries, and surrounding complexes illustrate a civilization capable of integrating empirical observation, engineering, environmental adaptation, and cultural symbolism into structures of immense scale and durability. Every stone, passageway, and alignment reflects careful planning, technical expertise, and cultural intentionality. Saqqara challenges modern narratives about the origins of architectural sophistication and engineering knowledge, showing that human ingenuity and problem-solving capacity have deep historical roots that predate modern technology by millennia. The legacy of Saqqara endures not only in its monumental structures but in the lessons it offers about resilience, precision, and interdisciplinary thinking. Its pyramids, temples, and tombs exemplify the integration of engineering, astronomy, environmental adaptation, and social organization, creating built environments that are functional, enduring, and symbolically profound. Saqqara reminds us that ancient societies were capable of extraordinary accomplishments, achieving feats of engineering and design that continue to inspire awe and study in the modern era. Every stone and chamber at Saqqara is a testament to the vision, skill, and intellect of a civilization that mastered materials, labor, and knowledge to leave a legacy that remains unparalleled in its scale, precision, and enduring significance. From the massive stones of the step pyramid to the intricate subterranean networks and celestial alignments, Saqqara exemplifies a civilization that transcended technological limitations through careful observation, ingenuity, and coordination. The site continues to captivate archaeologists, engineers, and historians because it challenges contemporary assumptions about the capabilities of early civilizations. Saqqara is more than an archaeological site, it is a monumental record of human achievement, a testament to the enduring capacity for creativity, problem-solving, and architectural excellence that has shaped the course of history and continues to inspire generations across the globe. In the arid and windswept deserts of southern Egypt, hidden within the shadow of the more famous Giza Plateau, lies the mysterious and largely overlooked site of Djoser's Step Pyramid Complex at Saqqara, a location that serves as a window into the revolutionary architectural and engineering advances of early dynastic Egypt. Though often studied for its spiritual and ceremonial importance, the Step Pyramid and its surrounding complex offer profound insight into the technological capabilities and inventive ingenuity of a civilization that thrived over 4 millennia ago. Constructed during the reign of Pharaoh Djoser under the guidance of his chief architect, Imhotep, the complex represents not merely a monumental tomb, but an architectural laboratory where techniques in stone masonry, spatial organization, water management, and environmental adaptation were tested, refined, and executed with unprecedented precision. The scale, complexity, and sophistication of these constructions continue to challenge modern engineers and historians, prompting questions about how an ancient society, without the benefit of modern tools or mathematical theory, could achieve such enduring feats. The Step Pyramid itself represents a radical departure from traditional mastaba tombs, evolving from a simple rectangular structure into a 6-tiered, stepped monument that soars nearly 60 meters high. Each tier was carefully aligned and proportioned, reflecting a level of geometric understanding that belies the technological limitations of the era. The limestone blocks used to construct the pyramid were quarried locally yet transported with remarkable coordination across uneven terrain, some weighing several tons each. The precise cutting, fitting, and placement of these stones ensured structural stability while allowing the monument to withstand environmental stresses such as seasonal flooding, sand erosion, and seismic activity over thousands of years. The builders demonstrated not only an intimate knowledge of material properties and mechanical forces but also the ability to organize large-scale projects with meticulous attention to detail and foresight. Beneath the pyramid lies an extensive labyrinth of subterranean chambers, galleries, and passageways, reflecting both technical ingenuity and spiritual purpose. These underground structures were carved with precision, incorporating corbelled ceilings, load-bearing walls, and complex access routes designed to protect the pharaoh's remains and facilitate ritual practices. Some corridors are aligned along cardinal points, while others are precisely measured to create acoustic effects or symbolic spatial relationships. The interplay between structural engineering and ritual significance illustrates the Egyptians' ability to integrate practical and symbolic functions seamlessly. Each chamber required careful calculation of load distribution, stone placement, and stability, emphasizing that the Step Pyramid was as much an engineering marvel as a spiritual monument. Transporting and positioning the massive stones for the Step Pyramid demanded exceptional logistical coordination. Without wheeled vehicles or cranes, the ancient builders likely relied on sledges, lubricated tracks, and teams of workers moving stones in a synchronized manner. Evidence from contemporary depictions suggests the use of organized labor, possibly involving thousands of individuals, each assigned specific tasks from quarrying and shaping to hauling and assembling the massive blocks. The precision with which these stones were ultimately positioned, often in exact alignment over significant vertical and horizontal distances, implies not only physical ingenuity but also sophisticated project management, communication systems, and an empirical understanding of mechanics. The execution of such a monumental task reflects a society capable of harmonizing human effort, technical skill, and environmental observation on a grand scale. The surrounding complex of the Step Pyramid further highlights the Egyptians' advanced understanding of architecture and landscape integration. Courtyards, ceremonial halls, and subsidiary pyramids were arranged with deliberate spatial relationships that guided movement, reinforced ritual significance, and emphasized the authority of the pharaoh. The axial alignment of these structures often corresponds with cardinal directions or celestial events, suggesting that astronomy played a critical role in the planning and design of the complex. Temples, chapels, and storage facilities were strategically positioned to accommodate the needs of priests, officials, and workers, demonstrating an early form of integrated urban and ceremonial planning. The Egyptians' ability to combine functional utility, aesthetic proportion, and symbolic meaning reveals a holistic approach to construction that integrated multiple domains of knowledge into a cohesive built environment. Water management at the Step Pyramid complex was another critical engineering achievement. Though the surrounding desert seems inhospitable, the builders incorporated drainage channels, retaining walls, and leveled platforms to mitigate the effects of rainwater and groundwater seepage. Subterranean passages were designed to remain dry, and courtyards were sloped to direct water away from critical structural elements. The step pyramid's foundation itself was carved into bedrock, providing a stable base that resisted settling and erosion over centuries. These considerations reflect a sophisticated understanding of hydrology and environmental forces, demonstrating that the architects of the complex could anticipate and mitigate potential structural and environmental challenges, ensuring the longevity of their constructions. The step pyramid complex also reveals advanced techniques in stone shaping and masonry. Limestone blocks were not only cut to precise dimensions but also polished and fitted to interlock without mortar. The joints were crafted with such accuracy that many stones have remained in perfect alignment despite thousands of years of natural stress. The builders employed corbelling, precise weight distribution, and incremental layering to create structural integrity that modern engineers still study to understand seismic resistance and long-term stability. The mastery of these techniques indicates an empirical understanding of mechanics and materials, achieved through observation, experimentation, and refinement over time, long before formal engineering knowledge existed. Social organization was central to the successful execution of the step pyramid and its associated structures. Coordinating labor for quarrying, transportation, and construction required hierarchical management, task specialization, and logistical planning. Skilled artisans worked alongside unskilled laborers, each contributing to specific stages of the project under supervision from architects and overseers. The ability to manage resources, labor, and time over decades of construction reflects an advanced administrative capacity that was critical to the realization of monumental architecture. It is evident that the step pyramid's builders combined technical knowledge, social coordination, and organizational foresight to accomplish feats that continue to astonish modern observers. The step pyramid complex also demonstrates the Egyptians' integration of spiritual symbolism with technical achievement. Temples, courtyards, and ceremonial halls were carefully aligned and proportioned to convey cosmological and theological concepts. Hieroglyphic inscriptions, reliefs, and symbolic architectural elements were embedded into functional structures, communicating religious, social, and political messages. This seamless integration of symbolism and utility illustrates a civilization that did not view engineering as separate from cultural or spiritual life. Instead, architecture became a medium through which technical skill, ritual practice, and societal values were expressed in harmony, creating an enduring legacy that communicated authority, identity, and cosmology across millennia. Astronomical knowledge was embedded throughout the complex. Certain corridors and chambers align with solstices and equinoxes, indicating that the builders possessed a sophisticated understanding of celestial movements and their implications for agriculture, ritual, and timekeeping. Achieving such precise alignments required systematic observation, measurement, and the ability to translate astronomical data into architectural design. The successful incorporation of celestial observation into monumental construction reflects the Egyptians' capacity for interdisciplinary thinking, combining geometry, observation, and spatial planning to achieve both functional and symbolic goals. The step pyramid's longevity is a testament to the effectiveness of ancient Egyptian engineering. Despite thousands of years of exposure to the elements, seismic activity, and human activity, the pyramid remains largely intact. Modern engineers study its foundations, stonework, and corbelled chambers to understand the methods employed to achieve such resilience. The enduring stability of the step pyramid underscores the Egyptians' empirical mastery of materials, structural dynamics, and environmental adaptation, revealing a level of sophistication in engineering and architecture that continues to inform contemporary study and admiration. Beyond the pyramid itself, the surrounding necropolis contains mastabas, subsidiary pyramids, and ceremonial structures, all reflecting technical ingenuity and standardized construction methods. The uniformity of stone cutting, alignment, and structural principles across multiple buildings indicates a coherent architectural tradition maintained over generations. These techniques illustrate an advanced understanding of building science, demonstrating that the Egyptians could not only innovate monumental structures but also replicate and standardize complex construction processes on a large scale. Ultimately, the step pyramid complex at Saqqara represents a convergence of empirical knowledge, technical mastery, and cultural intentionality. The structures exemplify advanced understanding of material properties, structural engineering, environmental adaptation, and astronomical alignment, all integrated within a symbolic and ceremonial framework. Each stone, corridor, and courtyard reflects careful planning, interdisciplinary knowledge, and the capacity to mobilize human effort effectively. Saqqara challenges modern assumptions about the technological and organizational capabilities of early civilizations, illustrating that the Egyptians possessed both the intellectual and practical means to create enduring architectural marvels. The legacy of the step pyramid is not only in its monumental scale but in the lessons it offers about human ingenuity, resilience, and problem-solving. The complex demonstrates that with careful observation, planning, and coordination, societies can achieve extraordinary feats that endure for millennia. From the quarrying of massive stones to the precise alignment of subterranean chambers, the step pyramid reflects a civilization capable of integrating engineering, astronomy, environmental adaptation, and spiritual symbolism into coherent, enduring, and awe-inspiring monuments. Its construction continues to inspire engineers, historians, and archaeologists, standing as a timeless testament to the heights of human creativity, intelligence, and organizational capacity. Every element of the step pyramid complex, from the massive interlocking limestone blocks to the sophisticated drainage systems and celestial alignments, reveals a civilization that transcended the technological limitations of its era. The Egyptians combined empirical knowledge, skilled labor, and meticulous planning to produce structures that were functional, enduring, and symbolically profound. Saqqara is more than an archaeological site, it is an enduring monument to human capability, offering insight into the ingenuity, foresight, and technical mastery that enabled a civilization to achieve what many would consider impossible. Its enduring presence challenges modern perceptions of ancient technology, inspiring awe and demanding a reconsideration of the sophistication of early engineering and architectural accomplishment. On a windswept plateau in southern Peru, overlooking the twisting Urubamba River, lies the ancient citadel of Machu Picchu, one of the most iconic and enigmatic sites of pre-Columbian civilization. Constructed in the mid-15th century during the reign of the Inca Emperor Pachacuti, Machu Picchu represents the pinnacle of Inca architectural, engineering, and environmental mastery. Unlike other sites that served primarily as military, political, or religious centers, Machu Picchu combines all these elements in a single, extraordinarily sophisticated urban and agricultural complex. Its terraces, temples, residential areas, and water systems reveal a civilization capable of harmonizing monumental construction with the challenging Andean landscape, creating a settlement that is both functional and breathtakingly beautiful. Even centuries later, modern engineers, archaeologists, and architects continue to study Machu Picchu in awe, struggling to fully comprehend the ingenuity and precision required to build such a site without modern tools, machinery, or written blueprints. The terraces of Machu Picchu are among the most striking examples of the Incas' understanding of environmental engineering. Carved into steep mountainsides, these agricultural terraces served multiple purposes. They stabilized the slopes, prevented landslides, optimized drainage, and created microclimates suitable for a variety of crops. Each terrace was carefully angled and layered with soil, gravel, and stones to regulate water flow, prevent erosion, and retain nutrients, demonstrating an intimate knowledge of agronomy, hydrology, and geology. The terraces also allowed for high-density agriculture in an otherwise inhospitable environment, supporting a population of several hundred people while preserving the integrity of the mountain itself. This integration of environmental adaptation, food production, and structural stability is a hallmark of Inca engineering, revealing a civilization that could manipulate its landscape with precision and foresight. Stonework at Machu Picchu is another testament to the Incas' advanced construction techniques. Buildings and temples were constructed using finely cut granite blocks, shaped to fit together perfectly without mortar. The interlocking stones were designed to withstand seismic activity common in the Andes, allowing walls and structures to shift slightly during earthquakes without collapsing. This technique, known as ashlar masonry, reflects both practical engineering and aesthetic sensibility, as walls are not only structurally resilient but also visually harmonious. Some of the largest stones weigh several tons and were transported across steep and rugged terrain, highlighting the Incas' sophisticated understanding of mechanics, leverage, and labor organization. The precision achieved in this masonry continues to baffle engineers and remains a subject of intensive study. Water management at Machu Picchu further demonstrates the Incas' remarkable technical skills. The site features an intricate network of aqueducts, canals, and drainage systems designed to capture and distribute water from mountain springs while preventing erosion and flooding. Stone channels were meticulously aligned, often with slight gradients, to ensure a steady flow of water throughout residential and agricultural areas. The drainage systems beneath plazas and terraces effectively prevent waterlogging, preserving both crops and structures. This integration of water management with urban planning reflects a civilization capable of not only observing and understanding natural hydrological systems but also manipulating them to suit human needs in a sustainable manner. Machu Picchu's urban layout exemplifies the Incas' mastery of spatial organization. Residential, ceremonial, and agricultural areas are carefully positioned to take advantage of natural terrain, sunlight exposure, and water availability. Temples and sacred sites are strategically located along high points, offering panoramic views and reinforcing spiritual and political authority. Residential areas are organized to facilitate daily life while accommodating social hierarchy, with evidence of carefully planned pathways, staircases, and plazas to guide movement through the complex. The integration of functional, ceremonial, and residential spaces demonstrates a holistic approach to urban planning, where engineering, aesthetics, and social organization converge seamlessly. Transportation of massive stones and construction materials presented formidable challenges that the Inca overcame with ingenuity and labor organization. Stones were quarried from local sources and maneuvered across steep, uneven paths using ropes, levers, ramps, and coordinated human effort. While no wheel or draft animal was employed, the construction achieved remarkable precision in stone placement, alignment, and stability. The logistical feat required a hierarchical labor system, careful planning, and real-time problem-solving, underscoring the Incas' sophisticated project management capabilities. The ability to execute large-scale construction in such a remote and rugged environment reveals both technical skill and an exceptional understanding of human resource coordination. Astronomical knowledge is subtly integrated into Machu Picchu's design. Certain structures, such as the Intihuatana stone, are aligned with celestial events, particularly solstices, which had both ritualistic and agricultural significance. The placement of temples, windows, and terraces often corresponds with solar, lunar, and stellar observations, allowing the Inca to track seasonal changes critical for crop cycles and ceremonial timing. This integration of astronomy with construction demonstrates a society capable of abstract thought, observation, and practical application, merging spiritual beliefs with functional engineering. The harmonious alignment of natural and built elements at Machu Picchu is a testament to the Incas' ability to blend cosmology, science, and architecture into a cohesive, enduring environment. The spiritual and ceremonial components of Machu Picchu are interwoven with its technical achievements. Temples, shrines, and ritual platforms are meticulously aligned, positioned, and constructed to enhance spiritual experiences and reflect cosmological principles. The Temple of the Sun, with its curved walls and strategic apertures, captures sunlight during solstices, creating dramatic illuminations that would have enhanced ritual significance. Similarly, the Intihuatana stone, a carved ritual rock, may have functioned as an astronomical clock, marking seasonal changes for both agricultural and ceremonial purposes. These structures illustrate the Incas' ability to integrate ritual practice with precise engineering, creating a built environment that was both functional and symbolically powerful. Machu Picchu also exemplifies the Incas' ability to create resilient structures capable of withstanding natural forces. The region is prone to heavy rainfall, landslides, and seismic activity, yet the site has endured for centuries. Terrace construction, interlocking masonry, and sophisticated drainage systems all contribute to the settlement's resilience. Retaining walls absorb seismic shocks, while terraces reduce slope instability, and aqueducts prevent water accumulation from compromising structural integrity. This combination of foresight, design, and material understanding reflects a level of engineering sophistication that remains impressive even to modern observers and has prompted extensive study in the fields of architecture, geology, and civil engineering. Social organization was critical to Machu Picchu's construction and maintenance. Coordinating labor across challenging terrain required a hierarchical system with specialized roles. Artisans, engineers, laborers, and planners worked in unison, implementing complex construction methods that demanded both precision and efficiency. Resource management, from sourcing stone to organizing food and shelter for workers, reflects advanced administrative capabilities. The successful completion of the complex demonstrates that Inca society possessed not only technical expertise but also an unparalleled capacity for project management, social coordination, and long-term planning. The integration of agriculture with urban design further highlights the Incas' holistic approach. Agricultural terraces were constructed adjacent to residential and ceremonial areas, maximizing the efficient use of space and resources. These terraces not only stabilized the mountainside but also provided a controlled environment for growing crops, incorporating microclimates, drainage channels, and soil management techniques. The combination of sustainable agriculture, urban planning, and architectural engineering demonstrates a civilization capable of balancing human needs with environmental constraints, producing a functional, aesthetically cohesive, and enduring settlement. Machu Picchu's artistry complements its engineering brilliance. Carved stonework, finely polished walls, trapezoidal doorways, and intricately designed staircases reveal a civilization that valued both form and function. Precision cutting, weight distribution, and interlocking stones all serve structural purposes while creating visual harmony. Even minor architectural details, such as the positioning of windows, drainage channels, or ceremonial altars, reflect an understanding of ergonomics, material properties, and environmental adaptation. This synthesis of aesthetic, functional, and structural considerations underscores the Incas' ability to think across disciplines, integrating technical knowledge with cultural and spiritual objectives. The enduring appeal of Machu Picchu lies not only in its dramatic location and beauty but in the profound technical mastery it represents. The site reflects a civilization capable of harmonizing construction, astronomy, agriculture, and ritual practice into a single, coherent, and resilient settlement. Every terrace, wall, and temple demonstrates an understanding of materials, mechanics, and the environment that continues to inspire architects and engineers today. Machu Picchu is a living testament to the ingenuity, resourcefulness, and holistic thinking of the Inca civilization, revealing a level of sophistication that challenges conventional notions of pre-Columbian technology and engineering. Ultimately, Machu Picchu embodies the fusion of human intellect, labor, and environmental awareness into an enduring architectural masterpiece. Its construction reflects not only technical expertise but also an extraordinary capacity for observation, planning, and social organization. The site's terraces stabilize mountainsides, its stonework resists earthquakes, its aqueducts manage water flow, and its ceremonial alignments track celestial movements, illustrating the Incas' multidisciplinary approach. The enduring presence of Machu Picchu, surviving centuries of natural forces and human intervention, is a testament to the vision, knowledge, and skill of its builders. It challenges modern perceptions of ancient engineering, revealing a civilization capable of creating monumental works that are both functionally brilliant and spiritually resonant. From the meticulous terraces to the precision masonry, from the sophisticated drainage systems to the astronomical alignments, Machu Picchu reveals a civilization that mastered the art of building in harmony with nature. The Inca transformed a rugged and seemingly inhospitable landscape into a thriving, resilient, and spiritually meaningful settlement. Machu Picchu stands as a symbol of human ingenuity, vision, and the ability to integrate science, engineering, art, and spirituality into enduring monuments. It is a testament to what can be achieved when human intelligence, labor, and observation are combined, leaving a legacy that continues to captivate, inspire, and challenge our understanding of ancient technological and architectural accomplishment. High in the rugged mountains of southeastern Turkey, overlooking the vast plains of Anatolia, lies Göbekli Tepe, a site that has upended long-held assumptions about the origins of human civilization. Dating back to around 9600 BCE, this monumental complex predates Stonehenge by more than 6 millennia and challenges conventional timelines that place the development of complex society, agriculture, and monumental architecture much later in human history. Unlike later sites associated with established cities or centralized governments, Göbekli Tepe was constructed by hunter-gatherer communities, suggesting that humans were capable of organizing massive construction projects long before the advent of agriculture or formal state structures. The site consists of massive stone pillars arranged in circular and oval enclosures, intricately carved with animal motifs and abstract symbols, revealing a civilization with remarkable technical skill, symbolic sophistication, and social organization that has left scholars and engineers alike grappling with profound questions about the origins of human ingenuity. The monumental pillars of Göbekli Tepe are the centerpiece of the site's enduring mystery. Many of these megaliths stand between 3 and 6 meters tall and weigh between 10 and 20 tons, yet they were quarried, transported, and erected without the use of wheels, draft animals, or advanced machinery. The stonework displays not only precise shaping but also careful alignment within circular enclosures, suggesting a sophisticated understanding of spatial geometry. Carvings depicting animals such as lions, foxes, snakes, and birds adorn the pillars, executed with remarkable skill and attention to detail. These reliefs are more than decorative, they convey symbolic meaning, possibly linked to spiritual beliefs, cosmology, or social identity. The integration of artistry with monumental construction demonstrates that the builders of Göbekli Tepe possessed both technical proficiency and conceptual complexity unprecedented for a society of hunter-gatherers. Transporting the massive pillars to their positions required extraordinary ingenuity. Without modern equipment or domesticated animals for hauling, researchers hypothesize that the builders used a combination of human labor, sledges, ropes, inclined planes, and earthen ramps. Coordinating such efforts would have necessitated detailed planning, organization of large workforces, and knowledge of leverage, friction, and weight distribution. The successful erection of these pillars, perfectly aligned within circular structures, implies that the builders possessed both empirical understanding and practical engineering solutions honed through experience. The ability to achieve such precision and scale without the technological advantages assumed necessary for megalithic construction challenges long-standing assumptions about the capabilities of early human societies. Göbekli Tepe's circular enclosures illustrate an advanced understanding of architecture and structural dynamics. The pillars, often arranged in pairs, support horizontal lintels that form the enclosure's perimeters, creating stable, freestanding structures without the use of mortar. Some pillars feature T-shaped designs, while others are slightly angled or positioned to optimize weight distribution and stability. The careful calibration of angles, spacing, and weight transfer indicates empirical knowledge of mechanics, likely developed through observation, trial, and iterative refinement. These architectural choices allowed the enclosures to withstand millennia of geological activity, erosion, and environmental stress, demonstrating an impressive grasp of long-term structural resilience. Symbolism and ritual appear central to Göbekli Tepe's design. The site lacks residential structures, suggesting that it functioned primarily as a ceremonial or religious complex rather than as a settlement. The carvings on the pillars, including representations of dangerous animals and abstract motifs, may have served as spiritual or ritualistic symbols, guiding communal practices, storytelling, or social cohesion. Some scholars speculate that the site was a center for gatherings, feasting, and ritual activity, implying that monumental construction may have emerged not from state directives or economic necessity, but from collective spiritual motivation. This challenges conventional theories that large-scale architecture only arises from centralized political power or sedentary agricultural societies. Astronomical alignment may also have played a role in the design of Göbekli Tepe. Researchers have noted that some enclosures and pillar orientations correspond with celestial events, such as solstices and lunar cycles, suggesting that the builders observed the movements of stars and planets and incorporated this knowledge into their construction. The ability to translate astronomical observation into large-scale architectural planning indicates a level of abstract thinking, mathematical reasoning, and empirical observation far earlier than previously believed. Aligning massive stone structures to celestial phenomena would have required careful measurement, long-term observation, and a shared system of knowledge among the builders, highlighting the complexity of these early societies. The social organization required to construct Göbekli Tepe is extraordinary. Coordinating the quarrying, transport, shaping, and placement of massive pillars would have demanded a high degree of planning, leadership, and division of labor. Although the society lacked formal cities, writing, or complex governance, it clearly possessed the capacity to mobilize large groups of people, assign specialized roles, and maintain cohesion over decades of construction. This suggests that social complexity and cooperation may have predated agriculture, challenging the assumption that organized labor and monumental architecture are exclusively products of settled, agrarian civilizations. The site exemplifies a model of pre-agricultural societal organization capable of achieving remarkable technical and social feats. The carvings at Göbekli Tepe reveal an astonishing level of artistic sophistication intertwined with engineering prowess. Each pillar displays intricate reliefs with animals, abstract shapes, and symbolic motifs, often executed with a sense of proportion, depth, and realism that implies careful planning and significant skill. These artistic elements were not merely decorative, they communicated meaning, perhaps encoding spiritual beliefs, mythologies, or social hierarchies. The integration of artistic symbolism with massive stone construction illustrates a multidimensional intelligence, combining creativity, technical skill, and structural understanding to create monumental works that are simultaneously functional, aesthetic, and meaningful. Environmental adaptation was essential to the success and longevity of Göbekli Tepe. The builders selected a site with natural elevation for visibility, strategic defense, and symbolic significance, while the stone used was locally sourced for durability and ease of shaping. Drainage and soil considerations were likely addressed to prevent erosion and structural failure, ensuring the enclosures would remain stable over millennia. The selection of materials, site planning, and structural execution reflect a nuanced understanding of geology, hydrology, and environmental forces. The site's endurance for over 11,000 years is a testament to the precision, foresight, and practical knowledge of its builders, highlighting their empirical mastery of both natural and built environments. The integration of engineering, symbolism, and social function at Göbekli Tepe provides insight into the cognitive and cultural capacities of early humans. These hunter-gatherer communities were capable of conceptualizing monumental structures, coordinating large-scale labor, embedding symbolic meaning, and manipulating materials with extraordinary precision. Such accomplishments require advanced reasoning, planning, and technical experimentation, suggesting that the roots of human ingenuity extend far deeper into prehistory than previously assumed. Göbekli Tepe compels a re-evaluation of the development of technology, architecture, and societal organization, demonstrating that complex problem-solving and collaborative construction were present long before the advent of agriculture, metallurgy, or written records. The site's construction techniques reveal remarkable engineering ingenuity. Pillars were quarried, shaped, and erected in precise positions using tools available at the time, likely made of flint or other hard stone. Their weight, balance, and positioning required careful calculation, empirical testing, and teamwork. Horizontal lintels were placed atop vertical pillars with stability ensured through subtle adjustments and interlocking features. These methods demonstrate that the builders possessed both practical knowledge of mechanics and an experimental approach to construction, achieving structural stability through observation, iteration, and skilled labor rather than formal mathematical theory. Göbekli Tepe also reshapes our understanding of the relationship between ritual and technology. The scale of construction suggests that spiritual or communal motivations were strong enough to organize labor and resources on an unprecedented scale. Monumental architecture may have preceded agriculture rather than emerging as a result of it, implying that the desire for ritual expression and social cohesion could have driven technological and engineering advancements. This challenges linear models of societal development, suggesting that the cognitive and organizational abilities required for complex construction existed in human societies long before sedentary, agrarian life. The preservation of Göbekli Tepe offers invaluable insight into early human capability. The site's stone enclosures, carvings, and structural alignments remain remarkably intact, allowing researchers to study the engineering, artistic, and organizational methods employed by these early builders. Modern engineering analysis reveals that the structures were not only durable but intentionally designed to endure, incorporating principles of weight distribution, stability, and environmental adaptation that are still studied and admired today. The survival of these monuments for over 11 millennia is a powerful testament to the foresight, skill, and ingenuity of prehistoric societies. Ultimately, Göbekli Tepe is more than an archaeological site, it is a monumental expression of early human intelligence, creativity, and technical capability. Its massive pillars, intricate carvings, and precisely aligned enclosures illustrate a society capable of complex problem-solving, environmental adaptation, and social coordination on a scale previously thought impossible for hunter-gatherer communities. The site challenges long-held assumptions about the origins of civilization, suggesting that the roots of engineering, architecture, and collective human ingenuity extend far deeper into prehistory than traditional narratives allow. Göbekli Tepe stands as a timeless reminder of humanity's capacity for innovation, vision, and monumental achievement even in the absence of formalized technology or centralized governance. From the transportation of massive stones to the precise geometric alignment of circular enclosures, from the artistic expression carved into each pillar to the organization of labor among a pre-agricultural society, Göbekli Tepe reveals a civilization that combined observation, experimentation, and collective effort to achieve extraordinary results. Its construction represents an unparalleled integration of engineering, artistry, symbolism, and social coordination, demonstrating that complex human achievement is not confined to agrarian or urban societies. Göbekli Tepe compels a profound reconsideration of the timeline of human development, revealing that the capacity for monumental engineering, architectural sophistication, and social organization emerged thousands of years earlier than previously imagined, leaving a legacy that continues to inspire, challenge, and awe modern scholars and engineers alike. Far to the north, in the rugged and frigid terrain of Scandinavia, the megalithic site of Ailes stones in southern Sweden presents a unique and enduring mystery that continues to baffle archaeologists, historians, and engineers alike. Comprising a stone ship formation over 67 meters in length, Ailes stones dates to somewhere between 1400 and 500 BCE, though its precise origins and purpose remain subjects of intense debate. The alignment, scale, and construction of this monument suggest not only a sophisticated understanding of geometry and spatial planning but also a deep connection to astronomy and ritual practice. Despite the comparatively small stones, ranging from 1 to several tons, their deliberate arrangement into a massive, coherent ship-like outline indicates a level of technical knowledge, social coordination, and symbolic insight far beyond what might be expected of Iron Age Scandinavian communities. Ailes stones challenges our assumptions about prehistoric engineering, illustrating that human societies in diverse regions of the world developed complex methods of monument building, integrating technical skill, celestial observation, and cultural meaning in ways that continue to inspire awe and investigation. The configuration of Ailes stones immediately distinguishes it from other megalithic monuments. The stones are arranged in a precise ship-like outline, with a clear prow, stern, and curved sides, demonstrating a conceptual and geometric sophistication that is remarkable for its time. Each stone was deliberately selected and placed, suggesting that the builders possessed both a vision for the overall form and a practical understanding of how to realize it on the ground. The uniformity in spacing, orientation, and height across the structure implies meticulous planning, likely involving preliminary surveys, alignment techniques, and an understanding of proportion. The monument's deliberate shape and size would have required coordinated labor and significant organizational capacity, demonstrating that prehistoric societies were capable of planning and executing large-scale projects with aesthetic, symbolic, and technical precision. Archaeological studies suggest that Ailes stones functioned not merely as a burial site but also as a celestial observatory. Several of the stones appear to align with solar events, including solstices and equinoxes, hinting that the monument was used to mark the passage of time, track seasonal changes, and possibly guide agricultural or ritual cycles. The ability to translate celestial observations into a large-scale terrestrial design reflects an advanced understanding of astronomy, geometry, and spatial reasoning. This dual function, as both a ritual monument and a tool for observing celestial patterns, reveals a culture capable of merging scientific knowledge with symbolic and ceremonial practice, embodying a sophisticated worldview that integrated human activity, cosmology, and environmental awareness. The labor and engineering involved in constructing Aile's stones also highlight the ingenuity of its builders. Though the stones are smaller than some of the massive megaliths found elsewhere in Europe or the Middle East, many weigh several tons, and their transportation, shaping, and positioning would have required significant effort and planning. Without wheeled vehicles or advanced machinery, the builders likely relied on human strength, sledges, levers, and simple mechanical principles to maneuver each stone into its designated position. Coordinating such a project would have necessitated a clear hierarchy of labor, task specialization, and meticulous oversight, suggesting a level of social organization that allowed for large-scale cooperative work despite the absence of a centralized state or formal bureaucracy. Environmental adaptation was crucial to the enduring success of Aile's stones. Constructed on a slight rise overlooking the surrounding landscape, the monument takes advantage of natural topography for visibility, stability, and drainage. The site is positioned in such a way that seasonal sun and shadow patterns accentuate its alignment with celestial events, demonstrating that the builders considered environmental and astronomical factors in tandem. The placement and orientation of each stone reveal an empirical understanding of terrain, gravitational stability, and environmental exposure, ensuring the monument's resilience against the harsh Scandinavian climate, including freezing winters, thawing cycles, and heavy precipitation. Such foresight reflects a sophisticated level of engineering that integrates environmental science, observation, and long-term planning. The symbolism embedded in Aile's stones further underscores the intellectual and cultural sophistication of its creators. The ship-like form may have been intended to represent a vessel for the dead, a spiritual passage into the afterlife, or a metaphor for journey and transition, ideas common in Norse cosmology and later Scandinavian myth. Each stone serves a dual purpose, as a structural element in the overall form and as a symbolic marker in a larger narrative or ritual context. The careful alignment of stones, combined with the monument's integration with celestial phenomena, suggests that the builders sought to create a holistic experience that combined functional, aesthetic, and spiritual considerations into a single monumental construct. This integration of multiple layers of meaning demonstrates a nuanced capacity for abstract thought, planning, and artistic expression, challenging assumptions that prehistoric engineering was purely utilitarian. Aile's stones also reflects the capacity of ancient societies to synthesize observation, experimentation, and practical engineering into enduring structures. The precise placement of each stone required an understanding of balance, weight distribution, and spatial relationships, as well as the ability to apply trial-and-error methods to ensure long-term stability. The construction techniques employed reveal empirical problem-solving, for instance, slight adjustments in the angle, depth, or orientation of stones likely compensated for ground instability or environmental pressures. The builder's ability to integrate these solutions seamlessly into a coherent geometric and symbolic design highlights their technical ingenuity and adaptive intelligence. Astronomical alignment, a key feature of Aile's stones, required careful observation and recording over multiple years. Builders would have needed to track the movement of the sun and other celestial bodies, understand seasonal cycles, and translate these patterns into precise spatial arrangements on the ground. This process indicates not only cognitive sophistication but also collaborative planning and intergenerational knowledge transfer, suggesting that the techniques and insights required to construct the monument were preserved, refined, and passed down over generations. Such continuity in observational and technical knowledge underscores the depth of understanding early societies possessed regarding both the cosmos and its application to terrestrial design. The social and organizational aspects of Aile's stones cannot be understated. Mobilizing a workforce capable of transporting, placing, and shaping multiple multi-ton stones required complex coordination. Leadership structures, division of labor, and logistical support for feeding, housing, and sustaining workers would have been necessary for the project's completion. The monument reflects an advanced ability to orchestrate collective effort for symbolic, spiritual, or social objectives, illustrating that social cohesion and shared purpose were critical components of monumental construction in prehistoric Scandinavia. This insight challenges the notion that engineering prowess necessarily depends on urbanization, formal governance, or technological advancement alone. Material selection at Ailes stones demonstrates empirical understanding and practical wisdom. Stones were chosen not only for their size and shape but also for durability, stability, and suitability for carving or placement. Builders would have assessed each boulder for its load-bearing properties and resistance to environmental stresses, integrating these considerations into the overall design. The combination of material science, structural understanding, and symbolic placement underscores the multidimensional intelligence of the society responsible for the monument. Every stone represents a deliberate choice reflecting both technical judgment and cultural intention, revealing an integration of function, durability, and meaning rarely acknowledged in prehistoric engineering. Ailes stone stands as a testament to the fusion of practical knowledge, social organization, and symbolic expression. The alignment, scale, and form reflect a civilization that could conceptualize complex geometric patterns, coordinate substantial human labor, and integrate ritual significance into physical structures. Unlike purely utilitarian constructions, the site demonstrates that prehistoric societies were capable of creating monuments that were simultaneously functional, durable, and deeply meaningful. This multidimensional approach reflects advanced cognitive abilities, highlighting the capacity for abstract thought, strategic planning, and the synthesis of observation, symbolism, and practical engineering. The resilience of Ailes stones over millennia further emphasizes the skill and foresight of its builders. Despite exposure to the harsh Scandinavian climate, including freezing winters, thaw cycles, and heavy precipitation, the monument remains remarkably intact. Its survival is a testament to the empirical methods employed in design and construction, including careful weight distribution, site selection, and environmental adaptation. The enduring presence of the site invites continued study, offering insights into prehistoric engineering, astronomy, social organization, and symbolic expression that remain relevant to modern disciplines of archaeology, architecture, and engineering. Ultimately, Ailes stones challenges conventional narratives about the technological and organizational capabilities of prehistoric societies. Its construction demonstrates that early humans possessed not only the technical knowledge to manipulate heavy materials but also the social and cognitive skills necessary to coordinate large-scale projects, integrate astronomical observation, and embed symbolic meaning into monumental forms. The site exemplifies a sophisticated understanding of geometry, structural stability, environmental forces, and celestial cycles, all realized without the technological advantages of later civilizations. Ailes stones compels us to recognize that complex engineering, abstract reasoning, and cultural sophistication emerged independently in diverse regions of the prehistoric world, reflecting a shared capacity for human ingenuity across time and geography. From the precise arrangement of multi-ton stones to the careful alignment with celestial events, from the integration of symbolic meaning to the orchestration of labor and resources, Ailes stones reveals a prehistoric society capable of extraordinary technical, cognitive, and organizational achievement. It stands as a monumental expression of human ingenuity, bridging practical engineering, astronomical knowledge, and cultural symbolism into a coherent, enduring structure. The site challenges assumptions about the origins of monumental construction, demonstrating that prehistoric communities possessed the insight, skill, and coordination necessary to create works of lasting significance. Ailes stones continues to inspire awe, inviting reflection on the capabilities of ancient societies and the enduring legacy of human creativity, precision, and vision. In the remote and arid expanses of northern Chile, within the desolate Atacama Desert, lies the enigmatic site of the Nazca Lines, a monumental testament to the ingenuity, precision, and symbolic sophistication of the ancient Nazca civilization. Stretching across more than 450 square kilometers, these geoglyphs comprise hundreds of figures, ranging from simple lines and geometric shapes to intricate depictions of animals, humans, and imaginary beings, some measuring hundreds of meters in length. The scale, precision, and orientation of the Nazca lines are staggering, considering they were created between 500 BCE and 500 CE by a pre-Columbian society without access to modern surveying tools, aerial perspectives, or advanced engineering instruments. The geoglyphs, etched into the desert floor by removing reddish-brown iron oxide-coated pebbles to reveal lighter-colored earth beneath, have endured for centuries due to the region's extremely dry climate, minimal wind, and stable landscape. Yet their purpose, method of construction, and extraordinary accuracy continue to provoke debate and wonder among archaeologists, engineers, and researchers, challenging assumptions about the technical capabilities and cultural motivations of ancient civilizations. The first aspect that strikes any observer is the extraordinary scale and precision of the figures. Some of the largest geoglyphs, such as the hummingbird, condor, or monkey, stretch over 300 meters in length, yet their proportions remain accurate and visually coherent when viewed from above, despite the absence of any known means for aerial observation. Achieving such scale required not only careful planning but also an advanced understanding of geometry, measurement, and perspective. Researchers have proposed that the Nazca people used a combination of grids, stakes, ropes, and line-of-sight calculations to map out these enormous designs, effectively creating a system of large-scale surveying that allowed them to reproduce intricate figures on a monumental scale. The precision achieved without modern instruments indicates a sophisticated empirical knowledge of spatial relationships and proportionality, revealing that the Nazca civilization possessed both technical skill and visionary planning. The creation of the Nazca lines also required an intimate understanding of materials and environmental conditions. The desert surface, covered in a layer of reddish pebbles, was carefully cleared to expose the lighter soil underneath, producing a stark visual contrast that endures to this day. The builders would have needed to account for the natural slope, contours, and potential erosion of the landscape, adjusting their designs to maintain visual integrity over large distances. Evidence suggests that the Nazca employed drainage knowledge, subtle grading, and precise stone removal techniques to stabilize the lines, preventing collapse or distortion. This attention to environmental adaptation reflects a level of engineering foresight that is particularly remarkable for a society without formalized engineering education or mechanized tools. The alignment of the Nazca lines adds another layer of complexity and sophistication. Many lines and figures are oriented in relation to astronomical events, including solstices, equinoxes, and the positions of certain celestial bodies. Some researchers posit that the geoglyphs functioned as a calendrical system, guiding agricultural practices, ceremonial events, and religious observances based on solar, lunar, and stellar cycles. The ability to translate celestial observation into precise terrestrial alignments indicates an advanced understanding of astronomy and its practical applications, merging spiritual, agricultural, and technical knowledge into a coherent system. The careful integration of cosmic and terrestrial considerations underscores the multidimensional thinking and planning that defined Nazca society. Labor organization and project management were critical to the creation of these massive geoglyphs. Constructing figures of such scale and precision would have required coordinated teams of workers, clear hierarchical oversight, and a division of labor for surveying, excavation, and maintenance. The process likely involved preliminary design sketches, the use of measuring ropes and stakes, and iterative verification of proportions to ensure fidelity to the intended patterns. This indicates that the Nazca possessed not only the technical understanding to execute large-scale projects but also the social and administrative structures to mobilize human labor effectively. Such coordination demonstrates a sophisticated ability to plan, communicate, and sustain complex projects over extended periods. The symbolic and ritual dimensions of the Nazca lines are equally compelling. Many geoglyphs depict animals with profound cultural significance, such as the hummingbird, which may represent fertility, the monkey as a symbol of agility or playfulness, or the spider potentially linked to agricultural cycles. Other figures represent human-like or fantastical forms, whose meanings remain speculative but likely reflect religious or cosmological beliefs. The sheer number and diversity of designs suggest that the Nazca lines were part of an elaborate ritual landscape, where the act of creation, the alignment with celestial bodies, and the visibility from elevated viewpoints or hilltops contributed to their spiritual and social significance. The geoglyphs were not merely artistic expressions, they were active components of a cultural system that integrated technology, symbolism, and communal identity. The technical methodology behind the geoglyphs also reveals ingenuity that defies conventional assumptions. Researchers have demonstrated that simple tools, wooden stakes, ropes, and careful observation, could produce remarkably precise figures when combined with rigorous planning and iterative correction. Lines were straight over kilometers, geometric shapes were accurately proportioned, and even large animal figures maintained correct anatomical ratios. This indicates that the Nazca developed empirical methods of measurement, scaling, and verification that allowed them to execute designs far larger than any individual could view or control in its entirety. The ability to conceptualize a large-scale image and translate it into precise, ground-level execution demonstrates both advanced cognitive capacity and sophisticated applied engineering knowledge. Water management and environmental awareness played a supporting role in the geoglyphs' preservation. The Atacama Desert is one of the driest places on Earth, and the lack of significant rainfall has ensured the survival of the lines for centuries. However, the Nazca were clearly aware of the desert's conditions and likely designed their lines to minimize disruption from wind, occasional rain, and shifting sands. Some researchers suggest that the figures were reinforced periodically, with maintenance crews carefully realigning stones and clearing debris to ensure longevity. This indicates an understanding of environmental dynamics and a commitment to preserving monumental works over time, reflecting a long-term perspective in both technical execution and cultural planning. The cultural and social implications of the Nazca lines are profound. Constructing geoglyphs of such scale implies a society capable of collaborative organization, shared vision, and collective effort. The combination of technical precision, astronomical alignment, symbolic meaning, and logistical coordination suggests that the Nazca were not merely subsistence farmers but a society with complex social, religious, and scientific knowledge. Monumental projects like these geoglyphs likely serve to reinforce communal identity, social cohesion, and spiritual beliefs, demonstrating that engineering and architecture were deeply intertwined with cultural practice. Artistry and aesthetic consideration were equally integrated into the construction process. Each geoglyph was designed to create visual impact, maintain proportional accuracy, and convey symbolic meaning. Some figures incorporate intricate details, such as elongated limbs or exaggerated features, suggesting a nuanced understanding of form and perception. The integration of artistry with engineering demonstrates a sophisticated multidisciplinary approach, where practical, aesthetic, and spiritual concerns were harmoniously balanced. This multidimensionality reflects a society capable of complex problem-solving, imaginative vision, and technical execution at a scale rarely achieved in pre-industrial civilizations. The enduring impact of the Nazca lines lies in their ability to blend functionality, spirituality, and technical mastery. They are simultaneously cultural expressions, astronomical instruments, and engineering feats. Their survival over centuries, with minimal degradation, is a testament to both the durability of the construction methods and the foresight of the designers in anticipating environmental conditions. The integration of large-scale geometry, celestial observation, labor coordination, and symbolic expression underscores the holistic intelligence of the Nazca civilization. Ultimately, the Nazca lines challenge modern assumptions about the capabilities of ancient societies. They reveal a civilization capable of conceptualizing and executing monumental works that required empirical observation, engineering skill, spatial reasoning, and social coordination. The geoglyphs illustrate that technological and cultural sophistication can emerge in societies without metal tools, written language, or centralized political structures, emphasizing the universality of human ingenuity. Aleph-like in their vastness, the lines demonstrate that early civilizations could manipulate landscapes to create works of profound technical, symbolic, and aesthetic significance. From the vast geometric patterns to the intricately detailed animal figures, from astronomical alignment to environmental adaptation, the Nazca Lines provide a window into a civilization that combined observation, engineering, artistry, and ritual practice into an enduring monumental landscape. They challenge our understanding of the timeline of human technological and cultural development, revealing that pre-Columbian societies were capable of complex planning, precise execution, and multidimensional thinking. The Nazca Lines endure not only as a marvel of ancient engineering but also as a testament to human creativity, vision, and the capacity to merge technical skill with cultural and spiritual expression, leaving a legacy that continues to captivate, inspire, and challenge our understanding of what ancient civilizations could achieve. Deep in the heart of the Indian subcontinent, along the banks of the Nirmada and other rivers, stand the massive stone structures of the ancient city of Mohenjo-Daro, one of the principal settlements of the Indus Valley civilization. Flourishing between 2600 and 1900 BCE, this city demonstrates an unparalleled level of urban planning, engineering sophistication, and civic organization for its time. Unlike many contemporaneous civilizations, Mohenjo-Daro was constructed according to a standardized grid layout, with streets running in perfect orthogonal alignment, residential blocks carefully planned, and drainage systems engineered to an extraordinary degree of precision. Its urban fabric reflects a civilization that understood not only the functional necessities of densely populated living but also how to integrate water management, waste removal, and structural durability into a cohesive, enduring system. The city challenges assumptions about early urban engineering, as it exhibits levels of technical expertise and civic foresight that continue to astonish modern architects, engineers, and historians. The most striking feature of Mohenjo-Daro is its meticulous urban planning. Streets were laid out in a rectilinear grid, with major avenues intersecting at right angles to form orderly blocks. Residential and commercial structures were arranged systematically, with careful consideration for ventilation, light, and accessibility. Houses were constructed with standardized baked bricks of uniform dimensions, allowing for structural consistency and ease of construction. Many homes featured multiple rooms, internal courtyards, and private wells, highlighting an understanding of spatial organization that maximized both utility and comfort. The uniformity in design suggests centralized planning and a strong tradition of civic regulation, indicating that the inhabitants of Mohenjo-Daro possessed not only technical knowledge but also social and administrative structures capable of implementing large-scale urban projects with remarkable precision. Integral to the functionality of Mohenjo-Daro was its sophisticated water management system. The city's streets incorporated covered drains, manholes, and channels that connected homes to centralized sewage networks, ensuring that waste was efficiently removed from residential areas. Wells were strategically located to provide access to fresh water, and some structures featured advanced systems for water storage and distribution. The integration of hydraulic engineering into everyday urban life reflects a deep understanding of fluid dynamics, sanitation, and public health long before these concepts became widespread elsewhere in the ancient world. The durability of these systems, many of which remain partially intact after thousands of years, demonstrates the engineer's foresight and mastery of materials, construction methods, and environmental adaptation. Mohenjo-Daro's monumental architecture further reveals the technical capabilities of the Indus Valley civilization. The Great Bath, a massive public water tank measuring approximately 12 by 7 meters, is perhaps the most iconic example. Constructed with finely fitted bricks and sealed with bitumen to prevent water leakage, it demonstrates advanced knowledge of waterproofing, load distribution, and maintenance. Surrounding the bath were dressing rooms and platforms, indicating that it served both functional and ritualistic purposes. The construction required precise planning to ensure stability and impermeability, highlighting a combination of empirical engineering, material science, and urban design that is extraordinary for a city of this era. Residential buildings at Mohenjo-Daro reveal additional layers of technical and cultural sophistication. Many homes were constructed with multiple stories, flat roofs, and internal courtyards, showcasing an understanding of load-bearing principles, ventilation, and climate adaptation. Bricks were baked to uniform dimensions, allowing for modular construction and ease of assembly. The interiors often featured niches, hearths, and drainage channels, reflecting careful consideration of practical needs. Even minor elements, such as the placement of staircases or the alignment of windows, indicate a systematic approach to building that maximized functionality, comfort, and durability. This level of standardization and technical knowledge is remarkable, especially given the absence of formalized engineering education or written construction manuals. The streets and marketplaces of Mohenjo-Daro further illustrate the civilization's mastery of urban design. Broad avenues facilitated movement and trade, while smaller lanes connected residential blocks efficiently. The careful placement of granaries, warehouses, and public buildings suggests a sophisticated understanding of logistics, resource distribution, and economic planning. Public spaces were designed for communal interaction, ceremonial functions, and commercial activity, reflecting a holistic approach to urban life that integrated social, economic, and technical considerations. The city's spatial organization demonstrates that early urban planners could balance human needs with environmental constraints, creating a settlement that was both functional and resilient. Engineering innovation extended to Mohenjo-Daro's construction techniques. Bricks were manufactured with remarkable uniformity, and the city's buildings were often reinforced with buttresses and foundations designed to withstand seasonal flooding. Some homes featured elevated platforms to protect against water infiltration, while drainage systems were carefully graded to ensure efficient flow. These design choices reflect a comprehensive understanding of environmental pressures, material properties, and long-term maintenance needs. The builder's ability to anticipate challenges and implement durable solutions underscores the advanced empirical knowledge that underpinned the city's construction. Sanitation and public health were central to Mohenjo-Daro's engineering achievements. The integration of covered drains, private wells, and centralized sewage networks minimized contamination and facilitated hygiene. Manholes allowed for access and maintenance, demonstrating that the engineers not only considered immediate functionality but also long-term serviceability. The city's planning suggests that health and environmental control were priorities, reflecting a society capable of systematic problem-solving and long-term urban management. This level of sophistication challenges assumptions that ancient cities were rudimentary or reactive in their design, revealing instead a civilization that applied engineering knowledge to enhance quality of life. Mohenjo-Daro's social organization was instrumental in its engineering accomplishments. Coordinating large-scale brick production, construction, and urban layout required a centralized system of oversight, labor allocation, and resource management. Skilled artisans, laborers, and planners worked together to execute complex designs, indicating a high degree of social cohesion and collaborative capacity. The uniformity in construction standards across the city suggests institutionalized practices, training systems, and regulatory mechanisms, highlighting the integration of technical skill, administrative control, and communal cooperation. This organizational sophistication allowed Mohenjo-Daro to achieve monumental urban and engineering feats without the hierarchical state structures commonly associated with later civilizations. The integration of environmental adaptation, urban planning, and engineering innovation is particularly evident in Mohenjo-Daro's handling of seasonal flooding. The city was strategically positioned on elevated terraces to minimize flood risk, yet drainage systems were meticulously designed to manage water flow during the monsoon season. Roads were sloped, channels were precisely graded, and buildings were constructed with elevated floors and watertight materials. This demonstrates not only technical knowledge but also a capacity for long-term observation, predictive planning, and environmental control. The Indus Valley engineers effectively harmonized natural forces with urban infrastructure, ensuring the city's resilience and sustainability. Trade and logistics were also central to Mohenjo-Daro's technical sophistication. The city was a hub for commerce, connecting surrounding regions through an extensive network of roads, waterways, and storage facilities. Granaries were carefully designed to store surplus crops, while warehouses facilitated the distribution of goods. The standardization of brick sizes, weights, and construction practices across multiple sites in the Indus Valley indicates that knowledge transfer and quality control were institutionalized, enabling consistent engineering practices over large distances. This level of logistical planning underscores the civilization's understanding of both technical and organizational systems. Mohenjo-daro's craftsmanship extended to artistic and functional elements integrated within its engineering framework. Terracotta figurines, seals, and inscriptions were often incorporated into residential and public spaces, revealing a society that valued aesthetic expression alongside practical construction. The combination of functional design with symbolic or artistic elements demonstrates a multidimensional intelligence capable of addressing technical, social, and cultural requirements simultaneously. This integration reflects a holistic approach to urban engineering, where utility, durability, and cultural expression coexist harmoniously. The durability of Mohenjo-daro structures is a testament to the empirical knowledge of its builders. Despite millennia of exposure to flooding, seismic activity, and environmental changes, many buildings, streets, and drainage systems remain remarkably intact. The precise alignment of streets, the stability of multi-story homes, and the resilience of brickwork indicate that the engineers employed tested methods, iterative refinement, and a deep understanding of materials to ensure longevity. This foresight underscores the civilization's capacity for long-term planning and its commitment to creating enduring infrastructure. Ultimately, Mohenjo-daro exemplifies the convergence of engineering, urban planning, and social organization in one of the world's earliest complex civilizations. Its grid layout, standardized construction, water management systems, and durable buildings reflect a society capable of integrating multiple domains of knowledge into a coherent, functional, and sustainable urban environment. The city challenges modern perceptions of early urban development, demonstrating that engineering excellence, administrative capacity, and environmental adaptation were achievable long before the rise of well-documented classical civilizations. From meticulously aligned streets to advanced drainage networks, from modular brick construction to the integration of public, residential, and ceremonial spaces, Mohenjo-daro showcases a civilization that mastered the art of urban engineering with remarkable foresight, precision, and social coordination. Its enduring legacy highlights the sophisticated technical, organizational, and cultural capabilities of the Indus Valley civilization, providing a window into how early humans combined observation, empirical knowledge, and collaborative effort to create urban landscapes that were functional, resilient, and profoundly innovative. The city stands as a testament to human ingenuity, foresight, and the capacity to harmonize engineering, environment, and society into structures that continue to inspire awe and study thousands of years after their construction. High on the windswept plains of southern Mexico and Guatemala, the ancient city of Teotihuacan stands as one of the most extraordinary examples of urban planning, architectural precision, and engineering sophistication in the pre-Columbian world. Flourishing between 100 BCE and 550 CE, Teotihuacan became the largest city in the Americas during its height, housing an estimated 125,000 or more inhabitants. Its scale, layout, and monumental structures reveal a civilization that mastered construction, urban organization, and infrastructure at a level that challenges our understanding of ancient engineering. The city's central avenues, temples, pyramids, and residential compounds demonstrate not only technical skill but also social, cultural, and cosmological awareness, illustrating a holistic approach to urban and architectural design rarely matched in antiquity. The achievements of Teotihuacan continue to inspire archaeologists, architects, and engineers, raising profound questions about how such sophistication was attained without modern machinery, standardized blueprints, or written records detailing construction methods. The urban layout of Teotihuacan is immediately striking in its scale and symmetry. The city is organized along the broad, central Avenue of the Dead, which stretches over 2 kilometers and is flanked by massive pyramidal structures, plazas, and residential complexes. Streets are arranged in a precise grid pattern, oriented with remarkable astronomical accuracy, likely aligned to celestial phenomena such as solstices and equinoxes. This meticulous planning facilitated movement, trade, and ceremonial processions, reflecting a deep understanding of urban dynamics, spatial geometry, and social organization. Residential and administrative compounds were systematically laid out to optimize access, security, and functional efficiency, demonstrating that Teotihuacan's planners possessed advanced cognitive and organizational abilities capable of orchestrating large-scale urban development with remarkable foresight and precision. Monumental architecture at Teotihuacan showcases extraordinary engineering skill. The Pyramid of the Sun, one of the largest structures in the Americas, rises over 65 meters above the surrounding plain and is composed of millions of carefully cut stones and adobe bricks. Its construction required precise leveling, layering, and stabilization techniques to ensure long-term durability. The Pyramid of the Moon, slightly smaller but equally imposing, aligns with the nearby Cerro Gordo mountain, creating a visual and symbolic axis that reflects both urban and cosmological considerations. The builder's ability to construct such massive structures, transport materials over significant distances, and ensure stability without advanced machinery is a testament to their mastery of empirical engineering, labor organization, and spatial planning. Residential and administrative compounds at Teotihuacan further reveal the civilization's technical and social sophistication. Multi-story apartment complexes housed hundreds of inhabitants and incorporated communal courtyards, storage areas, and service facilities. These structures demonstrate an understanding of load distribution, ventilation, and urban density management. Streets and alleys connecting these compounds were carefully planned to optimize circulation and access, while water collection and drainage systems ensured sanitation and sustainability. The modular construction techniques employed suggest standardized practices, quality control, and the capacity for efficient labor coordination, indicating that Teotihuacan functioned as both a highly organized civic center and a thriving urban environment. The construction of Teotihuacan required extraordinary logistical planning and resource management. Millions of tons of stone, adobe, and other materials were quarried, transported, and assembled, often over long distances from surrounding hills and riverbeds. Without wheeled vehicles or draft animals, the builders likely relied on human labor, sledges, ramps, and coordinated teams to move and position materials with remarkable precision. Organizing such massive efforts necessitated hierarchical oversight, specialized labor divisions, and detailed project planning. The scale and precision of construction highlight a sophisticated understanding of mechanics, leverage, and empirical problem-solving, demonstrating that Teotihuacan's engineers could execute projects of unprecedented complexity in the ancient world. Water management at Teotihuacan reflects advanced hydraulic engineering. The city incorporated reservoirs, canals, and drainage systems to supply potable water and manage rainfall. Aqueducts and carefully graded channels ensured the distribution of water across the urban landscape while preventing flooding or waterlogging. This integration of hydrology into urban design illustrates an understanding of environmental forces, material behavior, and long-term sustainability. Engineers had to account for variations in terrain, water pressure, and seasonal fluctuations, employing empirical knowledge and iterative problem-solving to create systems that remained functional for centuries. The sophistication of these solutions underscores the technical expertise and environmental awareness of Teotihuacan's planners. Astronomical and cosmological knowledge was embedded into Teotihuacan's urban design. The city's orientation, alignments of major pyramids, and placement of ceremonial spaces correspond to solar, lunar, and planetary cycles. The Pyramid of the Sun, for instance, aligns with the point on the horizon where the sun sets on specific days of the year, suggesting its use in ritual and calendrical observation. Ceremonial plazas, temples, and residential compounds were arranged to reflect both cosmological beliefs and social hierarchy, integrating technical construction with spiritual and symbolic considerations. This fusion of science, ritual, and urban planning reflects a society capable of sophisticated abstract thought and the practical application of astronomical knowledge in large-scale engineering projects. Teotihuacan's monumental murals and artistic expressions also reveal technical mastery. Elaborate murals depicting deities, mythological scenes, and symbolic motifs were integrated into public and private structures, demonstrating the civilization's ability to harmonize art with architecture. The execution of these murals required precise planning, pigment preparation, and understanding of wall surfaces and environmental conditions to ensure durability. Their presence within structurally sound buildings underscores the multidimensional intelligence of the society, which integrated engineering, aesthetics, and cultural expression into a cohesive urban environment. Labor organization was a critical component in realizing Teotihuacan's engineering feats. Coordinating tens of thousands of workers to construct monumental pyramids, residential complexes, and infrastructure systems required a highly organized social structure. Tasks were likely divided according to skill, including quarrying, transport, masonry, and artistic decoration, all synchronized under centralized oversight. Resource allocation, food provisioning, and logistical support for such large-scale operations necessitated advanced planning and administration, revealing a society with sophisticated governance, social cohesion, and the ability to execute complex engineering projects on an unprecedented scale. Environmental adaptation was central to Teotihuacan's enduring success. The city's location on a broad, arid plateau required careful management of water, climate, and terrain. Elevated foundations, drainage channels, and carefully selected construction materials ensured stability in the face of seismic activity, seasonal rainfall, and temperature extremes. The builder's ability to integrate engineering solutions with environmental conditions demonstrates empirical knowledge, foresight, and iterative problem-solving, allowing the city to thrive in a challenging landscape for centuries. Teotihuacan exemplifies how ancient civilizations achieved resilience and sustainability through careful observation, planning, and engineering innovation. The integration of monumental architecture, urban planning, and social organization at Teotihuacan reflects a holistic understanding of engineering that extends beyond simple construction. Every street, pyramid, and plaza was part of a larger system combining functionality, symbolic meaning, and environmental adaptation. Pyramids served not only as ceremonial centers but also as navigational anchors and social markers, while residential complexes accommodated population density efficiently and sustainably. The careful orchestration of space, materials, and labor demonstrates a civilization capable of complex problem-solving, long-term planning, and the integration of diverse forms of knowledge into coherent and enduring urban landscapes. Trade and economic infrastructure were essential to Teotihuacan's construction and maintenance. The city's location facilitated commerce with distant regions, requiring storage facilities, marketplaces, and transport routes integrated into the urban grid. Standardization of construction materials, particularly bricks and stone, suggests centralized control, quality assurance, and efficient supply chains capable of sustaining large-scale building projects. The ability to coordinate resource extraction, distribution, and construction across such a vast urban area highlights the technical, organizational, and engineering sophistication of Teotihuacan's planners. The durability and legacy of Teotihuacan testify to the precision and foresight of its engineers. Despite centuries of natural wear, seismic activity, and human intervention, the city's layout, pyramids, and infrastructure remain remarkably intact. The structural integrity of multi-tiered pyramids, the stability of streets and drainage networks, and the preservation of residential compounds all point to careful material selection, construction techniques, and long-term maintenance strategies. These achievements reveal an advanced empirical understanding of structural engineering principles, highlighting the city's ability to balance immediate functionality with enduring resilience. Ultimately, Teotihuacan exemplifies the convergence of technical knowledge, social organization, and cultural vision in one of the world's earliest complex civilizations. Its monumental pyramids, meticulously planned urban grid, sophisticated water management, and integration of artistic, astronomical, and symbolic elements reveal a society capable of combining empirical observation, engineering skill, and abstract thinking into monumental works that have endured for millennia. The city challenges conventional assumptions about pre-Columbian technological capabilities, demonstrating that advanced urban planning, monumental construction, and engineering innovation were achieved without written instructions, wheeled vehicles, or advanced machinery, relying instead on observation, labor coordination, and empirical problem-solving. From the precisely aligned pyramids to the extensive drainage systems, from modular residential compounds to astronomical orientation, Teotihuacan represents a civilization that integrated engineering, architecture, urban planning, and cultural expression at an extraordinary level. Its construction reflects deep technical understanding, organizational capacity, and environmental adaptation, while its symbolic and ceremonial components demonstrate advanced cognitive and spiritual sophistication. Teotihuacan endures as a monumental testament to human ingenuity, revealing that ancient civilizations were capable of complex, large-scale engineering, social coordination, and urban design that continues to inspire awe, challenge assumptions, and provide profound insight into the capabilities of early human societies. Far to the northeast of Europe, within the dense forests and frozen landscapes of Russia and Scandinavia, lie the enigmatic remnants of the Siberian and northern European megalithic structures, sites that continue to baffle archaeologists, engineers, and historians alike. Among them, the dolmens, stone circles, and earthen mounds scattered across regions such as Karelia, the Kola Peninsula, and the Ural Mountains demonstrate a level of technical skill, social organization, and symbolic sophistication that challenges conventional assumptions about prehistoric societies in these harsh environments. Dating back as far as 4000 BCE, these structures were constructed in areas with extreme climatic conditions, short building seasons, and limited resources, yet their creators achieved remarkable feats of engineering, geometry, and long-term durability. The purpose, methods, and meaning of these megalithic constructions remain subjects of ongoing debate, as they combine monumental scale, precise alignment, and symbolic motifs in ways that suggest a complex understanding of engineering, cosmology, and social cohesion long before the advent of formal civilizations. The sheer scale and precision of many of these northern structures are immediately striking. Dolmens, composed of massive horizontal capstones supported by vertical stones, were constructed to endure millennia of harsh weather, snow, and shifting soil. Some of the largest examples weigh several tens of tons, yet they were transported, positioned, and stabilized using only simple tools and human ingenuity. The precise placement of stones, often aligned with cardinal directions, celestial bodies, or topographical features, reflects an advanced understanding of geometry, weight distribution, and structural mechanics. In areas where metal tools were rudimentary and timber for levers was scarce, the builder's ability to manipulate enormous stones demonstrates a mastery of leverage, coordinated labor, and empirical engineering knowledge that continues to astonish modern researchers. Stone circles and ceremonial enclosures in these regions reveal a sophisticated integration of astronomy, geometry, and ritual function. Many of the circular arrangements align with solstices, equinoxes, or lunar cycles, suggesting that prehistoric communities observed celestial events closely and incorporated this knowledge into monumental construction. The precision required to align multi-ton stones over large distances indicates that the builders had developed methods for long-range surveying, careful measurement, and iterative adjustment. Such integration of empirical observation with symbolic or spiritual intent demonstrates a cognitive and cultural complexity that challenges assumptions that pre-agricultural or early agrarian societies in northern Europe were technologically primitive. Transporting the stones required ingenuity and coordinated effort. Without wheeled vehicles, draft animals, or advanced machinery, ancient builders relied on human strength, sledges, wooden rollers, ropes, and possibly earthen ramps to move massive boulders from quarries to their final locations. In icy or marshy terrain, builders would have had to adjust techniques seasonally, taking advantage of frozen surfaces for easier movement or employing counterweights and levers to raise stones into position. These methods require detailed knowledge of mechanical principles, friction, and force distribution, combined with the organizational capacity to manage teams of laborers over extended periods. Successfully erecting these monuments reflects both practical engineering expertise and sophisticated project management, highlighting the capabilities of prehistoric northern societies. The integration of environmental adaptation is evident throughout these northern megalithic sites. Builders carefully selected locations for visibility, drainage, and stability, often situating structures on elevated terrain or solid bedrock to mitigate the risks of flooding, erosion, or frost heaving. Foundations were sometimes reinforced with gravel, smaller stones, or timber to stabilize vertical supports, and the orientation of structures took into account prevailing winds, snow accumulation, and solar exposure. Such attention to environmental factors indicates empirical observation, planning, and iterative problem solving, revealing that these communities possessed not only technical skill but also a nuanced understanding of how to harmonize monumental construction with the challenges of a harsh and dynamic landscape. Symbolism and ritual were central to the purpose of these megaliths. Dolmens are widely believed to have functioned as burial chambers or ceremonial spaces, reflecting beliefs about death, the afterlife, and cosmological order. Stone circles and alignments may have served as gathering places for communal rituals, calendrical observances, or astronomical monitoring. The integration of symbolic meaning with precise engineering underscores the multidimensional intelligence of the builders, who combined practical construction knowledge with abstract conceptualization and cultural expression. This holistic approach suggests that monumental engineering in northern regions was not purely utilitarian but deeply intertwined with societal identity, spirituality, and communal cohesion. The construction techniques reveal remarkable experimentation and empirical learning. Builders demonstrated a sophisticated understanding of leverage, balance, and weight distribution, using inclined planes, counterweights, and incremental adjustments to position massive stones with precision. Vertical supports were carefully placed to bear the load of horizontal capstones, and minor adjustments were made to compensate for uneven terrain or variations in stone shape. The ability to achieve stability and alignment under these conditions reflects both practical observation and iterative refinement, indicating that northern prehistoric societies developed advanced engineering methods through hands-on problem-solving rather than formalized theory. Labor organization and social cohesion were crucial to these engineering feats. Constructing large megalithic structures required coordination among specialized teams of workers, including quarrymen, transporters, masons, and ritual overseers. Sustaining these efforts in regions with limited resources and harsh climates demanded logistical planning for food, shelter, and material supply. The ability to mobilize labor effectively suggests hierarchical oversight or communal organization capable of sustaining complex projects over years, if not decades. These social structures enabled prehistoric communities to execute ambitious architectural projects that combined technical precision, symbolic meaning, and long-term durability, revealing a sophisticated interplay of human intelligence, cooperation, and leadership. Astronomical knowledge was a key component in the design of northern megalithic monuments. Alignments with solstices, equinoxes, lunar cycles, and specific stellar configurations indicate that builders observed celestial events meticulously and incorporated them into construction planning. These alignments were not merely symbolic but could have served practical purposes, such as tracking seasonal changes, guiding agricultural cycles, or organizing communal rituals. Translating observations of the sky into precise terrestrial arrangements required careful measurement, planning, and iterative verification, highlighting the builder's empirical reasoning, observational skills, and capacity for long-term project management. Material selection further illustrates the builder's technical acumen. Stones were chosen for durability, weight, and suitability for shaping, with care taken to balance structural stability with symbolic and aesthetic considerations. In some cases, specific types of rock were selected for their color, texture, or resonance, suggesting an awareness of both functional and experiential qualities. The careful selection, transport, and positioning of stones reveal an understanding of mechanical properties, environmental resilience, and visual impact, reflecting an integration of engineering, artistry, and symbolic intention. The enduring nature of these northern megaliths attests to the empirical knowledge and foresight of their creators. Many structures have survived thousands of years, enduring freeze-thaw cycles, snow loads, and occasional seismic activity. Their stability is a testament to precise load distribution, foundation preparation, and adaptive construction methods. The fact that these monuments remain largely intact despite environmental challenges highlights the advanced engineering skills and long-term planning capabilities of prehistoric northern societies, challenging the perception that technological sophistication was exclusive to more temperate or urbanized regions. These northern megaliths also provide insight into societal cognition and abstract thought. The ability to conceptualize a multi-ton stone in a specific spatial arrangement, plan its transport and erection, and align it with celestial or topographical features indicates advanced problem-solving, spatial reasoning, and symbolic thinking. The integration of functionality, aesthetic proportion, and ritual significance reflects a multidimensional approach to construction, combining technical knowledge, social coordination, and cultural meaning in ways that are remarkably sophisticated for prehistoric societies. Ultimately, these northern megalithic structures redefine our understanding of prehistoric human capability. They demonstrate that communities in harsh and remote environments were not passive or technologically limited but capable of extraordinary feats of engineering, organization, and conceptualization. The combination of structural ingenuity, astronomical alignment, environmental adaptation, and symbolic meaning reveals a holistic intelligence that integrated empirical knowledge, practical skill, and cultural expression into monumental works that continue to inspire awe and inquiry. These sites challenge conventional chronologies and assumptions about the emergence of engineering expertise, indicating that technical innovation, social coordination, and abstract thinking were present across diverse regions far earlier than traditionally believed. From the precise alignment of massive stones to the integration of symbolic and ceremonial function, from environmental adaptation to labor organization and empirical problem-solving, the northern megaliths stand as enduring evidence of human ingenuity in the face of environmental and technological constraints. They exemplify a prehistoric understanding of geometry, mechanics, and astronomy combined with cultural, ritual, and social complexity. These monuments compel us to reconsider the capabilities of early societies, revealing that monumental engineering, technical sophistication, and abstract reasoning were not confined to well-documented urban civilizations but emerged independently in diverse and challenging landscapes, leaving a legacy that continues to inspire, challenge, and redefine our understanding of human history. In the remote deserts of Egypt, amidst the shifting sands and the relentless sun, stand the pyramids of Giza, colossal monuments that have fascinated and mystified humanity for millennia. Constructed during the 4th dynasty, around 2580 to 2560 BCE for the Great Pyramid of Khufu, these structures exemplify an extraordinary convergence of engineering, architectural ingenuity, and cultural ambition that continues to confound historians, engineers, and archaeologists. The precision, scale, and durability of these pyramids challenge our understanding of what ancient civilizations were capable of achieving, particularly considering the absence of advanced machinery, modern surveying tools, or large-scale mechanized labor. Beyond their monumental physical presence, the pyramids embody a sophisticated understanding of geometry, astronomy, logistics, and resource management, revealing that the builders possessed technical knowledge, organizational capacity, and visionary planning on a level comparable to the greatest engineering achievements of any era. The Great Pyramid of Khufu, the largest of the Giza pyramids, stands as a testament to human ingenuity. Originally reaching a height of approximately 146.6 meters, it comprises over 2.3 million limestone and granite blocks, each weighing between 2 and 70 tons. The precise arrangement of these stones, the near-perfect alignment with the cardinal points, and the remarkable level of geometric regularity in the pyramid's base illustrate that the builders possessed a sophisticated grasp of surveying, measurement, and construction techniques. Achieving such alignment over a base that spans more than 230 meters per side would have required meticulous observation, iterative verification, and advanced knowledge of geometry, particularly considering the technological limitations of the time. The precision with which the stones were cut, fitted, and placed ensures structural stability that has endured for over 4 millennia, underscoring the empirical engineering expertise of the ancient Egyptians. The construction process of the Great Pyramid reflects not only technical skill but also an advanced understanding of labor organization and project management. Moving and positioning millions of heavy stones required careful planning, coordinated effort, and sustained workforce management. Workers likely employed a combination of sledges, ramps, levers, and counterweights to transport massive stones from quarries, some of which were located tens of kilometers away. Archaeological evidence suggests that workers were organized into teams, with specialized roles including quarrying, transport, shaping, and placement, under the supervision of skilled overseers. Feeding, housing, and sustaining this workforce over decades required a sophisticated logistical infrastructure, revealing that the pyramid's construction was as much a social and administrative achievement as it was a technical one. Precision in alignment and geometry was central to the pyramid's construction. The base is nearly perfectly level, with variations of only a few centimeters over a span of more than 200 meters, and the sides are aligned to within a fraction of a degree to the cardinal points. Achieving this required systematic surveying techniques, possibly including sighting instruments, plumb lines, leveling devices, and careful observation of celestial bodies. The geometric exactness extends to the internal chambers, passageways, and corbelled ceilings, which were designed to distribute weight efficiently and prevent collapse. Such advanced understanding of structural mechanics demonstrates that the builders had empirical knowledge of forces, load-bearing principles, and long-term stability, integrating both architectural foresight and practical engineering. The internal design of the Great Pyramid further exemplifies sophisticated engineering. The King's Chamber, constructed from massive granite blocks, rests on a series of relieving chambers designed to distribute the immense weight of the stone above, preventing structural failure. The Grand Gallery, with its precise angles and height, likely functioned both as a passage and a weight management system, illustrating an advanced understanding of load distribution. Corbelled ceilings, precise jointing, and careful placement of stones reveal that the builders were acutely aware of the stresses and pressures exerted by the pyramid's immense mass. These internal features highlight a level of engineering knowledge that would remain unmatched for centuries, combining structural integrity with architectural sophistication. Astronomical alignment played a crucial role in the design of the Giza pyramids. The Great Pyramid sides are closely aligned with the cardinal points, and internal shafts appear to correspond with specific stars, such as Orion's belt and the circumpolar stars, which held significant religious and cosmological importance in ancient Egyptian belief. Such alignment suggests that the pyramids were conceived not merely as tombs but as cosmological instruments, integrating technical, spiritual, and observational knowledge. Translating celestial observation into architectural design on such a massive scale reflects a sophisticated capacity for abstract reasoning, long-term planning, and the integration of empirical observation with symbolic meaning.